Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Preface. The Airplane Flying Handbook is designed as a technical manual to introduce basic pilot skills and knowledge that are essential for piloting airplanes. It provides information on transition to other airplanes and the operation of various airplane systems. It is developed by the Flight Standards Service, Airman Testing's Standards Branch, in cooperation with various aviation educators and industry. This handbook is developed to assist student pilots learning to fly airplanes. It is also beneficial to pilots who wish to improve their flying proficiency and aeronautical knowledge, those pilots preparing for additional certificates or ratings, and flight instructors engaged in the instruction of both student and certificated pilots. It introduces the future pilot to the realm of flight and provides information and guidance in the performance of procedures and maneuvers required for pilot certification. Topics such as navigation and communication, meteorology, use of flight information publications, regulations, and aeronautical decision-making are available in other Federal Aviation Administration (FAA) publications. This handbook conforms to pilot training and certification concepts established by the FAA. There are different ways of teaching, as well as performing flight procedures and maneuvers, and many variations in the explanations of aerodynamic theories and principles. This handbook adopts a selective method and concept of flying airplanes. The discussion and explanations reflect the most commonly used practices and principles. Occasionally the word must or similar language is used where the desired action is deemed critical. The use of such language is not intended to add to, interpret, or relieve a duty imposed by Title 14 of the Code of Federal Regulations, 14 CFR. It is essential for persons using this handbook to also become familiar with and apply the pertinent parts of 14 CFR and the Aeronautical Information Manual, AIM. The AIM is available online at http://www.faa.gov/atpubs. Performance standards for demonstrating competence required for pilot certification are prescribed in the appropriate airplane practical test standard. The current Flight Standards Service Airman Training and Testing Material and Subject Matter Knowledge Codes for all airman certificates and ratings can be obtained from the Flight Standards Service website at http://av-info.faa.gov. The FAA greatly acknowledges the valuable assistance provided by many individuals and organizations throughout the aviation community, whose expertise contributed to the preparation of this handbook. This handbook supersedes FAA-H-8083-3 Airplane Flying Handbook, dated 1999. This handbook also supersedes AC-61-9B Pilot Transition Courses for Complex Single-Engine and Light Twin-Engine Airplanes, dated 1974, and related portions of AC-61-10A Private and Commercial Pilots Refresher Courses, dated 1972. This revision expands all technical subject areas from the previous edition, FAA-H-8083-3. It also incorporates new areas of safety concerns and technical information not previously covered. The chapters covering transitions to seaplanes and skiplanes have been removed. They will be incorporated into a new handbook under development, FAA-H-8083-23, Seaplane, Skiplane, and Float/Ski-Equipped Helicopter Operations Handbook. This handbook is available for download from the Flight Standards Service website at http://av-info.faa.gov. This website also provides information about availability of printed copies. This handbook is published by the U.S. Department of Transportation, Federal Aviation Administration, Airman Testing Standards Branch, AFS-630, P.O. Box 25082, Oklahoma City, OK 73125. Comments regarding this handbook should be sent in email form to afs630comments@faa.gov. AC00-2 Advisory Circular Checklist transmits the current status of FAA advisory circulars and other flight information publications. This checklist is available via the Internet at http://www.faa.gov/aba/html_2.html. End of preface. Chapter 1 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 1. Introduction to Flight Training. Purpose of Flight Training. The overall purpose of primary and intermediate flight training, as outlined in this handbook, is the acquisition and honing of basic airmanship skills. Airmanship can be defined as a sound acquaintance with the principles of flight, the ability to operate an airplane with competence and precision both on the ground and in the air, and the exercise of sound judgment that results in optimal operational safety and efficiency. Learning to fly an airplane has often been likened to learning to drive an automobile. This analogy is misleading, since an airplane operates in a different environment, three-dimensional. It requires a type of motor skill development that is more sensitive to this situation, such as coordination, the ability to use the hands and feet together subconsciously and in the proper relationship to produce desired results in the airplane. Timing, the application of muscular coordination at the proper instant to make flight and all maneuvers incident thereto a constant smooth process. Control touch, the ability to sense the action of the airplane and its probable actions in the immediate future with regard to attitude and speed variations by the sensing and evaluation of varying pressures and resistance of the control surfaces transmitted through the cockpit flight controls. Speed sense, the ability to sense instantly and react to any reasonable variation of airspeed. An airman becomes one with the airplane rather than a machine operator. An accomplished airman demonstrates the ability to assess a situation quickly and accurately and deduce the correct procedure to be followed under the circumstance. To analyze accurately the probable results of a given set of circumstances or of a proposed procedure, to exercise care and due regard for safety, to gauge accurately the performance of the aircraft, and to recognize personal limitations and limitations of the airplane and avoid approaching the critical points of each. The development of airmanship skills requires effort and dedication on the part of both the student pilot and the flight instructor, beginning with the very first training flight where proper habit formation begins, with the student being introduced to good operating practices. Every airplane has its own particular flight characteristics. The purpose of primary and intermediate flight training, however, is not to learn how to fly a particular make and model airplane. The underlying purpose of flight training is to develop skills and safe habits that are transferable to any airplane. Basic airmanship skills serve as a firm foundation for this. The pilot who has acquired necessary airmanship skills during training and demonstrates these skills by flying training-type airplanes with precision and safe flying habits will be able to easily transition to more complex and higher-performance airplanes. It should also be remembered that the goal of flight training is a safe and competent pilot, and that passing required practical tests for pilot certification is only incidental to this goal. Role of the FAA. The Federal Aviation Administration, FAA, is empowered by the U.S. Congress to promote aviation safety by prescribing safety standards for civil aviation. This is accomplished through the Code of Federal Regulations, CFRs, formerly referred to as Federal Aviation Regulations, FARs. Title 14 of the Code of Federal Regulations, 14 CFR Part 61, pertains to the certification of pilots, flight instructors, and ground instructors. 14 CFR Part 61 prescribes the eligibility, aeronautical knowledge, flight proficiency, and training and testing requirements for each type of pilot certificate issued. 14 CFR Part 67 prescribes the medical standards and certification procedures for issuing medical certificates for airmen and for remaining eligible for a medical certificate. 14 CFR Part 91 contains general operating and flight rules. The section is broad in scope and provides general guidance in the areas of general flight rules, visual flight rules, VFR, instrument flight rules, IFR, aircraft maintenance, and preventative maintenance and alterations. Within the FAA, the Flight Standards Service sets the aviation standards for airmen and aircraft operations in the United States and for American airmen and aircraft around the world. The FAA Flight Standards Service is headquartered in Washington, D.C., and is broadly organized into divisions based on work function: air transportation, aircraft maintenance, technical programs, a regulatory support division based in Oklahoma City, OK, and a general aviation and commercial division. Regional Flight Standards Division managers, one at each of the FAA's 9 regional offices, coordinate flight standards activities within their respective regions. The interface between the FAA Flight Standards Service and the aviation community/general public is the Local Flight Standards District Office, FSDO, Figure 1-1. The approximately 90 FSDOs are strategically located across the United States, each office having jurisdiction over a specific geographic area. The individual FSDO is responsible for all air activity occurring within its geographic boundaries. In addition to accident investigation and the enforcement of aviation regulations, the individual FSDO is responsible for the certification and surveillance of air carriers, air operators, flight schools/training centers, and airmen, including pilots and flight instructors. Each FSDO is staffed by aviation safety inspectors whose specialties include operations, maintenance, and avionics. General aviation operations inspectors are highly qualified and experienced aviators. Once accepted for the position, an inspector must satisfactorily complete a course of indoctrination training conducted at the FAA Academy, which includes airman evaluation and pilot testing techniques and procedures. Thereafter, the inspector must complete recurrent training on a regular basis. Among other duties, the FSDO inspector is responsible for administering FAA practical tests for pilot and flight instructor certificates and associated ratings. All questions concerning pilot certification and/or requests for other aviation information or services should be directed to the FSDO having jurisdiction in that particular geographic area. FSDO telephone numbers are listed in the blue pages of the telephone directory under United States Government Offices, Department of Transportation, Federal Aviation Administration. Role of the Pilot Examiner. Pilot and flight instructor certificates are issued by the FAA upon satisfactory completion of required knowledge and practical tests. The administration of these tests is an FAA responsibility normally carried out at the FSDO level by FSDO inspectors. The FAA, however, being a U.S. government agency, has limited resources and must prioritize its responsibilities. The agency's highest priority is the surveillance of certificated air carriers, with the certification of airmen, including pilots and flight instructors, having a lower priority. In order to satisfy the public need for pilot testing and certification services, the FAA delegates certain of these responsibilities as the need arises to private individuals who are not FAA employees. A designated pilot examiner, DPE, is a private citizen who is designated as a representative of the FAA administrator to perform specific, but limited, pilot certification tasks on behalf of the FAA, and may charge a reasonable fee for doing so. Generally, a DPE's authority is limited to accepting applications and conducting practical tests, leading to the issuance of specific pilot certificates and/or ratings. A DPE operates under the direct supervision of the FSDO that holds the examiner's designation file. A FSDO inspector is assigned to monitor the DPE's certification activities. Normally, the DPE is authorized to conduct these activities only within the designating FSDO's jurisdictional area. The FAA selects only highly qualified individuals to be designated pilot examiners. These individuals must have good industry reputations for professionalism, high integrity, a demonstrated willingness to serve the public, and adhere to FAA policies and procedures in certification matters. A designated pilot examiner is expected to administer practical tests with the same degree of professionalism, using the same methods, procedures, and standards as an FAA aviation safety inspector. It should be remembered, however, that a DPE is not an FAA aviation safety inspector. A DPE cannot initiate enforcement action, investigate accidents, or perform surveillance activities on behalf of the FAA. However, the majority of FAA practical tests at the recreational, private, and commercial pilot level are administered by FAA-designated pilot examiners. Role of the flight instructor. The flight instructor is the cornerstone of aviation safety. The FAA has adopted an operational training concept that places the full responsibility for student training on the authorized flight instructor. In this role, the instructor assumes the total responsibility for training the student pilot in all the knowledge areas and skills necessary to operate safely and competently as a certificated pilot in the National Airspace System. This training will include airmanship skills, pilot judgment and decision-making, and accepted good operating practices. An FAA-certificated flight instructor has to meet broad flying experience requirements, pass rigid knowledge and practical tests, and demonstrate the ability to apply recommended teaching techniques before being certificated. In addition, the flight instructor's certificate must be renewed every 24 months by showing continued success in training pilots, or by satisfactorily completing a flight instructor's refresher course or a practical test designed to upgrade aeronautical knowledge, pilot proficiency, and teaching techniques. A pilot training program is dependent on the quality of the ground and flight instruction the student pilot receives. A good flight instructor will have a thorough understanding of the learning process, knowledge of the fundamentals of teaching, and the ability to communicate effectively with the student pilot. A good flight instructor will use a syllabus and insist on correct techniques and procedures from the beginning of training so that the student will develop proper habit patterns. The syllabus should embody the building block method of instruction in which the student progresses from the known to the unknown. The course of instruction should be laid out so that each maneuver embodies the principles involving the performance of those previously undertaken. Consequently, through each new subject introduced, the student not only learns a new principle or technique, but broadens his or her application of those previously learned, and has his/her deficiencies in the previous maneuvers emphasized and made obvious. The flying habits of the flight instructor, both during flight instruction and as observed by students when conducting other pilot operations, have a vital effect on safety. Students consider their flight instructor to be a paragon of flying proficiency, whose flying habits they, consciously or unconsciously, attempt to imitate. For this reason, a good flight instructor will meticulously observe the safety practices taught the students. Additionally, a good flight instructor will carefully observe all regulations and recognized safety practices during all flight operations. Generally, the student pilot who enrolls in a pilot training program is prepared to commit considerable time, effort, and expense in pursuit of a pilot certificate. The student may tend to judge the effectiveness of the flight instructor and the overall success of the pilot training program solely in terms of being able to pass the requisite FAA practical test. A good flight instructor, however, will be able to communicate to the student that evaluation through practical tests is a mere sampling of pilot ability that is compressed into a short period of time. The flight instructor's role, however, is to train the total pilot. Sources of flight training. The major sources of flight training in the United States include FAA-approved pilot schools and training centers, non-certificated 14 CFR Part 61 flying schools, and independent flight instructors. FAA-approved schools are those flight schools certificated by the FAA as pilot schools under 14 CFR Part 141. See Figure 1-2. Application for certification is voluntary, and the school must meet stringent requirements for personnel, equipment, maintenance, and facilities. The school must operate in accordance with an established curriculum, which includes a training course outline, TCO, approved by the FAA. The TCO must contain student enrollment prerequisites, detailed description of each lesson, including standards and objectives, expected accomplishments and standards for each stage of training, and a description of the checks and tests used to measure a student's accomplishments. FAA-approved pilot school certificates must be renewed every 2 years. Renewal is contingent upon proof of continued high-quality instruction and a minimum level of instructional activity. Training at an FAA-certificated pilot school is structured. Because of this structured environment, the CFRs allow graduates of these pilot schools to meet the certification experience requirements of 14 CFR Part 61 with less flight time. Many FAA-certificated pilot schools have designated pilot examiners, DPEs, on their staff to administer FAA practical tests. Some schools have been granted examining authority by the FAA. A school with examining authority for a particular course or courses has the authority to recommend its graduates for pilot certificates or ratings without further testing by the FAA. A list of FAA-certificated pilot schools and their training courses can be found in Advisory Circular AC 140-2 FAA Certificated Pilot School Directory. FAA-approved training centers are certified under 14 CFR Part 142. Training centers, like certificated pilot schools, operate in a structured environment with approved courses and curricula and stringent standards for personnel, equipment, facilities, operating procedures, and record keeping. Training centers certificated under 14 CFR Part 142, however, specialize in the use of flight simulation, flight simulators, and flight training devices in their training courses. The overwhelming majority of flying schools in the United States are not certificated by the FAA. These schools operate under the provisions of 14 CFR Part 61. Many of these non-certificated flying schools offer excellent training and meet or exceed the standards required of FAA-approved pilot schools. Flight instructors employed by non-certificated flying schools, as well as independent flight instructors, must meet the same basic 14 CFR Part 61 flight instructor requirements for certification and renewal as those flight instructors employed by FAA-certificated pilot schools. In the end, any training program is dependent upon the quality of the ground and flight instruction a student pilot receives. Practical test standards. Practical tests for FAA pilot certificates and associated ratings are administered by FAA inspectors and designated pilot examiners in accordance with FAA-developed Practical Test Standards, PTS. See Figure 1-3. 14 CFR Part 61 specifies the areas of operation in which knowledge and skill must be demonstrated by the applicant. The CFRs provide the flexibility to permit the FAA to publish practical test standards containing the areas of operation and specific tasks in which competence must be demonstrated. The FAA requires that all practical tests be conducted in accordance with the appropriate practical test standards and the policies set forth in the introduction section of the Practical Test Standard Book. It must be emphasized that the Practical Test Standards book is a testing document rather than a teaching document. An appropriately rated flight instructor is responsible for training a pilot applicant to acceptable standards in all subject matter areas, procedures, and maneuvers included in the tasks within each area of operation in the appropriate practical test standard. The pilot applicant should be familiar with this book and refer to the standards it contains during training. However, the Practical Test Standard book is not intended to be used as a training syllabus. It contains the standards to which maneuvers/procedures on FAA practical tests must be performed and the FAA policies governing the administration of practical tests. Descriptions of tasks and information on how to perform maneuvers and procedures are contained in reference and teaching documents such as this handbook. A list of reference documents is contained in the introduction section of each Practical Test Standard book. Practical Test Standards may be downloaded from the Regulatory Support Division's AFS-600 website at http://afs600.faa.gov. Printed copies of Practical Test Standards can be purchased from the Superintendent of Documents, U.S. Government Printing Office, Washington, D.C. 20402. The official online bookstore website for the U.S. Government Printing Office is www.access.gpo.gov. Flight Safety Practices. In the interest of safety and good habit pattern formation, there are certain basic flight safety practices and procedures that must be emphasized by the flight instructor and adhered to by both instructor and student, beginning with the very first dual instruction flight. These include, but are not limited to, collision avoidance procedures, including proper scanning techniques and clearing procedures, runway incursion avoidance, stall awareness, positive transfer of controls, and cockpit workload management. Collision avoidance. All pilots must be alert for the potential for mid-air collision and near mid-air collisions. The general operating and flight rules in 14 CFR Part 91 set forth the concept of see and avoid. This concept requires that vigilance be maintained at all times by each person operating an aircraft, regardless of whether the operation is conducted under Instrument Flight Rules, IFR, or Visual Flight Rules, VFR. Pilots should also keep in mind their responsibility for continuously maintaining a vigilant outlook, regardless of the type of aircraft being flown and the purpose of the flight. Most mid-air collision accidents and reported near mid-air collision incidents occur in good VFR weather conditions and during the hours of daylight. Most of these accidents/incidents occur within 5 miles of an airport and or near navigation aids. The see and avoid concept relies on knowledge of the limitations of the human eye and the use of proper visual scanning techniques to help compensate for these limitations. The importance of and the proper techniques for visual scanning should be taught to the student pilot at the very beginning of flight training. The competent flight instructor should be familiar with the visual scanning and collision avoidance information contained in Advisory Circular AC 90-48, Pilot's Role in Collision Avoidance, and the Aeronautical Information Manual, AIM. There are many different types of clearing procedures. Most are centered around the use of clearing turns. The essential idea of the clearing turn is to be certain that the next maneuver is not going to proceed into another airplane's flight path. Some pilot training programs have hard and fast rules, such as requiring 2 90-degree turns in opposite directions before executing any training maneuver. Other types of clearing procedures may be developed by individual flight instructors. Whatever the preferred method, the flight instructor should teach the beginning student an effective clearing procedure and insist on its use. The student pilot should execute the appropriate clearing procedure before all turns and before executing any training maneuver. Proper clearing procedures, combined with proper visual scanning techniques, are the most effective strategy for collision avoidance. Runway incursion avoidance. A runway incursion is any occurrence at an airport involving an aircraft, vehicle, person, or object on the ground that creates a collision hazard or results in a loss of separation with an aircraft taking off, landing, or intending to land. The three major areas contributing to runway incursions are communications, airport knowledge, and cockpit procedures for maintaining orientation. Taxi operations require constant vigilance by the entire flight crew, not just the pilot taxiing the airplane. This is especially true during flight training operations. Both the student pilot and the flight instructor need to be continually aware of the movement and location of other aircraft and ground vehicles on the airport movement area. Many flight training activities are conducted at non-tower controlled airports. The absence of an operating airport control tower creates a need for increased vigilance on the part of pilots operating at those airports. Planning, clear communications, and enhanced situational awareness during airport surface operations will reduce the potential for surface incidents. Safe aircraft operations can be accomplished and incidents eliminated if the pilot is properly trained early on and, throughout his/her flying career, accomplishes standard taxi operating procedures and practices. This requires the development of formalized teaching of safe operating practices during taxi operations. The flight instructor is the key to this teaching. The flight instructor should instill in the student an awareness of the potential for runway incursion and should emphasize the runway incursion avoidance procedures contained in Advisory Circular AC 91-73, Part 91. Pilot and flight crew procedures during taxi operations, and Part 135 single pilot operations. Stall awareness. 14 CFR Part 61 requires that a student pilot receive and log flight training in stalls and stall recoveries prior to solo flight. During this training, the flight instructor should emphasize that the direct cause of every stall is an excessive angle of attack. The student pilot should fully understand that there are any number of flight maneuvers which may produce an increase in the wing's angle of attack, but the stall does not occur until the angle of attack becomes excessive. This critical angle of attack varies from 16 to 20 degrees, depending on the airplane design. The flight instructor must emphasize that low speed is not necessary to produce a stall. The wing can be brought to an excessive angle of attack at any speed. High pitch attitude is not an absolute indication of proximity to a stall. Some airplanes are capable of vertical flight with a corresponding low angle of attack. Most airplanes are quite capable of stalling at a level or near level pitch attitude. The key to stall awareness is the pilot's ability to visualize the wing's angle of attack in any particular circumstance, and thereby be able to estimate his/her margin of safety above stall. This is a learned skill that must be acquired early in flight training and carried through the pilot's entire flying career. The pilot must understand and appreciate factors such as airspeed, pitch attitude, load factor, relative wind, power setting, and aircraft configuration in order to develop a reasonably accurate mental picture of the wing's angle of attack at any particular time. It is essential to flight safety that a pilot take into consideration this visualization of the wing's angle of attack prior to entering any flight maneuver. Use of checklists. Checklists have been the foundation of pilot standardization and cockpit safety for years. The checklist is an aid to the memory and helps to ensure that critical items necessary for the safe operation of aircraft are not overlooked or forgotten. However, checklists are of no value if the pilot is not committed to its use. Without discipline and dedication to using the checklist at the appropriate times, the odds are on the side of error. Pilots who fail to take the checklist seriously become complacent, and the only thing that they can rely on is memory. The importance of consistent use of checklists cannot be overstated in pilot training. A major objective in primary flight training is to establish habit patterns that will serve pilots well throughout their entire flying career. The flight instructor must promote a positive attitude toward the use of checklists, and the student pilot must realize its importance. At a minimum, prepared checklists should be used for the following phases of flight: pre-flight inspection, before engine start, engine starting, before taxiing, before takeoff, after takeoff, cruise, descent, before landing, after landing, engine shutdown and securing. Positive transfer of controls. During flight training, there must always be a clear understanding between the student and flight instructor of who has control of the aircraft. Prior to any dual training flight, a briefing should be conducted that includes the procedure for the exchange of flight controls. The following 3-step process for the exchange of flight controls is highly recommended. When a flight instructor wishes the student to take control of the aircraft, he/she should say to the student, "You have the flight controls." The student should acknowledge immediately by saying, "I have the flight controls." The flight instructor confirms by again saying, "You have the flight controls." Part of the procedure should be a visual check to ensure that the other person actually has the flight controls. When returning the controls to the flight instructor, the student should follow the same procedure the instructor used when giving control to the student. The student should stay on the controls until the instructor says, "I have the flight controls." There should never be any doubt as to who is flying the aircraft at any one time. Numerous accidents have occurred due to a lack of communication or misunderstanding as to who actually had control of the aircraft, particularly between students and flight instructors. Establishing the above procedure during initial training will ensure the formation of a very beneficial habit pattern. End of Chapter 1.
Chapter 2, Part 1 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Ground Operations. Part 1. Visual Inspection. The accomplishment of a safe flight begins with careful visual inspection of the airplane. The purpose of the pre-flight visual inspection is twofold: to determine that the airplane is legally airworthy and that it is in condition for safe flight. The airworthiness of the airplane is determined in part by the following certificates and documents which must be on board the airplane when operated. See Figure 2-1. Airworthiness Certificate, Registration Certificate, FCC radio station license if required by the type of operation, airplane operating limitations, which may be in the form of an FAA-approved Airplane Flight Manual and/or Pilot's Operating Handbook, AFM/POH, placards, instrument markings, or any combination thereof. Airplane logbooks are not required to be kept in the airplane when it is operated. However, they should be inspected prior to flight to show that the airplane has had required tests and inspections. Maintenance records for the airframe and engine are required to be kept. There may also be additional propeller records. At a minimum, there should be an annual inspection within the preceding 12 calendar months. In addition, the airplane may also be required to have a 100-hour inspection in accordance with Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, Section 91.409b. If a transponder is to be used, it is required to be inspected within the preceding 24 calendar months. If the airplane is operated under Instrument Flight Rules, IFR, in controlled airspace, the pitot static system is also required to be inspected within the preceding 24 calendar months. The emergency locator transmitter, ELT, should also be checked. The ELT is battery-powered, and the battery replacement or recharge date should not be exceeded. Airworthiness directives, ADs, have varying compliance intervals and are usually tracked in a separate area of the appropriate airframe, engine, or propeller record. The determination of whether the airplane is in condition for safe flight is made by a pre-flight inspection of the airplane and its components. See Figure 2-2. The pre-flight inspections should be performed in accordance with a printed checklist provided by the airplane manufacturer for the specific make and model airplane. However, the following general areas are applicable to all airplanes. The pre-flight inspection of the airplane should begin while approaching the airplane on the ramp. The pilot should make note of the general appearance of the airplane, looking for obvious discrepancies, such as a landing gear out of alignment, structural distortion, skin damage, and dripping fuel or oil leaks. Upon reaching the airplane, all tie-downs, control locks, and chocks should be removed. Inside the cockpit, the inspection should start with the cabin door. If the door is hard to open or close, or if the carpeting or seats are wet from a recent rain, there is a good chance that the door, fuselage, or both are misaligned. This may be a sign of structural damage. The windshield and side windows should be examined for cracks and/or crazing. Crazing is the first stage of delamination of the plastic. Crazing decreases visibility, and a severely crazed window can result in near zero visibility due to the light refraction at certain angles to the sun. The pilot should check the seats, seat rails, and seat belt attach points for wear, cracks, and serviceability. The seat rail holes where the seat lock pins fit should also be inspected. The holes should be round and not oval. The pin and seat rail grips should also be checked for wear and serviceability. Inside the cockpit, 3 key items to be checked are 1. Battery and ignition switches off. 2. Control column locks removed. 3. Landing gear control down and locked. See Figure 2-3. The fuel selectors should be checked for proper operation in all positions, including the off position. Stiff selectors, or ones where the tank position is hard to find, are unacceptable. The primer should also be exercised. The pilot should feel resistance when the primer is both pulled out and pushed in. The primer should also lock securely. Faulty primers can interfere with proper engine operation. See Figure 2-4. The engine control should also be manipulated by slowly moving each through its full range to check for binding or stiffness. The airspeed indicator should be properly marked, and the indicator needle should read 0. If it does not, the instrument may not be calibrated correctly. Similarly, the vertical speed indicator, VSI, should also read 0 when the airplane is on the ground. If it does not, a small screwdriver can be used to zero the instrument. The VSI is the only flight instrument that a pilot has the prerogative to adjust. All others must be adjusted by an FAA-certificated repairman or mechanic. The magnetic compass is a required instrument for both VFR and IFR flight. It must be securely mounted with a correction card in place. The instrument face must be clear and the instrument case full of fluid. A cloudy instrument face, bubbles in the fluid, or a partially filled case renders the instrument unusable. See Figure 2-5. The gyro-driven attitude indicator should be checked before being powered. A white haze on the inside of the glass face may be a sign that the seal has been breached, allowing moisture and dirt to be sucked into the instrument. The altimeter should be checked against the ramp or field elevation after setting in the barometric pressure. If the variation between the known field elevation and the altimeter indication is more than 75 feet, its accuracy is questionable. The pilot should turn on the battery master switch and make note of the fuel quantity gauge indications for comparison with an actual visual inspection of the fuel tanks during the exterior inspection. Outer wing surfaces and tail section. The pilot should inspect for any signs of deterioration, distortion, and loose or missing rivets or screws, especially in the area where the outer skin attaches to the airplane structure. See Figure 2-6. The pilot should look along the wing spar rivet line, from the wingtip to the fuselage, for skin distortion. Any ripples and/or waves may be an indication of internal damage or failure. Loose or sheared aluminum rivets may be identified by the presence of black oxide, which forms rapidly when the rivet works free in its hole. Pressure applied to the skin adjacent to the rivet head will help verify the loosened condition of the rivet. When examining the outer wing surface, it should be remembered that any damage, distortion, or malformation of the wing leading edge renders the airplane unairworthy. Serious dents in the leading edge and disrepair of items such as stall strips and de-icer boots can cause the airplane to be aerodynamically unsound. Also, special care should be taken when examining the wingtips. Airplane wingtips are usually fiberglass. They are easily damaged and subject to cracking. The pilot should look at stop-drilled cracks for evidence of crack progression, which can, under some circumstances, lead to in-flight failure of the wingtip. The pilot should remember that fuel stains anywhere on the wing warrant further investigation, no matter how old the stains appear to be. Fuel stains are a sign of probable fuel leakage. On airplanes equipped with integral fuel tanks, evidence of fuel leakage can be found along rivet lines along the underside of the wing. Fuel and oil. Particular attention should be paid to the fuel quantity, type, and grade, and quality. See Figure 2-7. Many fuel tanks are very sensitive to airplane attitude when attempting to fuel for maximum capacity. Nosewheel strut extension, both high as well as low, can significantly alter the attitude, and therefore the fuel capacity. The airplane attitude can also be affected laterally by a ramp that slopes, leaving one wing slightly higher than another. Always confirm the fuel quantity indicated on the fuel gauges by visually inspecting the level of each tank. The type, grade, and color of fuel are critical to safe operation. The only widely available aviation gasoline, avgas, grade in the United States is low lead 100 octane or 100 LL. Avgas is dyed for easy recognition of its grade and has a familiar gasoline scent. Jet A, or jet fuel, is a kerosene-based fuel for turbine-powered airplanes. It has disastrous consequences when inadvertently introduced into reciprocating airplane engines. The piston engine operating on jet fuel may start, run, and power the airplane, but will fail because the engine has been destroyed from detonation. Jet fuel has a distinctive kerosene scent and is oily to the touch when rubbed between fingers. Jet fuel is clear or straw-colored, although it may appear dyed when mixed in a tank containing avgas. When a few drops of avgas are placed upon white paper, they evaporate quickly and leave just a trace of dye. In comparison, jet fuel is slower to evaporate and leaves an oily smudge. Jet fuel refueling trucks and dispensing equipment are marked with Jet A placards in white letters on a black background. Prudent pilots will supervise fueling to ensure that the correct tanks are filled with the right quantity, type, and grade of fuel. The pilot should always ensure that the fuel caps have been securely replaced following each fueling. Engines certificated for grades 80/87 or 91/96 avgas will run satisfactorily on 100 low lead. The reverse is not true. Fuel of a lower grade, octane, if found, should never be substituted for a required higher grade. Detonation will severely damage the engine in a very short period of time. Automotive gasoline is sometimes used as a substitute fuel in certain airplanes. Its use is acceptable only when the particular airplane has been issued a supplemental type certificate, STC, to both the airframe and engine allowing its use. Checking for water and other sediment contamination is a key pre-flight element. Water tends to accumulate in fuel tanks from condensation, particularly in partially filled tanks. Because water is heavier than fuel, it tends to collect in the low points of the fuel system. Water can also be introduced into the fuel system from deteriorated gas cap seals exposed to rain, or from the supplier's storage tanks and delivery vehicles. Sediment contamination can arise from dust and dirt entering the tanks during refueling or from deteriorating rubber fuel tanks or tank sealant. The best preventative measure is to minimize the opportunity for water to condense in the tanks. If possible, the fuel tank should be completely filled with the proper grade of fuel after each flight, or at least filled after the last flight of the day. The more fuel there is in the tanks, the less opportunity for condensation to occur. Keeping fuel tanks filled is also the best way to slow the aging of rubber fuel tanks and tank sealant. Sufficient fuel should be drained from the fuel strainer quick drain and from each fuel tank sump to check for fuel grade, color, water, dirt, and smell. If water is present, it will usually be in bead-like droplets, different in color, usually clear, sometimes muddy, in the bottom of the sample. In extreme cases, do not overlook the possibility that the entire sample, particularly a small sample, is water. If water is found in the first fuel sample, further samples should be taken until no water appears. Significant and/or consistent water or sediment contamination are grounds for further investigation by qualified maintenance personnel. Each fuel tank sump should be drained during pre-flight and after refueling. The fuel tank vent is an important part of a pre-flight inspection. Unless outside air is able to enter the tank as fuel is drawn out, the eventual result will be fuel gauge malfunction and/or fuel starvation. During the pre-flight inspection, the pilot should be alert for any signs of vent tubing damage as well as vent blockage. A functional check of the fuel vent system can be done simply by opening the fuel cap. If there is a rush of air when the fuel tank cap is cracked, there could be a serious problem with the vent system. The oil level should be checked during each pre-flight and rechecked with each refueling. Reciprocating airplane engines can be expected to consume a small amount of oil during normal operation. If the consumption grows or suddenly changes, qualified maintenance personnel should investigate. If line service personnel add oil to the engine, the pilot should ensure that the oil cap has been securely replaced. Landing gear, tires, and brakes. Tires should be inspected for proper inflation, as well as cuts, bruises, wear, bulges, embedded foreign object, and deterioration. As a general rule, tires with cord showing and those with cracked sidewalls are considered unairworthy. Brakes and brake systems should be checked for rust and corrosion. Loose nuts, bolts, alignment, brake pad, wear, cracks, signs of hydraulic fluid leakage, and hydraulic line security abrasion. An examination of the nose gear should include the shimmy damper, which is painted white, and the torque link, which is painted red, for proper servicing and general condition. All landing gear shock struts should also be checked for proper inflation. Engine and propeller. The pilot should make note of the condition of the engine cowling. See Figure 2-8. If the cowling rivet heads reveal aluminum oxide residue and chipped paint surrounding and radiating away from the cowling rivet heads, it is a sign that the rivets have been rotating until the holes have been elongated. If allowed to continue, the cowling may eventually separate from the airplane in flight. Certain engine-propeller combinations require installation of a prop spinner for proper engine cooling. In these cases, the engine should not be operated unless the spinner is present and properly installed. The pilot should inspect the propeller spinner and spinner mounting plate for security of attachment, any signs of chafing of propeller blades, and defects such as cracking. A cracked spinner is unairworthy. The propeller should be checked for nicks, cracks, pitting, corrosion, and security. The propeller hub should be checked for oil leaks, and the alternator generator drive belt should be checked for proper tension and signs of wear. When inspecting inside the cowling, the pilot should look for signs of fuel dye, which may indicate a fuel leak. The pilot should check for oil leaks, deterioration of oil lines, and to make certain that the oil cap, filter, oil cooler, and drain plug are secure. The exhaust system should be checked for white stains caused by exhaust leaks at the cylinder head or cracks in the stacks. The heat muff should also be checked for general condition and signs of cracks or leaks. The air filter should be checked for condition and secure fit, as well as hydraulic lines for deterioration and/or leaks. The pilot should also check for loose or foreign objects inside the cowling, such as birds' nests, shop rags, and/or tools. All visible wires and lines should be checked for security and condition. And lastly, when the cowling is closed, the cowling fasteners should be checked for security. Cockpit management. After entering the airplane, the pilot should first ensure that all necessary equipment, documents, checklists, and navigation charts appropriate for the flights are on board. If a portable intercom, headsets, or a handheld global positioning system, GPS, is used, the pilot is responsible for ensuring that the routing of wires and cables does not interfere with the motion or operation of any control. Regardless of what materials are to be used, they should be neatly arranged and organized in a manner that makes them readily available. The cockpit and cabin should be checked for articles that might be tossed about if turbulence is encountered. Loose items should be properly secured. All pilots should form the habit of good housekeeping. The pilot must be able to see inside and outside references. If the range of motion of an adjustable seat is inadequate, cushions should be used to provide the proper seating position. When the pilot is comfortably seated, the safety belt and shoulder harness, if installed, should be fastened and adjusted to a comfortably snug fit. The shoulder harness must be worn at least for the takeoff and landing, unless the pilot cannot reach or operate the controls with it fastened. The safety belt must be worn at all times when the pilot is seated at the controls. If the seats are adjustable, it is important to ensure that the seat is locked in position. Accidents have occurred as the result of seat movement during acceleration or pitch attitude changes during takeoffs or landings. When the seat suddenly moves too close or too far away from the controls, the pilot may be unable to maintain control of the airplane. 14 CFR Part 91 requires the pilot to ensure that each person on board is briefed on how to fasten and unfasten his or her safety belt, and, if installed, shoulder harness. This should be accomplished before starting the engine, along with a passenger briefing on the proper use of safety equipment and exit information. Airplane manufacturers have printed briefing cards available, similar to those used by airlines to supplement the pilot's briefing. End of Ground Operations, Part 1. Chapter 2, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Ground Operations, Part 2. Ground Operations. It is important that a pilot operates an airplane safely on the ground. This includes being familiar with standard hand signals that are used by ramp personnel. See Figure 2-9. Engine starting. The specific procedures for engine starting will not be discussed here, since there are as many different methods as there are different engines, fuel systems, and starting conditions. The before engine starting and engine starting checklist procedures should be followed. There are, however, certain precautions that apply to all airplanes. Some pilots have started the engine with the tail of the airplane pointed toward an open hangar door, parked automobiles, or a group of bystanders. This is not only discourteous, but may result in personal injury and damage to the property of others. Propeller blast can be surprisingly powerful. When ready to start the engine, the pilot should look in all directions to be sure that nothing is or will be in the vicinity of the propeller. This includes nearby persons and aircraft that could be struck by the propeller blast or the debris it might pick up from the ground. The anti-collision light should be turned on prior to engine start, even during daytime operations. At night, the position, navigation lights should also be on. The pilot should always call "clear" out of the side window and wait for a response from persons who may be nearby before activating the starter. When activating the starter, one hand should be kept on the throttle. This allows prompt response if the engine falters during starting, and allows the pilot to rapidly retard the throttle if revolutions per minute, RPM, are excessive after starting. A low RPM setting, 800 to 1000, is recommended immediately following engine start. It is highly undesirable to allow the RPM to race immediately after start, as there will be insufficient lubrication until the oil pressure rises. In freezing temperatures, the engine will also be exposed to potential mechanical distress until it warms and normal internal operating clearances are assumed. As soon as the engine is operating smoothly, the oil pressure should be checked. If it does not rise to the manufacturer's specified value, the engine may not be receiving proper lubrication and should be shut down immediately to prevent serious damage. Although quite rare, the starter motor may remain on and engaged after the engine starts. This can be detected by a continuous very high current draw on the ammeter. Some airplanes also have a starter engaged warning light, specifically for this purpose. The engine should be shut down immediately should this occur. Starters are small electric motors designed to draw large amounts of current for short periods of cranking. Should the engine fail to start readily, avoid continuous starter operation for periods longer than 30 seconds, without a cool-down period of at least 30 seconds to a minute. Some AFM-POH specify even longer. Their service life is drastically shortened from high heat through overuse. Hand propping. Even though most airplanes are equipped with electric starters, it is helpful if a pilot is familiar with the procedures and dangers involved in starting an engine by turning the propeller by hand. Hand propping. Due to the associated hazards, this method of starting should be used only when absolutely necessary and when proper precautions have been taken. An engine should not be hand-propped unless two people, both familiar with the airplane and hand-propping techniques, are available to perform the procedure. The person pulling the propeller blades through directs all activity and is in charge of the procedure. The other person, thoroughly familiar with the controls, must be seated in the airplane with the brakes set. As an additional precaution, chocks may be placed in front of the main wheels. If this is not feasible, the airplane's tail may be securely tied. Never allow a person unfamiliar with the controls to occupy the pilot seat when hand-propping. The procedure should never be attempted alone. When hand-propping is necessary, the ground surface near the propeller should be stable and free of debris. Unless a firm footing is available, consider relocating the airplane. Loose gravel, wet grass, mud, oil, ice, or snow might cause the person pulling the propeller through to slip into the rotating blades as the engine starts. Both participants should discuss the procedure and agree on voice commands and expected action. To begin the procedure, the fuel system and engine controls, tank selector, primer, pump, throttle, and mixture are set for a normal start. The ignition magneto switch should be checked to be sure that it is off. Then, the descending propeller blade should be rotated so that it assumes a position slightly above the horizontal. The person doing the hand-propping should face the descending blade squarely and stand slightly less than 1 arm's length from the blade. If a stance too far away were assumed, it would be necessary to lean forward in an unbalanced condition to reach the blade. This may cause the person to fall forward into the rotating blades when the engine starts. The procedure and commands for hand-propping are: person out front says, gas on, switch off, throttle closed, brakes set. Pilot seat occupant, after making sure the fuel is on, mixture is rich, ignition magneto switch is off, throttle is closed, and brakes set, says, gas on, switch off, throttle closed, brakes set. Person out front, after pulling the propeller through to prime the engine, says, brakes and contact. Pilot seat occupant checks the brakes set and turns the ignition switch on, then says, brakes and contact. The propeller is swung by forcing the blade downward rapidly, pushing with the palms of both hands. If the blade is gripped tightly with the fingers, the person's body may be drawn into the propeller blades should the engine misfire and rotate momentarily in the opposite direction. As the blade is pushed down, the person should step backward away from the propeller. If the engine does not start, the propeller should not be repositioned for another attempt until it is certain the ignition magneto switch is turned off. The words contact, mags on, and switch off, mags off, are used because they are significantly different from each other. Under noisy conditions or high winds, the words contact and switch off are less likely to be misunderstood than switch on and switch off. When removing the wheel chocks after the engine starts, it is essential that the pilot remember that the propeller is almost invisible. Incredible as it may seem, serious injuries and fatalities occur when people who have just started an engine walk or reach into the propeller arc to remove the chocks. Before the chocks are removed, the throttle should be set to idle and the chocks approached from the rear of the propeller. Never approach the chocks from the front or the side. The procedures for hand propping should always be in accordance with the manufacturer's recommendations and checklist. Special starting procedures are used when the engine is already warm, very cold, or when flooded or vapor locked. There will also be a different starting procedure when an external power source is used. Taxiing. The following basic taxi information is applicable to both nose-wheel and tail-wheel airplanes. Taxiing is the controlled movement of the airplane under its own power while on the ground. Since an airplane is moved under its own power between the parking area and the runway, the pilot must thoroughly understand and be proficient in taxi procedures. An awareness of other aircraft that are taking off, landing, or taxiing, and consideration for the right-of-way of others is essential to safety. When taxiing, the pilot's eyes should be looking outside the airplane, to the sides as well as the front. The pilot must be aware of the entire area around the airplane to ensure that the airplane will clear all obstructions and other aircraft. If at any time there is doubt about the clearance from an object, the pilot should stop the airplane and have someone check the clearance. It may be necessary to have the airplane towed or physically moved by a ground crew. It is difficult to set any rule for a single safe taxiing speed. What is reasonable and prudent under some conditions may be imprudent or hazardous under others. The primary requirements for safe taxiing are positive control, the ability to recognize potential hazards in time to avoid them, and the ability to stop or turn where and when desired, without undue reliance on the brakes. Pilots should proceed at a cautious speed on congested or busy ramps. Normally, the speed should be at the rate where movement of the airplane is dependent on the throttle. That is, slow enough so when the throttle is closed, the airplane can be stopped promptly. When yellow taxiway centerline stripes are provided, they should be observed unless necessary to clear airplanes or obstruction. When taxiing, it is best to slow down before attempting a turn. Sharp, high-speed turns place undesirable side loads on the landing gear and may result in an uncontrollable swerve or a ground loop. This swerve is most likely to occur when turning from a downwind heading toward an upwind heading. In moderate to high wind conditions, pilots will note the airplane's tendency to weather vane or turn into the wind when the airplane is proceeding crosswind. When taxiing at appropriate speeds in no-wind conditions, the aileron and elevator control surfaces have little or no effect on directional control of the airplane. The controls should not be considered steering devices and should be held in a neutral position. Their proper use while taxiing in windy conditions will be discussed later. See Figure 2-10. Steering is accomplished with rudder pedals and brakes. To turn the airplane on the ground, the pilot should apply rudder in the desired direction of turn and use whatever power or brake that is necessary to control the taxi speed. The rudder pedal should be held in the direction of the turn until just short of the point where the turn is to be stopped. Rudder pressure is then released, or opposite pressure is applied as needed. More engine power may be required to start the airplane moving forward or to start a turn than is required to keep it moving in any given direction. When using additional power, the throttle should immediately be retarded once the airplane begins moving to prevent excessive acceleration. When first beginning to taxi, the brakes should be tested for proper operation as soon as the airplane is put in motion. Applying power to start the airplane, moving forward slowly, then retarding the throttle and simultaneously applying pressure smoothly to both brakes does this. If braking action is unsatisfactory, the engine should be shut down immediately. The presence of moderate to strong headwinds and/or a strong propeller slipstream makes the use of the elevator necessary to maintain control of the pitch attitude while taxiing. This becomes apparent when considering the lifting action that may be created on the horizontal tail surfaces by either of those two factors. The elevator control in nosewheel type airplanes should be held in the neutral position, while in tailwheel type airplanes it should be held in the aft position to hold the tail down. Downwind taxiing will usually require less engine power after the initial ground roll is begun, since the wind will be pushing the airplane forward. See Figure 2-11. To avoid overheating the brakes when taxiing downwind, keep engine power to a minimum. Rather than continuously riding the brakes to control speed, it is better to apply brakes only occasionally. Other than sharp turns at low speed, the throttle should always be at idle before the brakes are applied. It is a common student error to taxi with a power setting that requires controlling taxi speed with the brakes. This is the aeronautical equivalent of driving an automobile with both the accelerator and brake pedals depressed. When taxiing with a quartering headwind, the wing on the upwind side will tend to be lifted by the wind unless the aileron control is held in that direction. Upwind aileron up. See Figure 2-12. Moving the aileron into the up position reduces the effect of the wind striking that wing, thus reducing the lifting action. This control movement will also cause the downwind aileron to be placed in the down position, thus a small amount of lift and drag on the downwind wing, further reducing the tendency of the upwind wing to rise. When taxiing with a quartering tailwind, the elevator should be held in the down position, and the upwind aileron down. See Figure 2-13. Since the wind is striking the airplane from behind, these control positions reduce the tendency of the wind to get under the tail and the wing and to nose the airplane over. The application of these crosswind taxi corrections helps to minimize the weather vaning tendency and ultimately results in making the airplane easier to steer. Normally, all turns should be started using the rudder pedal to steer the nose wheel. To tighten the turn after full pedal deflection is reached, the brake may be applied as needed. When stopping the airplane, it is advisable to always stop with the nose wheel straight ahead to relieve any side load on the nose wheel and to make it easier to start moving ahead. During crosswind taxiing, even the nose wheel type airplane has some tendency to weather vane. However, the weather vaning tendency is less than in tailwheel type airplanes because the main wheels are located farther aft, and the nose wheel's ground friction helps to resist the tendency. See Figure 2-14. The nose wheel linkage from the rudder pedals provides adequate steering control for safe and efficient ground handling, and normally only rudder pressure is necessary to correct for a crosswind. Before takeoff check. The before takeoff check is the systematic procedure for making a check of the engine, controls, systems, instruments, and avionics prior to flight. Normally, it is performed after taxiing to a position near the takeoff end of the runway. Taxiing to that position usually allows sufficient time for the engine to warm up to at least minimum operating temperatures. This ensures adequate lubrication and internal engine clearances before being operated at high power settings. Many engines require that the oil temperature reach a minimum value as stated in the AFM-POH before high power is applied. Air-cooled engines generally are closely cowled and equipped with pressure baffles that direct the flow of air to the engine in sufficient quantities for cooling in flight. On the ground, however, much less air is forced through the cowling and around the baffling. Prolonged ground operations may cause cylinder overheating long before there is an indication of rising oil temperature. Cowl flaps, if available, should be set according to the AFM-POH. Before beginning the before takeoff check, the airplane should be positioned clear of other aircraft. There should not be anything behind the airplane that might be damaged by the prop blast. To minimize overheating during engine run-up, it is recommended that the airplane be headed as nearly as possible into the wind. After the airplane is properly positioned for the run-up, it should be allowed to roll forward slightly so that the nose wheel or tail wheel will be aligned fore and aft. During the engine run-up, the surface under the airplane should be firm, a smooth, paved, or turf surface if possible, and free of debris. Otherwise, the propeller may pick up pebbles, dirt, mud, sand, or other loose objects and hurl them backwards. This damages the propeller and may damage the tail of the airplane. Small chips in the leading edge of the propeller form stress risers or lines of concentrated high stress. These are highly undesirable and may lead to cracks and possible propeller blade failure. While performing the engine run-up, the pilot must divide attention inside and outside the airplane. If the parking brake slips, or if application of the toe brakes is inadequate for the amount of power applied, the airplane could move forward unnoticed if attention is fixed inside the airplane. Each airplane has different features and equipment, and the before takeoff checklist provided by the airplane manufacturer or operator should be used to perform the run-up. After landing. During the after landing roll, the airplane should be gradually slowed to normal taxi speed before turning off the landing runway. Any significant degree of turn at faster speeds could result in ground looping and subsequent damage to the airplane. To give full attention to controlling the airplane during the landing roll, the after landing check should be performed only after the airplane is brought to a complete stop, clear of the active runway. There have been many cases of the pilot mistakenly grasping the wrong handle and retracting the landing gear instead of the flaps, due to the improper division of attention while the airplane was moving. However, this procedure may be modified if the manufacturer recommends that specific after-landing items be accomplished during landing rollout. For example, when performing a short-field landing, the manufacturer may recommend retracting the flaps on rollout to improve braking. In this situation, the pilot should make a positive identification of the flap control and retract the flaps. Clear of runway. Because of different features and equipment in various airplanes, the after-landing checklist provided by the manufacturer should be used. Some of the items may include flaps, identify and retract, cowl flaps, open, propeller control, full increase, trim tabs, set. Parking. Unless parking in a designated supervised area, the pilot should select a location and heading which will prevent the propeller or jet blast of other airplanes from striking the airplane broadside. Whenever possible, the airplane should be parked headed into the existing or forecast wind. After stopping on the desired heading, the airplane should be allowed to roll straight ahead enough to straighten the nose wheel or tail wheel. Engine shutdown. Finally, the pilot should always use the procedures in the manufacturer's checklist for shutting down the engine and securing the airplane. Some of the important items include: set the parking brakes on, set throttle to idle or 1000 RPM. If turbocharged, observe the manufacturer's spool down procedure. Turn ignition switch off, then on at idle to check for proper operation of switch in the off position. Set propeller control, if equipped, to full increase. Turn electrical units and radios off. Set mixture control to idle cutoff. Turn ignition switch to off when engine stops. Turn master electrical switch to off. Install control lock. Post-flight. A flight is never complete until the engine is shut down and the airplane is secured. A pilot should consider this an essential part of any flight. Securing and servicing. After engine shutdown and deplaning passengers, the pilot should accomplish a post-flight inspection. This includes checking the general condition of the aircraft. For departure, the oil should be checked and fuel added if required. If the aircraft is going to be inactive, it is a good operating practice to fill the tanks to the top to prevent water condensation from forming. When the flight is completed for the day, the aircraft should be hangared or tied down and the flight controls secured. End of Ground Operations, Part 2.
Chapter 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 3. Basic Flying Maneuvers. The Four Fundamentals. There are four fundamental basic flight maneuvers upon which all flying tasks are based: straight and level flight, turns, climbs, and descents. All controlled flight consists of either one or a combination of more than one of these basic maneuvers. If a student pilot is able to perform these maneuvers well, and the student's proficiency is based on accurate feel and control analysis rather than mechanical movements, the ability to perform any assigned maneuver will only be a matter of obtaining a clear visual and mental conception of it. The flight instructor must impart a good knowledge of these basic elements to the student and must combine them and plan their practice so that perfect performance of each is instinctive without conscious effort. The importance of this to the success of flight training cannot be overemphasized. As the student progresses to more complex maneuvers, discounting any difficulties in visualizing the maneuvers, most students' difficulties will be caused by a lack of training, practice, or understanding of the principles of one or more of these fundamentals. Effects and use of the controls. In explaining the functions of the controls, the instructor should emphasize that the controls never change in the results produced in relation to the pilot. The pilot should always be considered the center of movement of the airplane, or the reference point from which the movements of the airplane are judged and described. The following will always be true regardless of the airplane's attitude in relation to the earth. When back pressure is applied to the elevator control, the airplane's nose rises in relation to the pilot. When forward pressure is applied to the elevator control, the airplane's nose lowers in relation to the pilot. When right pressure is applied to the aileron control, the airplane's right wing lowers in relation to the pilot. When left pressure is applied to the aileron control, the airplane's left wing lowers in relation to the pilot. When pressure is applied to the right rudder pedal, the airplane's nose moves, yaws, to the right in relation to the pilot. When pressure is applied to the left rudder pedal, the airplane's nose moves, yaws, to the left in relation to the pilot. The preceding explanation should prevent the beginning pilot from thinking in terms of up or down in respect to the earth, which is only a relative state to the pilot. It will also make understanding of the functions of the controls much easier, particularly when performing steep bank turns and the more advanced maneuvers. Consequently, the pilot must be able to properly determine the control application required to place the plane in any attitude or flight condition that is desired. The flight instructor should explain that the controls will have a natural, live pressure while in flight, and that they will remain in neutral position of their own accord if the plane is trimmed properly. With this in mind, the pilot should be cautioned never to think of movement of the controls, but of exerting force on them against this live pressure or resistance. Movement of the controls should not be emphasized. It is the duration and the amount of force exerted on them that affects the displacement of the control surfaces and maneuvers the airplane. The amount of force the airflow exerts on a control surface is governed by the airspeed and the degree that the surface is moved out of its neutral or streamlined position. Since the airspeed will not be the same in all maneuvers, the actual amount the control surfaces are moved is of little importance, but it is important that the pilot maneuver the airplane by applying sufficient control pressure to obtain a desired result, regardless of how far the control surfaces are actually moved. The controls should be held lightly with the fingers, not grabbed and squeezed. Pressure should be exerted on the control yoke with the fingers. A common error in beginning pilots is a tendency to choke the stick. This tendency should be avoided as it prevents the development of feel, which is an important part of aircraft control. The pilot's feet should rest comfortably against the rudder pedals. Both heels should support the weight of the feet on the cockpit floor, with the ball of each foot touching the individual rudder pedals. The legs and feet should not be tense. They must be relaxed, just as when driving an automobile. When using the rudder pedals, pressure should be applied smoothly and evenly by pressing with the ball of one foot. Since the rudder pedals are interconnected and act in opposite directions, when pressure is applied to one pedal, pressure on the other must be relaxed proportionately. When the rudder pedal must be moved significantly, heavy pressure changes should be made by applying the pressure with the ball of the foot while the heels slide along the cockpit floor. Remember, the ball of each foot must rest comfortably on the rudder pedals so that even slight pressure changes can be felt. In summary, during flight, it is the pressure the pilot exerts on the control yoke and rudder pedals that causes the plane to move about its axes. When a control surface is moved out of its streamlined position, even slightly, the air flowing past it will exert a force against it and will try to return it to its streamlined position. It is this force that the pilot feels as pressure on the control yoke and the rudder pedals. Feel of the airplane. The ability to sense a flight condition without relying on cockpit instrumentation is often called feel of the airplane, but senses in addition to feel are involved. Sounds, inherent to flight, are an important sense in developing feel. The air that rushes past the modern light plane cockpit cabin is often masked by soundproofing, but it can still be heard. When the level of the sound increases, it indicates that airspeed is increasing. Also, the power plant emits distinctive sound patterns in different conditions of flight. The sound of the engine in cruise flight may be different from that in a climb, and different again from that in a dive. When power is used in fixed-pitch propeller airplanes, the loss of RPM is particularly noticeable. The amount of noise that can be heard will depend on how much the slipstream masks it out. But the relationship between the slipstream noise and the power plant noise aids the pilot in estimating not only the present airspeed but the trend of the airspeed. There are three sources of actual feel that are very important to the pilot. One is the pilot's own body as it responds to the forces of acceleration. The G loads imposed on the airframe are also felt by the pilot. Centripetal accelerations force the pilot down into the seat or raise the pilot against the seat belt. Radial accelerations, as they produce slips and skids of the airframe, shift the pilot from side to side in the seat. These forces need not be strong, only perceptible by the pilot to be useful. An accomplished pilot who has excellent feel for the airplane will be able to detect even the minutest change. The response of the aileron and rudder controls to the pilot's touch is another element of feel, and is one that provides direct information concerning airspeed. As previously stated, control surfaces move in the airstream and meet resistance proportional to the speed of the airstream. When the airstream is fast, the controls are stiff and hard to move. When the airstream is slow, the controls move easily, but must be deflected a greater distance. The pressure that must be exerted on the controls to effect a desired result, and the lag between the movement and the response of the airplane become greater as airspeed decreases. Another type of feel comes to the pilot through the airframe. It consists mainly of vibration. An example is the aerodynamic buffeting and shaking that precedes a stall. Kinesthesia, or the sensing of changes in direction or speed of motion, is one of the most important senses a pilot can develop. When properly developed, kinesthesia can warn the pilot of changes in airspeed and or the beginning of a settling or mushing of the airplane. The senses that contribute to feel of the airplane are inherent in every person. However, feel must be developed. The flight instructor should direct the beginning pilot to be attuned to these senses and teach an awareness of their meaning as it relates to the various conditions of flight. To do this effectively, the flight instructor must fully understand the difference between perceiving something and merely noticing it. It is a well-established fact that the pilot who develops a feel for the airplane early in flight training will have little difficulty with advanced flight maneuvers. Attitude flying. In contact, VFR flying, flying by attitude means visually establishing the airplane's attitude with reference to the natural horizon. See Figure 3-1. Attitude is the angular difference measured between an airplane's axis and the line of the Earth's horizon. Pitch attitude is the angle formed by the longitudinal axis, and bank attitude is the angle formed by the lateral axis. Rotation about the airplane's vertical axis, yaw, is termed an attitude relative to the airplane's flight path, but not relative to the natural horizon. In attitude flying, airplane control is composed of four components: pitch control, bank control, power control, and trim. Pitch control is the control of the airplane about the lateral axis by using the elevator to raise and lower the nose in relation to the natural horizon. Bank control is control of the airplane about the longitudinal axis by the use of ailerons to attain a desired bank angle in relation to the natural horizon. Power control is used when the flight situation indicates a need for a change in thrust. Trim is used to relieve all possible control pressures held after a desired attitude has been attained. The primary rule for attitude flying is attitude plus power equals performance. Integrated flight instruction. When introducing basic flight maneuvers to a beginning pilot, it is recommended that the integrated or composite method of flight instruction be used. This means the use of outside references and flight instruments to establish and maintain desired flight attitudes and airplane performance. See Figure 3-2. When beginning pilots use this technique, they achieve a more precise and competent overall piloting ability. Although this method of airplane control may become second nature with experience, the beginning pilot must make a determined effort to master the technique. The basic elements of which are as follows. The airplane's attitude is established and maintained by positioning the airplane in relation to the natural horizon. At least 90% of the pilot's attention should be devoted to this end, along with scanning for other airplanes. If, during a recheck of the pitch and/or bank, either or both are found to be other than desired, an immediate correction is made to return the airplane to the proper attitude. Continuous checks and immediate corrections will allow little chance for the airplane to deviate from the desired heading, altitude, and flight path. The airplane's attitude is confirmed by referring to the flight instruments and its performance checked. If airplane performance, as indicated by flight instruments, indicates a need for correction, a specific amount of correction must be determined, then applied with reference to the natural horizon. The airplane's attitude and performance are then rechecked by referring to flight instruments. The pilot then maintains the corrected attitude by reference to the natural horizon. The pilot should monitor the airplane's performance by making numerous quick glances at the flight instruments. No more than 10% of the pilot's attention should be inside the cockpit. The pilot must develop the skill to instantly focus on the appropriate flight instrument and then immediately return to the outside reference to control the airplane's attitude. The pilot should become familiar with the relationship between outside references to the natural horizon and the corresponding indications on flight instruments inside the cockpit. For example, a pitch attitude adjustment may require a movement of the pilot's reference point on the airplane of several inches in relation to the natural horizon, but correspond to a small fraction of an inch movement of the reference bar on the airplane's attitude indicator. Similarly, a deviation from desired bank, which is very obvious when referencing the wingtip's position relative to the natural horizon, may be nearly imperceptible on the airplane's attitude indicator to a beginning pilot. The use of integrated flight instruction does not and is not intended to prepare pilots for flight in instrument weather conditions. The most common error made by the beginning student is to make pitch or bank corrections while still looking inside the cockpit. Control pressure is applied, but the beginning pilot, not being familiar with the intricacies of flight by references to instruments, including such things as instrument lag and gyroscopic precession, will invariably make excessive attitude corrections and end up chasing the instruments. Airplane attitude, by reference to the natural horizon, however, is immediate in its indications, accurate and presented many times larger than any instrument could be. Also, the beginning pilot must be made aware that any time, for whatever reason, airplane attitude by reference to that horizon cannot be established and/or maintained, the situation should be considered a bona fide emergency. Straight and level flight. It is impossible to emphasize too strongly the necessity for forming correct habits of flying straight and level. All other flight maneuvers are in essence deviations from this fundamental flight maneuver. Many flight instructors and students are prone to believe that perfection in straight and level flight will come of itself, but such is not the case. It is not uncommon to find a pilot whose basic flying ability consistently falls just short of minimum expected standards, and upon analyzing the reasons for the shortcomings, to discover that the cause is the inability to fly straight and level properly. Straight and level flight is flight in which a constant heading and altitude are maintained. It is accomplished by making immediate and measured corrections for deviations in direction and altitude from unintentional slight turns, descents, and climbs. Level flight, at first, is a matter of consciously fixing the relationship of the position of some portion of the airplane, used as a reference point with the horizon. In establishing the reference points, the instructor should place the airplane in a desired position and aid the student in selecting reference points. The instructor should be aware that no two pilots see the relationship exactly the same. The references will depend on where the pilot is sitting, the pilot's height, whether short or tall, and the pilot's manner of sitting. It is, therefore, important that during the fixing of this relationship, the pilots sit in a normal manner. Otherwise, the points will not be the same when the normal position is resumed. In learning to control the airplane in level flight, it is important that the student be taught to maintain a light grip on flight controls, and that the control forces desired be exerted lightly and just enough to produce the desired result. The student should learn to associate the apparent movement of the references with the forces which produce it. In this way, the student can develop the ability to regulate the change desired in the airplane's attitude by the amount and direction of forces applied to the controls without the necessity of referring to instrument or outside references for each minor correction. The pitch attitude for level flight, constant altitude, is usually obtained by selecting some portion of the airplane's nose as a reference point and then keeping that point in a fixed position relative to the horizon. See Figure 3-3. Using the principles of attitude flying, that position should be cross-checked occasionally against the altimeter to determine whether or not pitch attitude is correct. If altitude is being gained or lost, the pitch attitude should be readjusted in relation to the horizon, and then the altimeter rechecked to determine if altitude is now being maintained. The application of forward or back elevator pressure is used to control this attitude. The pitch information obtained from the attitude indicator also will show the position of the nose relative to the horizon and will indicate whether elevator pressure is necessary to change the pitch attitude to return to level flight. However, the primary reference source is the natural horizon. In all normal maneuvers, the term increase the pitch attitude implies raising the nose in relation to the horizon. The term decreasing pitch attitude means lowering the nose. Straight flight, laterally level flight, is accomplished by visually checking the relationship of the airplane's wingtips with the horizon. Both wingtips should be equidistant above and below the horizon, depending on whether the plane is a high wing or low wing type. And any necessary adjustment should be made with the ailerons, noting the relationship of control pressure and the airplane's attitude. See Figure 3-4. The student should understand that any time the wings are banked, even though very slightly, the plane will turn. The objective of straight and level flight is to detect small deviations from laterally level flight as soon as they occur, necessitating only small corrections. Reference to the heading indicator should be made to note any change in direction. Continually observing the wingtips has advantages other than being the only positive check for leveling wings. It also helps divert the pilot's attention from the airplane's nose, prevents a fixed stare, and automatically expands the pilot's area of vision by increasing the range necessary for the pilot's vision to cover. In practicing straight and level flight, the wingtips can be used not only for establishing the airplane's lateral level attitude or bank, but to a lesser degree its pitch attitude. This is noted only for assistance in learning straight and level flight and is not a recommended practice for normal operations. The scope of a student's vision is also very important, for if it is obscured, the student will tend to look out to one side continually, usually the left, and consequently lean that way. This not only gives the student a biased angle from which to judge, but also causes the student to exert unconscious pressure on the controls in that direction, which results in dragging a wing. With the wings approximately level, it is possible to maintain straight flight by simply exerting the necessary forces on the rudder in the desired direction. However, the instructor should point out that the practice of using rudder alone is not correct and may make precise control of the airplane difficult. Straight and level flight requires almost no application of control pressures if the airplane is properly trimmed and the air is smooth. For that reason, the student must not form the habit of constantly moving the controls unnecessarily. The student must learn to recognize when corrections are necessary and then to make the measured response easily and naturally. To obtain the proper conception of the forces required on the rudder during straight and level flight, the airplane must be held level. One of the most common faults of beginning students is the tendency to concentrate on the nose of the airplane and attempting to hold the wings level by observing the curvature of the nose cowling. With this method, the reference line is very short, and its deviation, particularly if very slight, can go unnoticed. Also, a very small deviation from level by this short reference line becomes considerable at the wing tips and results in appreciable dragging of one wing. This attitude requires the use of additional rudder to maintain straight flight, giving a false conception of neutral control forces. The habit of dragging one wing and compensating with rudder pressure, if allowed to develop, is particularly hard to break, and if not corrected, will result in considerable difficulty in mastering other flight maneuvers. For all practical purposes, the airspeed will remain constant in straight and level flight with a constant power setting. Practice of intentional airspeed changes by increasing or decreasing the power will provide an excellent means of developing proficiency in maintaining straight and level flight at various speeds. Significant changes in airspeed will, of course, require considerable changes in pitch attitude and pitch trim to maintain altitude. Pronounced changes in pitch attitude and trim will also be necessary as the flaps and landing gear are operated. Common errors in performance of straight and level flight are attempting to use improper reference points on the airplane to establish attitude, forgetting the location of pre-selected reference points on subsequent flights, attempting to establish or correct airplane attitude using flight instruments rather than outside visual reference, attempting to maintain direction using only rudder control, habitually flying with one wing low, chasing the flight instruments rather than adhering to the principles of attitude flying, too tight a grip on the flight controls resulting in over-control and lack of feel, pushing or pulling on flight controls rather than exerting pressure against the airstream, improper scanning, and or devoting insufficient time to outside visual reference, head in the cockpit. Fixation on the nose, pitch attitude, reference point. Unnecessary or inappropriate control inputs. Failure to make timely and measured control inputs when deviations from straight and level flight are detected. Inadequate attention to sensory inputs in developing feel for the airplane. Trim control. The airplane is designed so that the primary flight controls, rudder, aileron, and elevator, are streamlined with the non-movable airplane surfaces when the airplane is cruising straight and level at normal weight and loading. If the airplane's flying out of that basic balance condition, one or more of the control surfaces is going to have to be held out of its streamlined position for continuous control input. The use of trim tabs relieves the pilot of this requirement. Proper trim technique is a very important and often overlooked basic flying skill. An improperly trimmed airplane requires constant control pressures, produces pilot tension and fatigue, distracts the pilot from scanning, and contributes to abrupt and erratic airplane attitude control. Because of their relatively low power and speed, not all light airplanes have a complete set of trim tabs that are adjustable from the cockpit. In airplanes where rudder, aileron, and elevator trim are available, a definite sequence of trim application should be used. Elevator stabilator should be trimmed first to relieve the need for control pressure to maintain constant airspeed, pitch attitude. Attempts to trim the rudder at varying airspeed are impractical to propeller-driven airplanes because of the change in the torque-correcting offset of the vertical fin. Once a constant airspeed, pitch attitude has been established, the pilot should hold the wings level with the aileron pressure while rudder pressure is trimmed out. Aileron trim should be adjusted to relieve any lateral control yoke pressure. A common trim control error is the tendency to overcontrol the plane with the trim adjustments. To avoid this, the pilot must learn to establish and hold the airplane in a desired attitude using the primary flight controls. The proper attitude should be established with reference to the horizon, then verified by reference to the performance indications on the flight instruments. The pilot should then apply trim in the above sequence to relieve whatever hand and foot pressure had been required. The pilot must avoid using the trim to establish or correct airplane attitude. The airplane attitude must be established and held first, then control pressures trimmed out so that the airplane will maintain the desired attitude in hands-off flight. Attempting to fly the airplane with trim tabs is a common fault in the basic flying technique even among experienced pilots. A properly trimmed airplane is an indication of good piloting skills. Any control pressures the pilot feels should be the result of deliberate pilot control input during a planned change of airplane attitude, not a result of pressures being applied by the airplane because the pilot is allowing it to assume control. End Chapter 3, Part 1. Recording by Dale Latham. Chapter 3, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 3, Part 2. Level turns. A turn is made by banking the wings in the direction of the desired turn. A specific angle of bank is selected by the pilot, control pressures applied to achieve the desired bank angle, and appropriate control pressures exerted to maintain the desired bank angle once it is established. See Figure 3-5. All four primary controls are used in close coordination when making turns. Their functions are as follows. The ailerons bank the wings and so determine the rate of turn at any given airspeed. The elevator moves the nose of the airplane up or down in relation to the pilot and perpendicular to the wings. Doing that, it both sets the pitch attitude in the turn and pulls the nose of the airplane around the turn. The throttle provides thrust, which may be used for airspeed to tighten a turn. The rudder offsets any yaw effects developed by other controls. The rudder does not turn the airplane. For purposes of this discussion, turns are divided into three classes: shallow turns, medium turns, and steep turns. Shallow turns are those in which the bank, less than approximately 20 degrees, is so shallow that the inherent lateral stability of the plane is acting to level the wings unless some aileron is applied to maintain the bank. Medium turns are those resulting from a degree bank, approximately 20 degrees to 45 degrees, at which the airplane remains at a constant bank. Steep turns are those resulting from a degree of bank, 45 degrees or more, at which the overbanking tendency of an airplane overcomes stability and the bank increases unless aileron is applied to prevent it. Changing the direction of the wings lift toward one side or the other causes the airplane to be pulled in that direction. See Figure 3-6. Applying coordinated aileron and rudder to bank the airplane in the direction of the desired turn does this. When an airplane is flying straight and level, the total lift is acting perpendicular to the wings and to the earth. As the airplane is banked into a turn, the lift then becomes the resultant of two components. One, the vertical lift component, continues to act perpendicular to the earth and opposes gravity. Second, the horizontal lift component, centripetal, acts parallel to the earth's surface and opposes inertia, apparent centrifugal force. These two lift components act at right angles to each other, causing the resultant total lifting force to act perpendicular to the banked wing of the airplane. It is the horizontal lift component that actually turns the airplane, not the rudder. When applying aileron to bank the airplane, the lowered aileron on the rising wing produces a greater drag than the raised aileron on the lowering wing. See Figure 3-7. This increased aileron yaws the plane towards the rising wing, or opposite to the direction of turn. To counteract this adverse yawing moment, rudder pressure must be applied simultaneously with aileron in the desired direction of the turn. This action is required to produce a coordinated turn. After the bank has been established in a medium banked turn, all pressure applied to the ailerons may be relaxed. The airplane will remain at a selected bank with no further tendency to yaw since there is no longer deflection of the ailerons. As a result, pressure may also be relaxed on the rudder pedals, and the rudder allowed to streamline itself with the direction of the slipstream. Rudder pressure maintained after the turn is established will cause the plane to skid to the outside of the turn. If a definite effort is made to center the rudder rather than let it streamline itself to the turn, it is probable that some opposite rudder pressure will be exerted inadvertently. This will force the plane to yaw opposite its turning path, causing the plane to slip to the inside of the turn. The ball in the turn and slip indicator will be displaced off-center whenever the airplane is skidding or slipping sideways. See Figure 3-8. In proper coordinated flight, there is no skidding or slipping. An essential basic airmanship skill is the ability of the pilot to sense or feel any uncoordinated condition, slip or skid, without referring to instrument reference. During this stage of training, the flight instructor should stress the development of this ability and insist on its use to attain perfect coordination in all subsequent training. In all constant altitude, constant airspeed turns, it is necessary to increase the angle of attack of the wing when rolling into the turn by applying up elevator. This is required because part of the vertical lift has been diverted to horizontal lift. Thus, the total lift must be increased to compensate for this loss. To stop the turn, the wings are returned to level flight by the coordinated use of ailerons and rudder applied in the opposite direction. To understand the relationship between airspeed, bank, and radius of turn, it should be noted that the rate of turn at any given true airspeed depends on the horizontal lift component. The horizontal lift component varies in proportion to the amount of bank. Therefore, the rate of turn at a given true airspeed increases as the angle of bank is increased. On the other hand, when a turn is made at a higher true airspeed at a given bank angle, the inertia is greater, and the horizontal lift component required for the turn is greater, causing the turning rate to become slower. See Figure 3-9 on next page. Therefore, at a given angle of bank, a higher true airspeed will make the radius of the turn larger because the airplane will be turning at a slower rate. When changing from a shallow bank to a medium bank, the airspeed of the wing on the outside of the turn increases in relation to the inside wing as the radius of turn decreases. The additional lift developed because of this increase in speed of the wing balances the inherent lateral stability of the airplane. At any given airspeed, aileron pressure is not required to maintain the bank. If the bank is allowed to increase from a medium to a steep bank, the radius of turn decreases further. The lift on the outside wing causes the bank to steepen, and opposite aileron is necessary to keep the bank constant. As the radius of the turn becomes smaller, a significant difference develops between the speed of the inside wing and the speed of the outside wing. The wing on the outside of the turn travels a longer circuit than the inside wing, yet both complete their respective circuits in the same length of time. Therefore, the outside wing travels faster than the inside wing, and as a result, it develops more lift. This creates an overbanking tendency that must be controlled by the use of ailerons. See Figure 3-10. Because the outboard wing is developing more lift, it also has more induced drag. This causes a slight slip during steep turns that must be corrected by use of the rudder. Sometimes during early training in steep turns, the nose may be allowed to get excessively low, resulting in a significant loss of altitude. To recover, the pilot should first reduce the angle of bank with coordinated use of rudder and aileron, then raise the nose of the airplane to level flight with the elevator. If recovery from an excessively nose-low steep bank condition is attempted by use of the elevator only, it will cause a steepening of the bank and could result in overstressing the airplane. Normally, small corrections for pitch during steep turns are accomplished with the elevator and the bank is held constant with the ailerons. To establish desired angle of bank, the pilot should use outside visual reference points as well as the bank indicator on the attitude indicator. The best outside reference for establishing the degree of bank is the angle formed by the raised wing of low-wing airplanes, the lowered wing of high-wing airplanes, and the horizon, or the angle made by the top of the engine cowling and the horizon. See Figure 3-11 on page 3-11. Since on most light airplanes the engine cowling is fairly flat, its horizontal angle to the horizon will give some indication of the approximate degree of bank. Also, information obtained from the attitude indicator will show the angle of the wing in relation to the horizon. Information from the turn coordinator, however, will not. The pilot's posture while seated in the airplane is very important, particularly during turns. It will affect the interpretation of outside visual references. At the beginning, the student may lean away from the turn in an attempt to remain upright in relation to the ground rather than ride with the airplane. This should be corrected immediately if the student is to properly learn to use visual references. See Figure 3-12. Parallax error is common among students and experienced pilots. This error is a characteristic of airplanes that have side-by-side seats because the pilot is seated to one side of the longitudinal axis about which the airplane rolls. This makes the nose appear to rise when making a left turn and to descend when making right turns. See Figure 3-13. Beginning students should not use large aileron and rudder applications because this produces a rapid roll rate and allows little time for corrections before the desired bank is reached. Slower, small control displacement roll rates provide more time to make necessary pitch and bank corrections. As soon as the airplane rolls from the wings level attitude, the nose should also start to move along the horizon, increasing its rate of travel proportionately as the bank is increased. The following variations provide excellent guides. If the nose starts to move before the bank starts, rudder is being applied too soon. If the bank starts before the nose starts turning, or the nose moves in the opposite direction, the rudder is being applied too late. If the nose moves up or down when entering a bank, excessive or insufficient up elevator is being applied. As the desired angle of bank is established, aileron and rudder pressures should be relaxed. This will stop the bank from increasing because the aileron and rudder control surfaces will be neutral in their streamlined position. The up elevator pressure should not be relaxed, but should be held constant to maintain a constant altitude. Throughout the turn, the pilot should cross-check the airspeed indicator, and if the airspeed has decreased more than 5 knots, additional power should be used. The cross-check should also include outside references, altimeter and vertical speed indicator, VSI, which can help determine whether or not the pitch attitude is correct. If gaining or losing altitude, the pitch attitude should be adjusted in relation to the horizon, and then the altimeter and VSI rechecked to determine if altitude is being maintained. During all turns, the aileron, rudder, and elevator are used to correct minor variations in pitch and bank, just as they are in straight and level flight. The rollout from a turn is similar to the roll-in, except the flight controls are applied in the opposite direction. Aileron and rudder are applied in the direction of the rollout or toward the high wing. As the angle of bank decreases, the elevator pressure should be relaxed as necessary to maintain altitude. Since the airplane will continue turning as long as there is any bank, the rollout must be started before reaching the desired heading. The amount of lead required to roll out on the desired heading will depend on the degree of bank used in the turn. Normally, the lead is 1/2 the degrees of bank. For example, if the bank is 30 degrees, lead the rollout by 15 degrees. As the wings become level, the control pressure should be smoothly relaxed so that the controls are neutralized as the plane returns to straight and level flight. As the rollout is being completed, attention should be given to the outside visual references, as well as the attitude and heading indicators to determine that the wings are being leveled and the turn stopped. Instruction in level turns should begin with medium turns so that the student has an opportunity to grasp the fundamentals of turning flight without having to deal with overbanking tendency or the inherent stability of the airplane attempting to level the wings. The instructor should not ask the student to roll the plane from bank to bank, but to change its attitude from level to bank, bank to level, and so on with slight pause at the termination of each phase. This pause allows the airplane to free itself from the effects of any misuse of the controls and assures the correct start for the next turn. During those exercises, the idea of control forces rather than movement should be emphasized by pointing out the resistance of the controls to varying forces applied to them. The beginning student should be encouraged to use the rudder freely. Skidding in this phase indicates positive control use and may be easily corrected later. The use of too little rudder or rudder use in the wrong direction at this stage of training, on the other hand, indicates a lack of proper conception of coordination. In practicing turns, the action of the airplane's nose will show any error in coordination of the controls. Often during the entry or recovery from a bank, the nose will describe a vertical arc above or below the horizon and then remain in proper position after the bank is established. This is the result of the lack of timing and coordination of forces on the elevator and rudder controls during entry and recovery. It indicates that the student has knowledge of correct turns, but the entry and recovery techniques are in error. Because the elevator and ailerons are on one control and pressures on both are executed simultaneously, the beginning pilot is often apt to continue pressure on one of these unintentionally when force on the other only is intended. This is particularly true in left-hand turns because the position of the hands makes correct movement slightly awkward at first. This is sometimes responsible for the habit of climbing slightly in right-hand turns and diving slightly in left-hand turns. This results from many factors, including the unequal rudder pressures required to the right and to the left when turning, due to the torque effect. The tendency to climb in right-hand turns and descend in left-hand turns is also prevalent in airplanes using side-by-side cockpit steering. In this case, it is due to the pilots being seated to one side of the longitudinal axis about which the airplane rolls. This makes the nose appear to rise during a correctly executed left turn and to descend during a correctly executed right turn. An attempt to keep the nose on the same apparent level will cause climbing in right turns and diving in left turns. Excellent coordination and timing of all the controls in turning requires much practice. It is essential that this coordination be developed because it is the very basis of this fundamental flight maneuver. If the body is properly relaxed, it will act as a pendulum and may be swayed by any force acting on it. During a skid, it will be swayed away from the turn, and during a slip, toward the inside of the turn. The same effects will be noted in tendencies to slide on the seat. As the feel of the flying develops, the properly directed student will become highly sensitive to this last tendency and will be able to detect the presence of, or even the approach of, a slip or skid long before any other indication is present. Common errors in the performance of level turns are Failure to adequately clear the area before beginning the turn. Attempting to execute the turn solely by instrument reference. Attempting to sit up straight in relation to the ground during a turn rather than riding with the airplane. Insufficient feel for the airplane as evidenced by the inability to detect slips or skids without reference to flight instruments. Attempting to maintain a constant bank angle by referencing the cant of the airplane's nose. Fixating on the nose reference while excluding wingtip reference. Ground shyness, making flat turns, skidding, while operating at low altitudes in a conscious or subconscious effort to avoid banking close to the ground. Holding rudder in a turn. Gaining proficiency in turns in only one direction, usually the left. Failure to coordinate the use of throttle with other controls. Altitude gain lost during the turn. Climbs and climbing turns. When an airplane enters a climb, it changes its flight path from level flight to an inclined plane or climb attitude. In a climb, weight no longer acts in the direction perpendicular to the flight path. It acts in a rearward direction. This causes an increase in total drag requiring an increase in thrust, power, to balance the forces. An airplane can only sustain a climb angle when there is sufficient thrust to offset increased drag. Therefore, climb is limited by the thrust available. Like other maneuvers, climbs should be performed using outside visual references and flight instruments. It is important that the pilot know the engine power settings and pitch attitudes that will produce the following conditions of climb. Normal climb. Normal climb is performed at an airspeed recommended by the airplane manufacturer. Normal climb speed is generally somewhat higher than the airplane's best rate of climb. The additional airspeed provides better engine cooling, easier control, and better visibility over the nose. Normal climb is sometimes referred to as cruise climb. Complex or high-performance airplanes may have a specified cruise climb in addition to normal climb. Best rate of climb. Best rate of climb, VY, is performed at an airspeed where the most excess power is available over that required for level flight. This condition of climb will produce the most gain in altitude in the least amount of time. Maximum rate of climb in feet per minute. The best rate of climb made at full allowable power is a maximum climb. It must be fully understood that attempts to obtain more climb performance than the airplane is capable of by increasing pitch attitude will result in a decrease in the rate of altitude gained. Best angle of climb. The best angle of climb, Vx, is performed at an airspeed that will produce the most altitude gained in a given distance. Best angle of climb, airspeed, Vx, is considerably lower than the best rate of climb, Vy, and is the airspeed where most excess thrust is available over that required for level flight. The best angle of climb will result in a steeper climb path, although the airplane will take longer to reach the same altitude than it would at best rate of climb. The best angle of climb, therefore, is used in clearing obstacles after takeoff. See Figure 3-14. It should be noted that, as altitude increases, the speed for best angle of climb increases, and the speed for the best rate of climb decreases. The point at which these two speeds meet is the absolute ceiling of the airplane. See Figure 3-15 on next page. A straight climb is entered by greatly increasing pitch attitude to a predetermined level using back elevator pressure and simultaneously increasing engine power to the climb power setting. Due to an increase in the downwash over the horizontal stabilizer as power is applied, the airplane's nose will tend to immediately begin to rise of its own accord to an attitude higher than that at which it would stabilize. The pilot must be prepared for this. As a climb is started, the airspeed will gradually diminish. This reduction in airspeed is gradual because of the initial momentum of the airplane. The thrust required to maintain straight and level flight at a given airspeed is not sufficient to maintain the same airspeed in a climb. Climbing flight requires more power than flying level because of the increased drag caused by the gravity acting rearward. Therefore, power must be advanced to a higher power setting to offset the increased drag. The propeller effects at climb power are a primary factor. This is because airspeed is significantly lower than at cruising speed, and the airplane's angle of attack is significantly greater. Under these conditions, torque and asymmetrical loading of the propeller will cause the airplane to roll and yaw to the left. To counteract this, the right rudder must be used. During the early practice of climbs and climbing turns, this may make coordination of the controls seem awkward. Left climbing turn, holding right rudder. But after a little practice, this correction for propeller effects will become instinctive. Trim is also a very important consideration during a climb. After the climb has been established, the airplane should be trimmed to relieve all pressures from the flight controls. If changes are made in the pitch attitude, power, or airspeed, the airplane should be retrimmed in order to relieve control pressures. When performing a climb, the power should be advanced to the climb power recommended by the manufacturer. If the airplane is equipped with a controllable pitch propeller, it will have not only an engine tachometer, but also a manifold pressure gauge. Normally, the flaps and landing gear, if retractable, should be in retracted position to reduce drag. As the airplane gains altitude during the climb, the manifold pressure gauge, if equipped, will indicate a loss of manifold pressure, power. This is because the same volume of air going into the engine's induction system gradually decreases in density as altitude increases. When the volume of air in the manifold decreases, it causes a loss of power. This will occur at a rate of approximately 1 inch of manifold pressure for every 1,000 foot gain in altitude. During prolonged climbs, the throttle must be continually advanced if constant power is to be maintained. To enter the climb, simultaneously advance the throttle and apply back elevator pressure to raise the nose of the airplane to the proper position in relation to the horizon. As the powers increase, the airplane's nose will rise due to increased download on the stabilizer. This is caused by increased slipstream. As the pitch attitude increases and the airspeed decreases, progressively more right rudder must be applied to compensate for propeller effects and to hold a constant heading. After the climb is established, back elevator pressure must be maintained to keep the pitch attitude constant. As the airspeed decreases, the elevators will try to return to their neutral or streamline position, and the airplane's nose will tend to lower. Nose-up elevator trim should be used to compensate for this so that the pitch attitude can be maintained without holding back elevator pressure. Throughout the climb, since the power is fixed at the climb power setting, the airspeed is controlled by the use of elevator. A cross-check of airspeed indicator, attitude indicator, and the position of the airplane's nose in relation to the horizon will determine if the pitch attitude is correct. At the same time, a constant heading should be held with the wings level if a straight climb is being performed, or a constant angle of bank and rate of turn if the climbing turn is being performed. See Figure 3-16. To return to straight and level flight from a climb, it is necessary to initiate the level off at approximately 10% of the rate of climb. For example, if the airplane is climbing at 500 feet per minute, FPM, leveling off should start 50 feet below the desired altitude. The nose must be lowered gradually, because a loss of altitude will result if the pitch attitude is changed to a level flight position without allowing the airspeed to increase proportionately. After the airplane is established in level flight at constant altitude, climb power should be retained temporarily so that the airplane will accelerate to the cruise airspeed more rapidly. When the speed reaches the desired cruise speed, the throttle setting and the propeller control, if equipped, should be set to the cruise power setting and the airplane trimmed. After allowing time for engine temperatures to stabilize, adjust the mixture control as required. In the performance of climbing turns, the following factors should be considered. With a constant power setting, the same pitch attitude and airspeed cannot be maintained in a bank as in the straight climb due to the increase in the total lift required. The degree of bank should not be too steep. A steep bank significantly decreases the rate of climb. The bank should always remain constant. It is necessary to maintain a constant airspeed and constant rate of turn in both right and left turns. The coordination of all flight controls is a primary factor. At a constant power setting, the airplane will climb at a slightly shallower climb angle because some of the lift is being used to turn the plane. Attention should be diverted from fixation on the airplane's nose and divided equally among inside and outside references. There are two ways to establish a climbing turn. Either establish a straight climb and then turn, or enter the climb and turn simultaneously. Climbing turns should be used when climbing to a local practice area. Climbing turns allow better visual scanning, and it is easier for other pilots to see a turning aircraft. In any turn, the loss of vertical lift and increased induced drag due to the increased angle of attack becomes greater as the angle of bank is increased. So shallow turns should be used to maintain an efficient rate of climb. All factors that affect a plane during level flight, constant altitude, turns, will affect it during climbing turns or any other training maneuver. It will be noted that because of the low airspeed, aileron drag, adverse yaw, will have a more prominent effect than it did in straight and level flight, and more rudder pressure will have to be blended with aileron pressure to keep the airplane in coordinated flight during changes in bank angle. Additional elevator back pressure and trim will also have to be used to compensate for centrifugal force, for the loss of vertical lift, and to keep pitch attitude constant. During climbing turns, as in any turn, the loss of vertical lift and induced drag due to the increased angle of attack becomes greater as the angle of bank is increased, so shallow turns should be used to maintain an efficient rate of climb. If a medium or steep bank turn is used, climb performance will be degraded. Common errors in performance of climbs and climbing turns are attempting to establish climb pitch attitude by referencing the airspeed indicator, resulting in chasing the airspeed. Applying elevator pressure too aggressively, resulting in excessive climb angle. Applying elevator pressure too aggressively during level off, resulting in negative G forces. Inadequate or inappropriate rudder pressure during climbing turns. Allowing the plane to yaw in straight climbs, usually due to an inadequate right rudder pressure. Fixation on the nose during straight climbs, resulting in climbing with one wing low. Failure to initiate climbing turn properly with the use of rudder and elevators, resulting in little turn, but rather a climb with one wing low. Improper coordination, resulting in a slip, which counteracts the effects of a climb, resulting in little or no altitude gain. Inability to keep pitch and bank attitude constant during climbing turns. Attempting to exceed the airplane's climb capability. End Chapter 3, Part 2. Recording by Dale Latham. Chapter 3, Part 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 3, Part 3. Descents and Descending Turns. When an airplane enters a descent, it changes its flight path from level to an inclined plane. It is important that the pilot know the power settings and pitch attitudes that will produce the following conditions of descent. Partial power descent. The normal method for losing altitude is to descend with partial power. This is often termed cruise or en route descent. The airspeed and power setting recommended by the airplane manufacturer for prolonged descent should be used. The target descent rate should be 400 to 500 fpm. The airspeed may vary from cruise airspeed to that used on the downwind leg of the landing pattern. But the wide range of possible airspeeds should not be interpreted to permit erratic pitch changes. The desired airspeed, pitch attitude, and power combination should be pre-selected and kept constant. Descent at minimum safe airspeed. A minimum safe airspeed descent is a nose-high, power-assisted descent condition principally used for clearing obstacles during a landing approach to a short runway. The airspeed used for this descent is recommended by the airplane manufacturer and normally is no greater than 1.3 VSO. Some characteristics of the minimum safe airspeed descent are a steeper than normal descent angle and the excessive power that may be required to produce acceleration at low airspeed. Should mushing and or an excessive rate of descent be allowed to develop. Glides. A glide is a basic maneuver in which the airplane loses altitude in a controlled descent with little or no engine power. Forward motion is maintained by gravity pulling the airplane along an inclined path, and the descent rate is controlled by the pilot balancing forces of gravity and lift. Although glides are directly related to the practice of power-off accuracy landings, they have a specific operational purpose in normal landing approaches and forced landings after engine failure. Therefore, it is necessary that they be performed more subconsciously than other maneuvers because most of the time during their execution, the pilot will be giving full attention to details other than the mechanics of performing the maneuver. Since glides are usually performed relatively close to the ground, accuracy of their execution and the formation of proper techniques and habits are of special importance. Because the application of controls is somewhat different in glides than in power-on descents, gliding maneuvers require the perfection of a technique somewhat different from that required of ordinary power-on maneuvers. This control difference is caused primarily by two factors: the absence of the usual propeller slipstream and the difference in the relative effectiveness of the various control surfaces at slow speeds. The glide ratio of an airplane is the distance the airplane will, with power off, travel forward in relation to the altitude it loses. For instance, if an airplane travels 10,000 feet forward while descending 1,000 feet, its glide ratio is said to be 10:1. The glide ratio is affected by all four fundamental forces that act on an airplane: weight, lift, drag, and thrust. If all factors affecting the airplane are constant, the glide ratio will be constant. Although the effect of the wind will not be covered in this section, it is a very prominent force acting on the gliding distance of the airplane in relationship to its movement over the ground. With a tailwind, the airplane will glide farther because of the higher ground speed. Conversely, with a headwind, the airplane will not glide as far because of the slower ground speed. Variations in weight do not affect the glide angle provided the pilot uses the correct airspeed. Since it is the lift over drag, L/D, ratio that determines the distance the airplane can glide, weight will not affect the distance. The glide ratio is based only on the relationship of the aerodynamic forces acting on the airplane. The only effect weight has is to vary the time the airplane will glide. The heavier the airplane, the higher the airspeed must be to obtain the same glide ratio. For example, if two airplanes have the same L/D ratio, but different weights, start a glide from the same altitude, the heavier airplane gliding at the higher airspeed will arrive at the same touchdown point in a shorter time. Both airplanes will cover the same distance, only the lighter airplane will take a longer time. Under various flight conditions, the drag factor may change through the operation of the landing gear and/or flaps. When the landing gear or the flaps are extended, drag increases and the airspeed will decrease unless the pitch attitude is lowered. As the pitch is lowered, the glide path steepens and reduces the distance traveled. With the power off, a windmilling propeller also creates considerable drag, thereby retarding the airplane's forward movement. Although the propeller thrust of the airplane is normally dependent on the power output of the engine, the throttle is in the closed position during a glide, so the thrust is constant. Since power is not used during the glide or power off approach, the pitch attitude must be adjusted as necessary to maintain a constant airspeed. The best speed for the glide is the one at which the airplane will travel the greatest forward distance for a given loss of altitude in still air. This best glide speed corresponds to the angle of attack resulting in the least drag on the airplane and giving the best lift-to-drag ratio, L/D max. See Figure 3-17. Any change in the gliding airspeed will result in a proportionate change in the glide ratio. Any speed other than the best glide speed results in more drag. Therefore, as the glide airspeed is reduced or increased from the optimum or best glide speed, the glide ratio is also changed. When descending at a speed below the best glide speed, induced drag increases. When descending at a speed above best glide speed, parasite drag increases. In either case, the rate of descent will increase. See Figure 3-18. This leads to a cardinal rule of airplane flying that a student pilot must understand and appreciate. The pilot must never attempt to stretch a glide by applying back elevator pressure and reducing the airspeed below the airplane's recommended best glide speed. Attempts to stretch a glide will invariably result in an increase in the rate and angle of descent and may precipitate an inadvertent stall. To enter a glide, the pilot should close the throttle and advance the propeller, if so equipped, to a low pitch, high RPM. A constant altitude should be held with back pressure on the elevator control until the airspeed decreases to the recommended glide speed. Due to the decrease in downwash over the horizontal stabilizer as power is reduced, the airplane's nose will tend to immediately begin to lower of its own accord to an attitude lower than that at which it would stabilize. The pilot must be prepared for this. To keep pitch attitude constant over the power change, the pilot must counteract the immediate trim change. If the pitch attitude is allowed to decrease during glide entry, excess speed will be carried into the glide and retard the attainment of the correct glide angle and airspeed. Speed should be allowed to dissipate before the pitch attitude is decreased. This point is particularly important in so-called clean airplanes, as they are very slow to lose their speed, and any slight deviation of the nose downward results in an immediate increase in airspeed. Once the airspeed has dissipated to normal or best glide speed, the pitch attitude should be allowed to decrease to maintain that speed. This should be done with reference to the horizon. When the speed has stabilized, the airplane should be retrimmed for hands-off flight. When the approximate gliding pitch attitude is established, the airspeed indicator should be checked. If the airspeed is higher than recommended speed, the pitch attitude is too low, and if the airspeed is less than recommended, the pitch attitude is too high. Therefore, the pitch attitude should be readjusted accordingly, referencing the horizon. After the adjustment has been made, the airplane should be retrimmed so that it will maintain the attitude without the need of hold pressure on the elevator control. The principles of attitude flying require that the proper flight attitude be established using outside visual references first, then using flight instruments as a secondary check. It is a good practice to always retrim the plane after each pitch adjustment. A stabilized, power-off descent at the best glide speed is often referred to as a normal glide. The flight instructor should demonstrate a normal glide and direct the student pilot to memorize the airplane's angle and speed by visually checking the airplane's attitude with reference to the horizon, and noting the pitch of the sound made by the air passing over the structure, the pressure on the controls, and the feel of the airplane. Due to lack of experience, the beginning students may be unable to recognize slight variations of speed and angle of bank immediately by vision or by the pressure required on the controls. Hearing will probably be the indicator that will be the most easily used at first. The instructor should, therefore, be certain that the student understands that an increase in the pitch of sound denotes increasing speed, while a decrease in pitch denotes less speed. When such an indication is received, the student should consciously apply the other two means of perception as to establish the proper relationship. The student pilot must use all three elements consciously until they become habits, and must be alert when attention is diverted from the attitude of the plane and be responsive to any warning given by a variation in the feel of the airplane or controls, or by the change in the pitch of the sound. After a good comprehension of normal glide is attained, the student pilot should be instructed in the differences in the results of normal and abnormal glides. Abnormal glides being those conducted at speeds other than normal best glide speed. Pilots who do not acquire an understanding and appreciation of these differences will experience difficulties with accuracy landings, which are comparatively simple if the fundamentals of the glide are thoroughly understood. Too fast a glide during the approach for landings invariably results in floating over the ground for varying distance or even overshooting, while too slow a glide causes undershooting, flat approaches, or hard touchdowns. A pilot without the ability to recognize a normal glide will not be able to judge where the plane will go, or can be made to go in an emergency. Whereas, in a normal glide, the flight path may be sighted to a spot on the ground on which the airplane will land. This cannot be done in any abnormal glide. Gliding turns. The action of a control system is somewhat different in a glide than with power. Making gliding maneuvers stand in a class by themselves and require the perfection of a technique different from that required for ordinary power maneuvers. The control difference is caused mainly by two factors: the absence of the usual slipstream and the difference or relative effectiveness of the various control surfaces at various speeds, and particularly at reduced speed. The latter factor has its effect exaggerated by the first, and makes the task of coordination even more difficult for the inexperienced pilot. These principles should be thoroughly explained in order that the student may be alert to any necessary differences in coordination. After a feel for the airplane and a control touch have been developed, the necessary compensation will be automatic. But while any mechanical tendency exists, the students will have difficulty executing gliding turns, particularly when making a practical application of them in attempting accuracy landings. Three elements in gliding turns which tend to force the nose down and increase glide speed are: decrease in effective lift due to the direction of the lifting force being at an angle to the pull of gravity, the use of the rudder acting as it does in the entry to a power turn, normal stability, and inherent characteristics of the airplane to nose down with power off. These three factors make it necessary to use more back pressure on the elevator than is required for straight glide or a power turn and, therefore, have a greater effect on the relationship of control coordination. When recovery is being made from a gliding turn, the force on the elevator control, which was applied during the turn, must be decreased or the nose will come up too high and considerable speed will be lost. This error will require considerable attention and conscious control adjustment before the normal glide can again be resumed. In order to maintain the most efficient or normal glide in a turn, more altitude must be sacrificed than in straight glide, since this is the only way speed can be maintained without power. Turning in a glide decreases the performance of the airplane to an even greater extent than a normal turn with power. Still, another factor is the difference in rudder action in turns with and without power. In power turns, it is required that the desired recovery point be anticipated and the use of controls and that considerably more pressure than usual be exerted on the rudder. In the recovery from a gliding turn, the same rudder action takes place, but without as much pressure being necessary. The actual displacement of the rudder is approximately the same, but it seems to be less in a glide because the resistance to the pressure is so much less due to the absence of the propeller slipstream. This often results in a much greater application of rudder through a greater range than is realized, resulting in an abrupt stoppage of the turn when the rudder is applied for recovery. This factor is particularly important during landing practice since the student almost invariably recovers from the last turn too soon and may enter a cross-control condition trying to correct the landing with the rudder alone. This results in landing from a skid that is too easily mistaken for a drift. There is another danger in excessive rudder use during gliding turns. As the airplane skids, the bank will increase. This often alarms the beginning pilot when it occurs close to the ground, and the pilot may respond by applying aileron pressure toward the outside to stop the bank. At the same time, the rudder forces the nose down, and the pilot may apply back elevator pressure to hold it up. If allowed to progress, this situation may result in a fully developed cross-control condition. A stall in this situation will almost certainly result in a spin. The level off from a glide must be started before reaching the desired altitude because of the airplane's downward inertia. The amount of lead depends on the rate of descent and the pilot's control technique. With too little lead, there will be a tendency to descend below the selected altitude. For example, assuming a 500 foot per minute rate of descent, the altitude must be led by 100 to 150 feet to level off at the airspeed higher than the glide speed. At the lead point, power should be increased to the appropriate level flight cruise setting so the desired airspeed will be attained at the desired altitude. The nose tends to rise as both airspeed and downwash on the tail section increase. The pilot must be prepared for this and smoothly control the pitch attitude to attain level flight attitude so that the level off is completed at the desired altitude. Particular attention should be paid to the action of the airplane's nose when recovering and entering gliding turns. The nose must not be allowed to describe an arc with relation to the horizon, and particularly it must not be allowed to come up during recovery from turns, which require a constant variation of relative pressures on the different controls. Common errors in performance of descents and descending turns are failure to adequately clear the area, inadequate back elevator control during a glide entry resulting in too steep a glide, failure to slow the airplane to approximate glide speed prior to lowering pitch attitude, attempting to maintain a normal glide solely by reference to flight instruments, inability to sense changes in airspeed through sound and feel, inability to stabilize the glide, chasing the airspeed indicator. Attempting to stretch the glide by applying back elevator pressure. Skidding or slipping during gliding turns due to inadequate appreciation of the difference in rudder action as opposed to turns with power. Failure to lower pitch attitude during gliding turn entry, resulting in a decrease in airspeed. Excessive rudder pressure during recovery from gliding turns. Inadequate pitch control during recovery from straight glides. Ground shyness, resulting in cross-controlling during gliding turns near the ground. Failure to maintain constant bank angle during gliding turns. Pitch and power. No discussion of climbs and descents would be complete without touching on the question of what controls altitude and what controls airspeed. The pilot must understand the effects of both power and elevator control, working together during different conditions of flight. The closest one can come to a formula for determining airspeed altitude control that is valid under all circumstances is a basic principle of attitude flying, which states, at any pitch attitude, the amount of power used will determine whether the airplane will climb, descend, or remain level at that attitude. Through a wide range of nose-low attitudes, a descent is the only possible condition of flight. The addition of power to any of these attitudes will only result in a greater rate of descent at a faster airspeed. Through a range of attitudes from very slightly nose-low to about 30-degree nose-up, a typical light airplane can be made to climb, descend, or maintain altitude depending on the power used. In about the lower third of this range, the airplane will descend at idle power without stalling. As pitch attitude is increased, however, engine power will be required to prevent a stall. Even more power will be required to maintain altitude, and even more for a climb. At a pitch attitude approaching 30 degrees nose up, all available power will provide only enough thrust to maintain altitude. A slight increase in the steepness of climb or a slight decrease in the power will reduce a descent. From that point, the least inducement will result in a stall. End Chapter 3, Part 3. Recording by Dale Latham.
Chapter 4, Part 1 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 4. Slow Flight, Stalls, and Spins. Introduction. The maintenance of lift and control of an airplane in flight requires a certain minimum airspeed. This critical airspeed depends on certain factors, such as gross weight, load factors, and existing density altitude. The minimum speed below which further controlled flight is impossible is called the stalling speed. An important feature of pilot training is the development of the ability to estimate the margin of safety above the stalling speed. Also, the ability to determine the characteristic responses of any airplane at different airspeeds is of great importance to the pilot. The student pilot, therefore, must develop this awareness in order to safely avoid stalls and to operate an airplane correctly and safely at slow airspeeds. Slow flight. Slow flight can be thought of by some as a speed that is less than cruise. In pilot training and testing, however, slow flight is broken down into two distinct elements. 1. The establishment, maintenance of, and maneuvering of the airplane at airspeeds and in configurations appropriate to takeoffs, climbs, descents, landing approaches, and go-rounds, and 2. Maneuvering at the slowest airspeed at which the airplane is capable of maintaining controlled flight without indications of a stall, usually 3 to 5 knots above stalling speed. Flight at less than cruise airspeeds. Maneuvering during slow flight demonstrates the flight characteristics and degree of controllability of an airplane at less than cruise speeds. The ability to determine the characteristic control responses at the lower airspeeds appropriate to takeoffs, departures, and landing approaches is a critical factor in stall awareness. As airspeed decreases, control effectiveness decreases disproportionately. For instance, there may be a certain loss of effectiveness when the airspeed is reduced from 30 to 20 miles per hour above the stalling speed, but there will normally be a much greater loss as the airspeed is further reduced to 10 miles per hour above stalling. The objective of maneuvering during slow flight is to develop the pilot's sense of feel and ability to use the controls effectively, and to improve proficiency in performing maneuvers that require slow airspeeds. Maneuvering during slow flight should be performed using both instrument indications and outside visual reference. Slow flight should be practiced from straight glides, straight and level flight, and from medium banked gliding and level flight turns. Slow flight at approach speeds should include slowing the airplane smoothly and promptly from cruising to approach speeds without changes in altitude or heading, and determining and using appropriate power and trim settings. Slow flight at approach speed should also include configuration changes, such as landing gear and flaps, while maintaining heading and altitude. Flight at minimum controllable airspeed. This maneuver demonstrates the flight characteristics and degree of controllability of the airplane at its minimum flying speed. By definition, the term flight at minimum controllable airspeed means a speed at which any further increase in angle of attack or local load factor or reduction in power will result in an immediate stall. Instruction in flight at minimum controllable airspeed should be introduced at reduced power settings, with the airspeed sufficiently above stall to permit maneuvering, but close enough to stall to sense the characteristics of flight at very low airspeed, which are sloppy controls, ragged response to control inputs, and difficulty maintaining altitude. Maneuvering at minimum controllable airspeed should be performed using both instrument indications and outside visual reference. It is important that pilots form the habit of frequent reference to the flight instruments, especially the airspeed indicator, while flying at very low airspeeds. However, a feel for the airplane at very low airspeeds must be developed to avoid inadvertent stalls and to operate the airplane with precision. To begin the maneuver, the throttle is gradually reduced from cruising position. While the airspeed is decreasing, the position of the nose in relation to the horizon should be noted and should be raised as necessary to maintain altitude. When the airspeed reaches the maximum allowable for landing gear operation, the landing gear, if equipped with retractable gear, should be extended and all gear down checks performed. As the airspeed reaches the maximum allowable for flap operation, full flaps should be lowered and the pitch attitude adjusted to maintain altitude. Figure 4-1. Additional power will be required as the speed further decreases to maintain the airspeed just above a stall. As the speed decreases further, the pilot should note the feel of the flight controls, especially the elevator. The pilot should also note the sound of the airflow as it falls off in tone level. As airspeed is reduced, the flight controls become less effective and the normal nose-down tendency is reduced. The elevators become less responsive and course control movements become necessary to retain control of the airplane. The slipstream effect produces a strong yaw, so the application of rudder is required to maintain coordinated flight. The secondary effect of applied rudder is to induce a roll, so aileron is required to keep the wings level. This can result in flying with crossed controls. During these changing flight conditions, it is important to retrim the airplane as often as necessary to compensate for changes in control pressures. If the airplane had been trimmed for cruising speed, heavy aft control pressure will be needed on the elevators, making precise control impossible. If too much speed is lost or too little power is used, further back pressure on the elevator control may result in a loss of altitude or a stall. When the desired pitch attitude and minimum control airspeed have been established, it is important to continually cross-check the attitude indicator, altimeter, and airspeed indicator, as well as outside references to ensure that accurate control is being maintained. The pilot should understand that when flying more slowly than the minimum drag speed, LD max, the airplane will exhibit a characteristic known as speed instability. If the airplane is disturbed by even the slightest turbulence, the airspeed will decrease. As airspeed decreases, the total drag also increases, resulting in a further loss in airspeed. The total drag continues to rise and the speed continues to fall. Unless more power is applied and or the nose is lowered, the speed will continue to decay right down to the stall. This is an extremely important factor in the performance of slow flight. The pilot must understand that, at speed less than minimum drag speed, the airspeed is unstable and will continue to decay if allowed to do so. When the attitude, airspeed, and power have been stabilized in straight flight, turns should be practiced to determine the airplane's controllability characteristics at this minimum speed. During the turns, power and pitch attitude may need to be increased to maintain the airspeed and altitude. The objective is to acquaint the pilot with the lack of maneuverability at minimum speeds, the danger of incipient stalls, and the tendency of the airplane to stall as the bank is increased. A stall may occur as a result of abrupt or rough control movements when flying at this critical airspeed. Abruptly raising the flaps while at minimum controllable airspeed will result in lift suddenly being lost, causing the airplane to lose altitude or perhaps stall. Once flight at minimum controllable airspeed is set up properly for level flight, a descent or climb at minimum controllable airspeed can be established by adjusting the power as necessary to establish the desired rate of descent or climb. The beginning pilot should note that increased yawing tendency at minimum control airspeed at high power settings with the flaps fully extended. In some airplanes, an attempt to climb at such low airspeed may result in a loss of altitude even with the maximum power applied. Common errors in the performance of slow flight are failure to adequately clear the area, inadequate back pressure as power is reduced, resulting in altitude loss, excessive back elevator pressure as power is reduced, resulting in a climb, followed by a rapid reduction in airspeed and mushing, inadequate compensation for adverse yaw during turns, fixation on the airspeed indicator, failure to anticipate changes in lift as flaps are extended or retracted, inadequate power management, inability to adequately divide attention between airplane control and orientation. Stalls. A stall occurs when the smooth airflow over the airplane's wing is disrupted, and the lift degenerates rapidly. This is caused when the wing exceeds its critical angle of attack. This can occur at any airspeed, in any attitude, with any power setting. Figure 4-2. The practice of stall recovery and the development of awareness of stalls are of primary importance in pilot training. The objectives in performing intentional stalls are to familiarize the pilot with the conditions that produce stalls, to assist in recognizing an approaching stall, and to develop the habit of taking prompt preventative or corrective action. Intentional stalls should be performed at an altitude that will provide adequate height above the ground for recovery and return to normal flight level. Though it depends on the degree to which a stall has progressed, most stalls require some loss of altitude during recovery. The longer it takes to recognize the approaching stall, the more complete the stall is likely to become, and the greater the loss of altitude to be expected. Recognition of stalls. Pilots must recognize the flight conditions that are conducive to stalls and know how to apply the necessary corrective action. They should learn to recognize an approaching stall by sight, sound, and feel. The following cues may be useful in recognizing the approaching stall. Vision is useful in detecting a stall condition by noting the attitude of the airplane. This sense can only be relied on when the stall is a result of an unusual attitude of the airplane. Since the airplane can be stalled from a normal attitude, vision in this instance would be of little help in detecting the approaching stall. Hearing is also helpful in sensing a stall condition. In the case of fixed-pitch propeller airplanes in a power-on condition, a change in sound due to loss of revolutions per minute, RPM, is particularly noticeable. The lessening of the noise made by the air flowing along the airplane's structure as airspeed decreases is also quite noticeable, and when the stall is almost complete, vibration and incident noises often increase greatly. Kinesthesia, or the sensing of changes in direction or speed of motion, is probably the most important and best indicator to the trained and experienced pilot. If this sensitivity is properly developed, it will warn of a decrease in speed or the beginning of a settling or mushing of the airplane. Feel is an important sense in recognizing the onset of a stall. The feeling of control pressures is very important. As speed is reduced, the resistance to pressures on the controls becomes progressively less. Pressures exerted on the controls tend to become movements of the control surfaces. The lag between these movements and the response of the airplane becomes greater until, in a complete stall, all controls can be moved with almost no resistance and with little immediate effect on the airplane. Just before the stall occurs, buffeting, uncontrollable pitching, or vibrations may begin. Several types of stall warning indicators have been developed to warn pilots of an approaching stall. The use of such indicators is valuable and desirable, but the reason for practicing stalls is to learn to recognize stalls without the benefit of warning devices. Fundamentals of stall recovery. During the practice of intentional stalls, the real objective is not to learn how to stall an airplane, but to learn how to recognize an approaching stall and take prompt corrective action. Figure 4-3. Though the recovery actions must be taken in a coordinated manner, they are broken down into 3 actions here for explanation purposes. First, at the indication of a stall, the pitch, attitude, and angle of attack must be decreased positively and immediately. Since the basic cause of a stall is always an excessive angle of attack, the cause must first be eliminated by releasing the back elevator pressure that was necessary to attain that angle of attack, or by moving the elevator control forward. This lowers the nose and returns the wing to an effective angle of attack. The amount of elevator control pressure, or movement, depends on the design of the airplane, the severity of the stall, and the proximity of the ground. In some airplanes, a moderate movement of the elevator control, perhaps slightly forward of neutral, is enough, while in others a forcible push to the full forward position may be required. An excessive negative load on the wings caused by excessive forward movement of the elevator may impede rather than hasten the stall recovery. The object is to reduce the angle of attack, but only enough to allow the wing to regain lift. Second, the maximum allowable power should be applied to increase the airplane's airspeed and to assist in reducing the wing's angle of attack. The throttle should be promptly but smoothly advanced to the maximum allowable power. The flight instructor should emphasize, however, that power is not essential for a safe stall recovery if sufficient altitude is available. Reducing the angle of attack is the only way of recovering from a stall, regardless of the amount of power used. Although stall recoveries should be practiced without, as well as with, the use of power, in most actual stalls, the application of more power, if available, is an integral part of the stall recovery. Usually, the greater the power applied, the less the loss of altitude. Maximum allowable power applied at the instant of a stall will usually not cause overspeeding of an engine equipped with a fixed-pitch propeller due to the heavy air load imposed on the propeller at slow airspeeds. However, it will be necessary to reduce the power as airspeed is gained after the stall recovery, so the airspeed will not become excessive. When performing intentional stalls, the tachometer indication should never be allowed to exceed the red line. maximum allowable RPM, marked on the instrument. Third, straight and level flight should be regained with coordinated use of all controls. Practice in both power on and power off stalls is important because it simulates stall conditions that could occur during normal flight maneuvers. For example, the power on stalls are practiced to show what could happen if the airplane were climbing at an excessively nose-high attitude immediately after takeoff or during a climbing turn. The power-off turning stalls are practiced to show what could happen if the controls are improperly used during a turn from a base leg to the final approach. The power-off straight-ahead stall simulates the attitude and flight characteristics of a particular airplane during the final approach and landing. Usually, the first few practices should include only approaches to stalls, with the recovery initiated as soon as the first buffeting or partial loss of control is noted. In this way, the pilot can become familiar with the indications of an approaching stall without actually stalling the airplane. Once the pilot becomes comfortable with this procedure, the airplane should be slowed in such a manner that it stalls in as near a level pitch attitude as possible. The student pilot must not be allowed to form the impression that in all circumstances a high pitch attitude is necessary to exceed the critical angle of attack, or that in all circumstances a level or near level pitch attitude is indicative of a low angle of attack. Recovery should be practiced without the addition of power by merely relieving enough back elevator pressure that the stall is broken and the airplane assumes a normal glide attitude. The instructor should also introduce the student to a secondary stall at this point. Stall recoveries should then be practiced with the addition of power to determine how effective power will be in executing a safe recovery and minimizing altitude loss. Stall accidents usually result from an inadvertent stall at a low altitude in which recovery was not accomplished prior to contact with the surface. As a preventative measure, stalls should be practiced at an altitude which will allow recovery no lower than 1,500 feet above ground level, AGL. To recover with a minimum loss of altitude requires a reduction of the angle of attack, lowering of the airplane's pitch attitude, application of power, and termination of the descent without entering another secondary stall. Use of ailerons/rudder in stall recovery. Different types of airplanes have different stall characteristics. Most airplanes are designed so that the wing will stall progressively outward from the wing roots, where the wings attach to the fuselage, to the wing tips. This is the result of designing the wings in a manner that the wing tips have less angle of incidence than the wing roots. See Figure 4-4. Such a design feature causes the wing tips to have a smaller angle of attack than the wing roots during flight. Exceeding the critical angle of attack causes a stall. The wing roots of an airplane will exceed the critical angle before the wing tips, and the wing roots will stall first. The wings are designed in this manner so that aileron control will be available at high angles of attack, slow airspeed, and give the airplane more stable stalling characteristics. When the airplane is in a stalled condition, the wing tips continue to provide some degree of lift, and the ailerons still have some control effect. During recovery from a stall, the return of lift begins at the tips and progresses towards the roots. Thus, the ailerons can be used to level the wings. Using the ailerons requires finesse to avoid an aggravated stall condition. For example, if the right wing dropped during the stall and excessive aileron control were applied to the left to raise the wing, the aileron deflected downward, right wing, would produce a greater angle of attack and drag, and possibly a more complete stall at the tip as the critical angle of attack is exceeded. The increase in drag created by the high angle of attack on that wing might cause the airplane to yaw in that direction. This adverse yaw could result in a spin unless directional control was maintained by rudder and/or the aileron control sufficiently reduced. Even though excessive aileron pressure may have been applied, a spin will not occur if directional yaw control is maintained by timely application of coordinated rudder pressure. Therefore, it is important that the rudder be used properly during both the entry and the recovery from a stall. The The primary use of the rudder in stall recoveries is to counteract any tendency of the airplane to yaw or slip. The correct recovery technique would be to decrease the pitch attitude by applying forward elevator pressure to break the stall, advancing the throttle to increase airspeed, and simultaneously maintaining directional control with coordinated use of the aileron and rudder. Stall characteristics. Because of engineering design variations, the stall characteristics for all airplanes cannot be specifically described. However, the similarities found in small general aviation training type airplanes are noteworthy enough to be considered. It will be noted that the power on and power off stall warning indications will be different. The power off stall will have less noticeable clues, buffeting, shaking, than the power on stall. In the power off stall, the predominant clue can be the elevator control position, full up elevator against the stops, and a high descent rate. When performing the power on stall, the buffeting will likely be the predominant clue that provides a positive indication of the stall. For the purpose of airplane certification, the stall warning may be furnished either through the intermittent aerodynamic qualities of the airplane or by a stall warning device that will give a clear, distinguishable indication of the stall. Most airplanes are equipped with a stall warning device. The factors that affect the stalling characteristics of the airplane are balance, bank, pitch attitude, coordination, drag, and power. The pilot should learn the effect of the stall characteristics of the airplane being flown and the proper correction. It should be re-emphasized that a stall can occur at any airspeed, in any attitude, or at any power setting, depending on the total number of factors affecting the particular airplane. A number of factors may be induced as a result of other factors. For example, when the airplane is in a nose-high turning attitude, the angle of bank has a tendency to increase. This occurs because with the airspeed decreasing, the airplane begins flying in a smaller and smaller arc. Since the outer wing is moving in a larger radius and traveling faster than the inner wing, it has more lift and causes an overbanking tendency. At the same time, because the decreasing airspeed and lift on both wings, the pitch attitude tends to lower. In addition, since the airspeed is decreasing while the power setting remains constant, the effect of torque becomes more prominent, causing the airplane to yaw. During the practice of power-on turning stalls to compensate for these factors and to maintain a constant flight attitude until a stall occurs, aileron pressure must be continually adjusted to keep the bank attitude constant. At the same time, back elevator pressure must be continually increased to maintain the pitch attitude, as well as right rudder pressure increased to keep the ball centered and to prevent adverse yaw from changing the turn rate. If the bank is allowed to become too steep, the vertical component of lift decreases and makes it even more difficult to maintain a constant pitch attitude. Whenever practicing turning stalls, a constant pitch and bank attitude should be maintained until the stall occurs. Whatever control pressures are necessary should be applied even though the controls appear to be crossed. Aileron pressure in one direction, rudder pressure in the opposite direction. During the entry to a power-on turning stall to the right, in particular, the controls will be crossed to some extent. This is due to the right rudder pressure being used to overcome torque and left aileron pressure being used to prevent the bank from increasing. End of Chapter 4, Part 1. Chapter 4, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 4, Part 2. Approaches to stalls. Imminent stalls. Power on or power off. An imminent stall is one in which an airplane is approaching a stall but is not allowed to completely stall. This stall maneuver is primarily for practice in retaining or regaining full control of the airplane immediately upon recognizing that it is almost in a stall, or that a stall is likely to occur if timely preventative action is not taken. The practice of stalls is of particular value in developing a pilot's sense of feel for executing maneuvers in which maximum airplane performance is required. These maneuvers require flight with the airplane approaching a stall and recovery initiated before a stall occurs. As in all maneuvers that involve significant changes in altitude or direction, the pilot must ensure that the area is clear of other air traffic before executing the maneuver. These stalls may be entered and performed in attitudes and with the same configuration of the basic full stalls or other maneuvers described in this chapter. However, instead of allowing a complete stall when first buffeting or decay of control effectiveness is noted, the angle of attack must be reduced immediately by releasing the back elevator pressure and applying whatever additional power is necessary. Since the airplane will not be completely stalled, the pitch attitude needs to be decreased only to a point where minimum controllable airspeed is attained, or until adequate control effectiveness is regained. The pilot must promptly recognize the indication of a stall and take timely, positive control action to prevent a full stall. Performance is unsatisfactory if a full stall occurs, if an excessively low pitch attitude is attained, or if the pilot fails to take timely action to avoid excessive airspeed, excessive loss of altitude, or a spin. Full stalls power off. The practice of power-off stalls is usually performed with normal landing approach conditions, in simulation of an accidental stall occurring during landing approaches. Airplanes equipped with flaps and/or retractable landing gear should be in the landing configuration. Airspeed in excess of the normal approach speed should not be carried into a stall entry, since it could result in an abnormally nose-high attitude. Before executing these practice stalls, the pilot must be sure the area is clear of other air traffic. After extending the landing gear, applying carburetor heat if applicable, and retarding the throttle to idle or normal approach power, the airplane should be held at constant altitude in level flight until the airspeed decelerates to that of a normal approach. The airplane should then be smoothly nosed down into normal approach attitude to maintain that airspeed. Wing flaps should be extended and pitch attitude adjusted to maintain the airspeed. When the approach attitude and airspeed have stabilized, the airplane's nose should be smoothly raised to an attitude that will induce a stall. Directional control should be maintained with the rudder, the wings held level by the use of the ailerons, and a constant pitch attitude maintained with the elevator until the stall occurs. The stall will be recognized by clues, such as full-up elevator, high descent rate, uncontrollable nose-down pitching, and possible buffeting. Recovering from the stall should be accomplished by reducing the angle of attack, releasing back elevator pressure, and advancing the throttle to maximum allowable power. Right rudder pressure is necessary to overcome the engine torque effects as power is advanced and the nose is being lowered. Figure 4-5. The nose should be lowered as necessary to regain flying speed and returned to straight and level flight attitude. After establishing a positive rate of climb, the flaps and landing gear are retracted as necessary, and when in level flight, the throttle should be returned to cruise power setting. After recovery is complete, a climb or go-around procedure should be initiated, as the situation dictates, to assure a minimum loss of altitude. Recovery from power-off stalls should also be practiced from shallow banked turns to simulate an inadvertent stall during a turn from base leg to final approach. During the practice of these stalls, care should be taken that the turn continues at a uniform rate until the complete stall occurs. If the power-off turn is not properly coordinated while approaching the stall, wallowing may result when the stall occurs. If the airplane is in a slip, the outer wing may stall first and whip downward abruptly. This does not affect the recovery procedure in any way. The angle of attack must be reduced, the heading maintained, and the wings leveled by coordinated use of the controls. In the practice of turning stalls, no attempt should be made to stall the airplane on a predetermined heading. However, to simulate a turn from base to final approach, the stall normally should be made to occur within a heading change of approximately 90 degrees. After the stall occurs, the recovery should be made straight ahead with minimum loss of altitude and accomplished in accordance with the recovery procedure discussed earlier. Recoveries from power-off stalls should be accomplished both with and without the addition of power, and may be initiated either just after the stall occurs or after the nose has pitched down through the level flight attitude. Full stalls power on. Power on stall recoveries are practiced from straight climbs and climbing turns with 15 to 20 degree banks to simulate an accidental stall occurring during takeoffs and climbs. Airplanes equipped with flaps and/or retractable gear should normally be in the takeoff configuration. However, power-on stalls should also be practiced with the aircraft in a clean configuration, flaps and/or gear retracted, as in departure and normal climbs. After establishing the takeoff or climb configuration, the airplane should be slowed to the normal liftoff speed while clearing the area for other air traffic. When the desired speed is attained, the power should be set at takeoff power for the takeoff stall or the recommended climb power for the departure stall while establishing a climb attitude. The purpose of reducing the airspeed to liftoff airspeed before the throttle is advanced to the recommended setting is to avoid an excessively steep nose-up attitude for a long period before the airplane stalls. After the climb attitude is established, the nose is then brought smoothly upward to an attitude obviously impossible for the airplane to maintain, and is held at that attitude until the full stall occurs. In most airplanes, after attaining the stalling attitude, the elevator control must be moved progressively further back as the airspeed decreases until, at the full stall, it will have reached its limit and cannot be moved back any farther. Recovery from the stall should be accomplished by immediately reducing the angle of attack, by positively releasing back elevator pressure, and, in the case of a departure stall, smoothly advancing the throttle to maximum allowable power. In this case, since the throttle is already at the climb power setting, the addition of power will be relatively slight. Figure 4-6. The nose should be lowered as necessary to regain flying speed with a minimum loss of altitude and then raised to climb attitude. Then the airplane should be returned to the normal straight and level flight attitude, and when in normal level flight, the throttle should be returned to cruise power setting. The pilot must recognize instantly when the stall has occurred and take prompt action to prevent a prolonged stall condition. Secondary stall. This stall is called a secondary stall, since it may occur after a recovery from a preceding stall. It is caused by attempting to hasten the completion of a stall recovery before the airplane has regained sufficient flying speed. Figure 4-7. When this stall occurs, the back elevator pressure should be released just as in normal stall recovery. When sufficient airspeed has been regained, the airplane can then be returned to straight and level flight. This stall usually occurs when the pilot uses abrupt control input to return to straight and level flight after a stall or spin recovery. It also occurs when the pilot fails to reduce the angle of attack sufficiently during a stall recovery by not lowering pitch attitude sufficiently, or by attempting to break the stall by using power only. Accelerated stalls. Though the stalls just discussed normally occur at a specific airspeed, the pilot must thoroughly understand that all stalls result solely from attempts to fly at excessively high angles of attack. During flight, the angle of attack of an airplane wing is determined by a number of factors, the most important of which are the airspeed, gross weight of the airplane, and the load factors imposed by maneuvering. At the same gross weight, airplane configuration, and power setting, a given airplane will consistently stall at the same indicated airspeed if no acceleration is involved. The airplane will, however, stall at a higher indicated airspeed when excessive maneuvering loads are imposed by steep turns, pull-ups, or other abrupt changes in its flight path. Stalls entered from such flight situations are called accelerated maneuver stalls, a term which has no reference to the airspeeds involved. Stalls which result from abrupt maneuvers tend to be more rapid or severe than the unaccelerated stalls, and because they occur at higher than normal airspeeds and/or may occur at lower than anticipated pitch attitudes, they may be unexpected by an inexperienced pilot. Failure to take immediate steps toward recovery when an accelerated stall occurs may result in a complete loss of flight control, notably power-on spins. This stall should never be practiced with wing flaps in the extended position due to the lower G-load limitations in that configuration. Accelerated maneuver stalls should not be performed in any airplane which is prohibited from such maneuvers by its type certification restrictions or Airplane Flight Manual, AFM, and/or Pilot's Operating Handbook, POH. If they are permitted, they should be performed with a bank of approximately 45 degrees, and in no case at a speed greater than the airplane manufacturer's recommended airspeeds or the design maneuvering speed specified for the airplane. The design maneuvering speed is the maximum speed at which the airplane can be stalled, or full available aerodynamic control will not exceed the airplane's limit load factor. At or below this speed, the airplane will usually stall before the limit load factor can be exceeded. These speeds must not be exceeded because of the extremely high structural loads that are imposed on the airplane, especially if there is turbulence. In most cases, these stalls should be performed at no more than 1.2 times the normal stall speed. The objective of demonstrating accelerated stalls is not to develop competency in setting up the stall, but rather to learn how they may occur and to develop the ability to recognize such stalls immediately and to take prompt, effective recovery action. It is important that recoveries are made at the first indication of a stall, or immediately after the stall has fully developed. A prolonged stall condition should never be allowed. An airplane will stall during a coordinated steep turn exactly as it does from straight flight, except that the pitching and rolling actions tend to be more sudden. If the airplane is slipping toward the inside of the turn at the time the stall occurs, it tends to roll rapidly toward the outside of the turn as the nose pitches down, because the outside wing stalls before the inside wing. If the airplane is skidding toward the outside of the turn, it will have a tendency to roll to the inside of the turn because the inside wing stalls first. If the coordination of the turn at the time of the stall is accurate, the airplane's nose will pitch away from the pilot just as it does in a straight flight stall, since both wings stall simultaneously. An accelerated stall demonstration is entered by establishing the desired flight attitude, then smoothly, firmly, and progressively increasing the angle of attack until a stall occurs. Because of the rapidly changing flight attitude, sudden stall entry, and possible loss of altitude, it is extremely vital that the area be clear of other aircraft and the entry altitude be adequate for safe recovery. This demonstration stall, as in all stalls, is accomplished by exerting excessive back elevator pressure. Most frequently, it would occur during improperly executed steep turns, stall and spin recoveries, and pullouts from steep dives. The objectives are to determine the stall characteristics of the airplane and develop the ability to instinctively recover at the onset of a stall at other than normal stall speed or flight attitudes. An accelerated stall, although usually demonstrated in steep turns, may actually be encountered anytime excessive back elevator pressure is applied and/or the angle of attack is increased too rapidly. From straight and level flight at maneuvering speed or less, the airplane should be rolled into a steep level flight turn and back elevator pressure gradually applied. After the turn and bank are established, back elevator pressure should be smoothly and steadily increased. The resulting apparent centrifugal force will push the pilot's body down in the seat, increasing the wing loading and decrease the airspeed. After the airspeed reaches the design maneuvering speed, or within 20 knots above the unaccelerated stall speed, back elevator pressure should be firmly increased until a definite stall occurs. These speed restrictions must be observed to prevent exceeding the load limit of the airplane. When the airplane stalls, recovery should be made promptly by releasing sufficient back elevator pressure and increasing power to reduce the angle of attack. If an uncoordinated turn is made, one wing may tend to drop suddenly, causing the airplane to roll in that direction. If this occurs, the excessive back elevator pressure must be released, power added, and the airplane returned to straight and level flight with coordinated control pressure. The pilot should recognize when the stall is imminent and take prompt action to prevent a completely stalled condition. It is imperative that a prolonged stall, excessive airspeed, excessive loss of altitude, or spin be avoided. Cross-control stall. The objective of a cross-control stall demonstration maneuver is to show the effect of improper control technique and to emphasize the importance of using coordinated control pressures whenever making turns. This type of stall occurs with the controls crossed, aileron pressure applied in one direction and rudder pressure applied in the opposite direction. In addition, when excessive back elevator pressure is applied, a cross-control stall may result. This is a stall that is most apt to occur during a poorly planned and executed base-to-final approach turn, and often is the result of overshooting the center line of the runway during that turn. Normally, the proper action to correct for overshooting the runway is to increase the rate of turn by using coordinated aileron and rudder. At the relatively low altitude of a base-to-final approach turn, improperly trained pilots may be apprehensive of steepening the bank to increase the rate of turn, and, rather than steepening the bank, they hold the bank constant and attempt to increase the rate of turn by adding more rudder pressure in an effort to align it with the runway. The addition of inside rudder pressure will cause the speed of the outer wing to increase, therefore creating greater lift on that wing. To keep that wing from rising and to maintain a constant angle of bank, opposite aileron pressure needs to be applied. The added inside rudder pressure will also cause the nose to lower in relation to the horizon. Consequently, additional back elevator pressure would be required to maintain a constant pitch attitude. The resulting condition is a turn with the rudder applied in one direction, aileron in the opposite direction, and excessive back elevator pressure, a pronounced cross-control condition. Since the airplane is in a skidding turn during the cross-control condition, the wing on the outside of the turn speeds up and produces more lift than the inside wing. Thus, the airplane starts to increase its bank. The down aileron on the inside of the turn helps drag that wing back, slowing it up and decreasing its lift, which requires more aileron application. This further causes the airplane to roll. The roll may be so fast that it is possible the bank will be vertical or past vertical before it can be stopped. For the demonstration of the maneuver, it is important that it be entered at a safe altitude because of the possible extreme nose-down attitude and loss of altitude that may result. Before demonstrating this stall, the pilot should clear the area for other air traffic while slowly retarding the throttle. Then the landing gear, if retractable gear, should be lowered and the throttle closed and the altitude maintained until the airspeed approaches the normal glide speed. Because of the possibility of exceeding the airplane's limitations, flaps should not be extended. While the gliding altitude and airspeed are being established, the airplane should be retrimmed. When the glide is stabilized, the airplane should be rolled into a medium banked turn to simulate a final approach turn that would overshoot the center line of the runway. During the turn, excessive rudder pressure should be applied in the direction of the turn, but the bank held constant by applying opposite aileron pressure. At the same time, increased back elevator pressure is required to keep the nose from lowering. All of these control pressures should be increased until the airplane stalls. When the stall occurs, recovery is made by releasing the control pressures and increasing power as necessary to recover. In a cross-control stall, the airplane often stalls with little warning. The nose may pitch down, the inside wing may suddenly drop, and the airplane may continue to roll to an inverted position. This is usually the beginning of a spin. It is obvious that close to the ground is no place to allow this to happen. Recovery must be made before the airplane enters an abnormal attitude, vertical spiral, or spin. It is a simple matter to return to straight and level flight by coordinated use of the controls. The pilot must be able to recognize when this stall is imminent and must take immediate action to prevent a completely stalled condition. It is imperative that this type of stall not occur during an actual approach to a landing, since recovery may be impossible prior to ground contact due to the low altitude. The flight instructor should be aware that during traffic pattern operations, any conditions that result in overshooting the turn from base leg to final approach dramatically increases the possibility of an unintentional accelerated stall while the airplane is in a cross-control condition. Elevator trim stall. The elevator trim stall maneuver shows what can happen when full power is applied for a go-around and positive control of the airplane is not maintained. Figure 4-8. Such a situation may occur during a go-around procedure from a normal landing approach or a simulated forced landing approach, or immediately after takeoff. The objective of the demonstration is to show the importance of making smooth power applications, overcoming strong trim forces, and maintaining positive control of the airplane to hold safe flight attitudes, and using proper and timely trim techniques. At a safe altitude, and after ensuring the area is clear of other aircraft, the pilot should slowly retard the throttle and extend the landing gear, if retractable gear. 1/2 to full flaps should be lowered, the throttle closed, and altitude maintained until the airspeed approaches the normal glide speed. When the normal glide is established, the airplane should be trimmed for the glide, just as would be done during a landing approach, nose-up trim. During the simulated final approach glide, the throttle is then advanced smoothly to maximum allowable power, as would be done in a go-around procedure. The combined forces of thrust, torque, and back elevator trim will tend to make the nose rise sharply and turn to the left. When the throttle is fully advanced and the pitch attitude increases above the normal climbing attitude, and it is apparent that a stall is approaching, adequate forward pressure must be applied to return the airplane to the normal climbing attitude. While holding the airplane in this attitude, the trim should then be adjusted to relieve the heavy control pressures and the normal go-around and level-off procedures completed. The pilot should recognize when a stall is approaching and take prompt action to prevent a completely stalled condition. It is imperative that a stall not occur during an actual go-around from a landing approach. Common errors in the performance of intentional stalls are failure to adequately clear the area, inability to recognize an approaching stall condition through feel for the airplane, premature recovery, over-reliance on the airspeed indicator while excluding other cues, inadequate scanning resulting from an unintentional wing-low condition during entry, excessive back elevator pressure resulting in an exaggerated nose-up attitude during entry, inadequate rudder control, inadvertent secondary stall during recovery, failure to maintain a constant bank angle during turning stalls, excessive forward elevator pressure during recovery resulting in negative load on the wings, excessive airspeed buildup during recovery, failure to take timely action to prevent a full stall during the conduct of imminent stalls. End of Part 2 of Chapter 4. Chapter 4, Part 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Elfer. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 4, Part 3. Spins. A spin may be defined as an aggravated stall that results in what is termed autorotation, wherein the airplane follows a downward corkscrew path. As the airplane rotates around a vertical axis, the rising wing is less stalled than the descending wing, creating a rolling, yawing, and pitching motion. The airplane is basically being forced downward by gravity, rolling, yawing, and pitching in a spiral path. Figure 4-9. The auto-rotation results from an unequal angle of attack on the airplane's wings. The rising wing has a decreasing angle of attack, where the relative lift increases and the drag decreases. In effect, this wing is less stalled. Meanwhile, the descending wing has an increasing angle of attack, past the wing's critical angle of attack, stall, where the relative lift decreases and drag increases. A spin is caused when the airplane's wing exceeds its critical angle of attack, stall, with a side slip or yaw acting on the airplane at or beyond the actual stall. During this uncoordinated maneuver, a pilot may not be aware that a critical angle of attack has been exceeded until the airplane yaws out of control toward the lowering wing. If stall recovery is not initiated immediately, the airplane may enter a spin. If this stall occurs while the airplane is in a slipping or skidding turn, this can result in a spin entry and rotation in the direction that the rudder is being applied, regardless of which wingtip is raised. Many airplanes have to be forced to spin and require considerable judgment and technique to get the spin started. These same airplanes that have to be forced to spin may be accidentally put into a spin by mishandling the controls in turns, stalls, and flight at minimum controllable airspeeds. This fact is additional evidence of the necessity for the practice of stalls until the ability to recognize and recover from them is developed. Often a wing will drop at the beginning of a stall. When this happens, the nose will attempt to move, yaw, in the direction of the low wing. This is where use of the rudder is important during a stall. The correct amount of opposite rudder must be applied to keep the nose from yawing toward the low wing. By maintaining directional control and not allowing the nose to yaw toward the low wing before stall recovery is initiated, a spin will be averted. If the nose is allowed to yaw during the stall, the airplane will begin to slip in the direction of the lowered wing and will enter a spin. An airplane must be stalled in order to enter a spin. Therefore, continued practice in stalls will help the pilot develop a more instinctive and prompt reaction to recognizing an approaching spin. It is essential to learn to apply immediate corrective action anytime it is apparent that the airplane is nearing spin conditions. If it is impossible to avoid a spin, the pilot should immediately execute spin recovery procedures. Spin procedures. The flight instructor should demonstrate spins in those airplanes that are approved for spins. Special spin procedures or techniques required for a particular airplane are not presented here. Before beginning any spin operations, the following items should be reviewed: the airplane's AFM/POH limitations section, placards, or type certification data to determine if the airplane is approved for spins. Weight and balance limitations. Recommended entry and recovery procedures. The requirements for parachutes. It would be appropriate to review a current Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, for the latest parachute requirements. A thorough airplane pre-flight should be accomplished with special emphasis on excess or loose items that may affect the weight, center of gravity, and controllability of the airplane. Slack or loose control cables, particularly rudder and elevator, could prevent full anti-spin control deflections and delay or preclude recovery in some airplanes. Prior to beginning spin training, the flight area above and below the airplane must be clear of other air traffic. This may be accomplished while slowing the airplane for the spin entry. All spin training should be initiated at an altitude high enough for a completed recovery at or above 1,500 feet AGL. It may be appropriate to introduce spin training by first practicing both power on and power off stalls in a clean configuration. This practice would be used to familiarize the student with the airplane's specific stall and recovery characteristics. Care should be taken with handling of the power, throttle, in entries and during spins. Carburetor heat should be applied according to the manufacturer's recommendations. There are 4 phases of a spin: entry, incipient, developed, and recovery. Figure 4-10. Entry phase. The entry phase is where the pilot provides the necessary elements for the spin, either accidentally or intentionally. The entry procedure for demonstrating a spin is similar to a power-off stall. During the entry, the power should be reduced slowly to idle, while simultaneously raising the nose to a pitch attitude that will ensure a stall. As the airplane approaches a stall, smoothly apply full rudder in the direction of the desired spin rotation, while applying full back-up elevator to the limit of travel. Always maintain the ailerons in the neutral position during the spin, unless AFM/POH specifies otherwise. Incipient phase. The incipient phase is from the time the airplane stalls and rotation starts until the spin has fully developed. This change may take up to 2 turns for most airplanes. Incipient spins that are not allowed to develop into a steady-state spin are the most commonly used in the introduction to spin training and recovery techniques. In this phase, the aerodynamic and inertial forces have not achieved a balance. As the incipient spin develops, the indicated airspeed should be near or below stall airspeed, and the turn and slip indicator should indicate the direction of the spin. The incipient spin recovery procedure should be commenced prior to the completion of 360 degrees of rotation. The pilot should apply full rudder opposite to the direction of rotation. If the pilot is not sure of the direction of the spin, check the turn and slip indicator. It will show a deflection in the direction of rotation. Developed phase. The developed phase occurs when the airplane's angular rotation rate, airspeed, and vertical speed are stabilized while in a flight path that is nearly vertical. This is where airplane aerodynamic forces and inertial forces are in balance, and the attitude, angles, and self-sustaining motions about the vertical axis are constant or repetitive. The spin is in equilibrium. Recovery phase. The recovery phase occurs when the angle of attack of the wings decreases below the critical angle of attack and autorotation slows. Then the nose steepens and autorotation stops. This phase may last for a quarter of a turn to several turns. To recover, control inputs are initiated to disrupt the spin equilibrium by stopping the rotation and stall. To accomplish spin recovery, the manufacturer's recommended procedures should be followed. In the absence of the manufacturer's recommended spin recovery procedures and techniques, the following spin recovery procedures are recommended. Step 1. Reduce the power, throttle to idle. Power aggravates the spin characteristics. It usually results in a flatter spin attitude and increased rotation rates. Step 2. Position the ailerons to neutral. Ailerons may have an adverse effect on spin recovery. Aileron control in the direction of the spin may speed up the rate of rotation and delay the recovery. Aileron control opposite the direction of the spin may cause the down aileron to move the wing deeper into the stall and aggravate the situation. The best procedure is to ensure that the ailerons are neutral. Step 3. Apply full opposite rudder against the rotation. Make sure that full, against the stop, opposite rudder has been applied. Step 4. Apply a positive and brisk, straightforward movement of the elevator control forward of the neutral to break the stall. This should be done immediately after full rudder application. The forceful movement of the elevator will decrease the excessive angle of attack and break the stall. The controls should be held firmly in this position. When the stall is broken, the spinning will stop. Step 5. After spin rotation stops, neutralize the rudder. If the rudder is not neutralized at this time, the ensuing increased airspeed acting upon a deflected rudder will cause a yawing or skidding effect. Slow and overly cautious control movements during spin recovery must be avoided. In certain cases, it has been found that such movements result in the airplane continuing to spin indefinitely, even with anti-spin inputs. A brisk and positive technique, on the other hand, results in a more positive spin recovery. Step 6. Begin applying back elevator pressure to raise the nose to level flight. Caution must be used not to apply excessive back elevator pressure after the rotation stops. Excessive back elevator pressure can cause a secondary stall and result in another spin. Care should be taken not to exceed the G-load limits and airspeed limitations during recovery. If the flaps and/or retractable landing gear are extended prior to the spin, they should be retracted as soon as possible after spin entry. It is important to remember that the above spin recovery procedures and techniques are recommended for use only in the absence of the manufacturer's procedures. Before any pilot attempts to begin spin training, the pilot must be familiar with the procedures provided by the manufacturer for spin recovery. The most common problems in spin recovery include pilot confusion as to the direction of spin rotation and whether the maneuver is a spin versus spiral. If airspeed is increasing, the airplane is no longer in a spin but in a spiral. In a spin, the airplane is stalled. The indicated airspeed, therefore, should reflect stall speeds. Intentional spins. The intentional spinning of an airplane, for which the spin maneuver is not specifically approved, is not authorized by this handbook or by the Code of Federal Regulations. The official sources for determining if the spin maneuver is approved or not approved for a specific airplane are type certification data sheets or the aircraft specifications. The limitations section of the FAA-approved AFM/POH. The limitation sections may provide additional specific requirements for spin authorization, such as limiting gross weight, CG range, and amount of fuel. On a placard located in clear view of the pilot and the airplane, no acrobatic maneuvers including spins approved. In airplanes placarded against spins, there is no assurance that recovery from a fully developed spin is possible. There are occurrences involving airplanes wherein spin restrictions are intentionally ignored by some pilots. Despite the installation of placards prohibiting intentional spins in these airplanes, a number of pilots and some flight instructors attempt to justify the maneuver, rationalizing that the spin restriction results merely because of a technicality in the airworthiness standards. Some pilots reason that the airplane was spin tested during its certification process and therefore no problem should result from demonstrating or practicing spins. However, these pilots overlook the fact that a normal category airplane certification only requires the airplane recover from a one-turn spin in not more than one additional turn or 3 seconds, whichever takes longer. This same test of controllability can be used in certificating an airplane in the utility category, 14 CFR section 23.221b. The point is that 360 degrees of rotation, one-turn spin, does not provide a stabilized spin. If the airplane's controllability has not been explored by the engineering test pilot beyond the certification requirements, prolonged spins, inadvertent or intentional in that airplane, place an operating pilot in an unexplored flight situation. Recovery may be difficult or impossible. In 14 CFR Part 23, Airworthiness Standards, Normal, Utility, Acrobatic, and Commuter category airplanes, there are no requirements for investigation of controllability in a true spinning condition for the normal category airplanes. The one-turn margin of safety is essentially a check of the airplane's controllability in a delayed recovery from a stall. Therefore, in airplanes placarded against spins, there is absolutely no assurance whatever that recovery from a fully developed spin is possible under any circumstances. The pilot of an airplane placarded against intentional spins should assume that the airplane may well become uncontrollable in a spin. Weight and balance requirements. With each airplane that is approved for spinning, the weight and balance requirements are important for safe performance and recovery from the spin maneuver. Pilots must be aware that just minor weight or balance changes can affect the airplane's spin recovery characteristics. Such changes can either alter or enhance the spin maneuver and/or recovery characteristics. For example, the addition of weight in the aft baggage compartment or additional fuel may still permit the airplane to be operated within CG, but could seriously affect the spin and recovery characteristics. An airplane that may be difficult to spin intentionally in the utility category, restricted aft CG, and reduced weight could have less resistance to spin entry in the normal category, less restricted aft CG, and increased weight. The situation is due to the airplane being able to generate a higher angle of attack and load factor. Furthermore, an airplane that is approved for spins in the utility category, but loaded in the normal category, may not recover from a spin that is allowed to progress beyond the incipient phase. Common errors in the performance of intentional spins are failure to apply full rudder pressure in the desired spin direction during spin entry, failure to apply and maintain full up elevator pressure during spin entry, resulting in a spiral, failure to achieve a fully stalled condition prior to spin entry, failure to apply full rudder against the spin during recovery, failure to apply sufficient forward elevator pressure during recovery, failure to neutralize the rudder during recovery after rotation stops, resulting in a possible secondary spin, slow and overly cautious control movements during recovery, excessive back elevator pressure after rotation stops, resulting in possible secondary stall, insufficient back elevator pressure during recovery, resulting in excessive airspeed. End of Chapter 4.
Chapter 5, Part 1 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Takeoffs and Departure Climbs, Part 1. General. This chapter discusses takeoffs and departure climbs in tricycle landing gear, nosewheel type airplanes under normal conditions, and under conditions which require maximum performance. A thorough knowledge of takeoff principles both in theory and practice will often prove of extreme value throughout a pilot's career. It will often prevent an attempted takeoff that would result in an accident or during an emergency, make possible a takeoff under critical conditions when a pilot with a less well-rounded knowledge and technique would fail. The takeoff, though relatively simple, often presents the most hazards of any part of a flight. The importance of thorough knowledge and faultless technique and judgment cannot be overemphasized. It must be remembered that the manufacturer's recommended procedures, including airplane configuration and airspeeds and other information relevant to takeoffs and departure climbs in a specific make and model airplane, are contained in the FAA-approved Airplane Flight Manual and/or Pilot's Operating Handbook, AFM-POH, for that airplane. If any of the information in this chapter differs from the airplane manufacturer's recommendations as contained in the AFM-POH, the airplane manufacturer's recommendations take precedence. Terms and definitions. Although the takeoff and climb is one continuous maneuver, it will be divided into 3 separate steps for purposes of explanation. 1. The takeoff roll. 2. The liftoff. And 3. The initial climb after becoming airborne. See Figure 5-1. Takeoff roll, ground roll. The portion of the takeoff procedure during which the airplane is accelerated from a standstill to an airspeed that provides sufficient lift for it to become airborne. Liftoff, rotation. the act of becoming airborne as a result of the wings lifting the airplane off the ground or the pilot rotating the nose up, increasing the angle of attack to start a climb. Initial climb begins when the airplane leaves the ground and a pitch attitude has been established to climb away from the takeoff area. Normally, it is considered complete when the airplane has reached a safe maneuvering altitude or an en route climb has been established. Prior to takeoff, before taxiing onto the runway or takeoff area, the pilot should ensure that the engine is operating properly and that all controls, including flaps and trim tabs, are set in accordance with the before takeoff checklist. In addition, the pilot must make certain that the approach and takeoff paths are clear of other aircraft. At uncontrolled airports, pilots should announce their intentions on the Common Traffic Advisory Frequency, CTAF, assigned to that airport. When operating from an airport with an operating control tower, pilots must contact the tower operator and receive a takeoff clearance before taxiing onto the active runway. It is not recommended to take off immediately behind another aircraft, particularly large, heavily loaded transport airplanes, because of the wake turbulence that is generated. While taxiing onto the runway, the pilot can select ground reference points that are aligned with the runway direction as aids to maintaining directional control during the takeoff. These may be runway centerline markings, runway lighting, distant trees, towers, buildings, or mountain peaks. Normal takeoff. A normal takeoff is one in which the airplane is headed into the wind or the wind is very light. Also, the takeoff surface is firm and of sufficient length to permit the airplane to gradually accelerate to normal liftoff and climb-out speed, and there are no obstructions along the takeoff path. There are two reasons for making a takeoff as nearly into the wind as possible. First, the airplane's speed while on the ground is much less than if the takeoff were made downwind, thus reducing wear and stress on the landing gear. Second, a shorter ground roll and therefore much less runway length is required to develop the minimum lift necessary for takeoff and climb. Since the airplane depends on airspeed in order to fly, a headwind provides some of that airspeed, even with the airplane motionless, from the wind flowing over the wings. Takeoff roll. After taxiing onto the runway, the airplane should be carefully aligned with the intended takeoff direction and the nose wheel positioned straight or centered. After releasing the brakes, the throttle should be advanced smoothly and continuously to take off power. An abrupt application of power may cause the airplane to yaw sharply to the left because of the torque effects of the engine and propeller. This will be most apparent in high horsepower engines. As the airplane starts to roll forward, the pilot should assure both feet are on the rudder pedals so that the toes or balls of the feet are on the rudder portions, not on the brake portions. Engine instruments should be monitored during takeoff roll for any malfunctions. In nose-wheel type airplanes, pressures on the elevator control are not necessary beyond those needed to steady it. Applying unnecessary pressure will only aggravate the takeoff and prevent the pilot from recognizing when elevator control pressure is actually needed to establish the takeoff attitude. As speed is gained, the elevator control will tend to assume a neutral position if the airplane is correctly trimmed. At the same time, directional control should be maintained with smooth, prompt, positive rudder corrections throughout the takeoff roll. The effects of engine torque and P factor at the initial speeds tend to pull the nose to the left. The pilot must use whatever rudder pressure and aileron needed to correct for these effects or for existing wind conditions to keep the nose of the airplane headed straight down the runway. The use of brakes for steering purposes should be avoided, since this will cause slower acceleration of the airplane's speed, lengthening the takeoff distance, and possibly result in severe swerving. While the speed of the takeoff roll increases, more and more pressure will be felt on the flight controls, particularly the elevators and rudder. If the tail surfaces are affected by the propeller slipstream, they become effective first. As the speed continues to increase, all of the flight controls will gradually become effective enough to maneuver the airplane about its three axes. It is at this point, in the taxi to flight transition, that the airplane is being flown more than taxied. As this occurs, progressively smaller rudder deflections are needed to maintain direction. The feel of resistance to the movement of the controls and the airplane's reaction to such movements are the only real indicators of the degree of control attained. This feel of resistance is not a measure of the airplane's speed, but rather of its controllability. To determine the degree of controllability, the pilot must be conscious of the reaction of the airplane to the control pressures and immediately adjust the pressures as needed to control the airplane. The pilot must wait for the reaction of the airplane to the applied control pressures and attempt to sense the control resistance to pressure, rather than attempt to control the airplane by movement of the controls. Balanced control surfaces increase the importance of this point because they materially reduce the intensity of the resistance offered to pressures exerted by the pilot. At this stage of training, beginning takeoff practice, a student pilot will normally not have a full appreciation of the variations of control pressures with the speed of the airplane. The student, therefore, may tend to move the controls through wide ranges, seeking the pressures that are familiar and expected, and as a consequence over-control the airplane. The situation may be aggravated by the sluggish reaction of the airplane to these movements. The flight instructor should take measures to check these tendencies and stress the importance of the development of feel. The student pilot should be required to feel lightly for resistance and accomplish the desired results by applying pressure against it. This practice will enable the student pilot, as experience is gained, to achieve a sense of the point when sufficient speed has been acquired for the takeoff, instead of merely guessing, fixating on the airspeed indicator, or trying to force performance from the airplane. Liftoff. Since a good takeoff depends on the proper takeoff attitude, it is important to know how this attitude appears and how it is attained. The ideal takeoff attitude requires only minimum pitch adjustments shortly after the airplane lifts off to attain the speed for the best rate of climb. VY. See Figure 5-2. The pitch attitude necessary for the airplane to accelerate to VY speed should be demonstrated by the instructor and memorized by the student. Initially, the student pilot may have a tendency to hold excessive back elevator pressure just after liftoff, resulting in an abrupt pitch up. The flight instructor should be prepared for this. Each type of airplane has a best pitch attitude for normal liftoff. However, varying conditions may make a difference in the required takeoff technique. A rough field, a smooth field, a hard surface runway, or a short or soft muddy field all call for a slightly different technique, as will smooth air in contrast to a strong gusty wind. The different techniques for those other than normal conditions are discussed later in this chapter. When all the flight controls become effective during the takeoff roll in a nose-wheel type airplane, back elevator pressure should be gradually applied to raise the nose wheel slightly off the runway, thus establishing the takeoff or liftoff attitude. This is often referred to as rotating. At this point, the position of the nose in relation to the horizon should be noted, then back elevator pressure applied as necessary to hold this attitude. The wings must be kept level by applying aileron pressure as necessary. The airplane is allowed to fly off the ground while in the normal takeoff attitude. Forcing it into the air by applying excessive back elevator pressure would only result in an excessively high pitch attitude and may delay the takeoff. As discussed earlier, excessive and rapid changes in pitch attitude result in proportionate changes in the effects of torque, thus making the airplane more difficult to control. Although the airplane can be forced into the air, this is considered an unsafe practice and should be avoided under normal circumstances. If the airplane is forced to leave the ground by using too much back elevator pressure before adequate flying speed is attained, the wing's angle of attack may be excessive, causing the airplane to settle back to the runway or even to stall. On the other hand, if sufficient back elevator pressure is not held to maintain the correct takeoff attitude after becoming airborne, or the nose is allowed to lower excessively, the airplane may also settle back to the runway. This would occur because the angle of attack is decreased and lift diminished to the degree where it will not support the airplane. It is important, then, to hold the correct attitude constant after rotation or liftoff. As the airplane leaves the ground, the pilot must continue to be concerned with maintaining the wings in a level attitude. as well as holding the proper pitch attitude. Outside visual scan to maintain proper airplane pitch and bank attitude must be intensified at this critical point. The flight controls have not yet become fully effective, and the beginning pilot will often have a tendency to fixate on the airplane's pitch attitude and/or airspeed indicator and neglect the natural tendency of the airplane to roll just after breaking ground. During takeoffs in a strong, gusty wind, it is advisable that an extra margin of speed be obtained before the airplane is allowed to leave the ground. A takeoff at the normal takeoff speed may result in a lack of positive control or a stall when the airplane encounters a sudden lull in strong, gusty wind or other turbulent air currents. In this case, the pilot should allow the airplane to stay on the ground longer to attain more speed, then make a smooth, positive rotation to leave the ground. Initial climb. Upon liftoff, the airplane should be flying at approximately the pitch attitude that will allow it to accelerate to Vy. This is the speed at which the airplane will gain the most altitude in the shortest period of time. If the airplane has been properly trimmed, some back elevator pressure may be required to hold this attitude until the proper climb speed is established. On the other hand, relaxation of any back elevator pressure before this time may result in the airplane settling, even to the extent that it contacts the runway. The airplane will pick up speed rapidly after it becomes airborne. Once a positive rate of climb is established, the flaps and landing gear can be retracted, if equipped. It is recommended that takeoff power be maintained until reaching an altitude of at least 500 feet above the surrounding terrain or obstacles. The combination of Vy and takeoff power assures the maximum altitude gained in a minimum amount of time. This gives the pilot more altitude from which the airplane can be safely maneuvered in case of an engine failure or other emergency. Since the power on the initial climb is fixed at the takeoff power setting, the airspeed must be controlled by making slight pitch adjustments using the elevators. However, the pilot should not fixate on the airspeed indicator when making these pitch changes, but should instead continue to scan outside to adjust the airplane's attitude in relation to the horizon. In accordance with the principles of attitude flying, the pilot should first make the necessary pitch change with reference to the natural horizon and hold the new attitude momentarily, and then glance at the airspeed indicator as a check to see if the new attitude is correct. Due to inertia, the airplane will not accelerate or decelerate immediately as the pitch is changed. It takes a little time for the airspeed to change. If the pitch attitude has been over or under corrected, the airspeed indicator will show a speed that is more or less than that desired. When this occurs, the cross-checking and appropriate pitch-changing process must be repeated until the desired climbing attitude is established. When the correct pitch attitude has been attained, it should be held constant while cross-checking it against the horizon and other outside visual references. The airspeed indicator should be used only as a check to determine if the attitude is correct. After the recommended climb airspeed has been established and a safe maneuvering altitude has been reached, the power should be adjusted to the recommended climb setting and the airplane trimmed to relieve the control pressures. This will make it easier to hold a constant attitude and airspeed. During initial climb, it is important that the takeoff path remain aligned with the runway to avoid drifting into obstructions or the path of another aircraft that may be taking off from a parallel runway. Proper scanning techniques are essential to a safe takeoff and climb, not only for maintaining attitude and direction, but also for collision avoidance in the airport area. When the student pilot nears the solo stage of flight training, it should be explained that the airplane's takeoff performance will be much different when the instructor is out of the airplane. Due to decreased load, the airplane will become airborne sooner and will climb more rapidly. The pitch attitude that the student has learned to associate with initial climb may also differ due to decreased weight, and the flight controls may seem more sensitive. If the situation is unexpected, it may result in increased tension that may remain until after the landing. Frequently, the existence of this tension and the uncertainty that develops due to the perception of an abnormal takeoff results in poor performance on the subsequent landing. Common errors in the performance of normal takeoffs and departure climbs are failure to adequately clear the area prior to taxiing into position on the active runway, abrupt use of the throttle, failure to check engine instruments for signs of malfunction after applying takeoff power, failure to anticipate the airplane's left-turning tendency on initial acceleration, overcorrecting for left-turning tendency, relying solely on the airspeed indicator rather than develop feel for indications of speed and airplane controllability during acceleration and liftoff, failure to attain proper liftoff attitude, inadequate compensation for torque P-factor during initial climb resulting in a side slip, over-control of elevators during initial climb out, limiting scan to areas directly ahead of the airplane, pitch attitude and direction, resulting in allowing a wing, usually the left, to drop immediately after liftoff. Failure to maintain best rate of climb airspeed, VY. Failure to employ the principles of attitude flying during climb out, resulting in chasing the airspeed indicator. Crosswind takeoff. While it is usually preferable to take off directly into the wind whenever possible or practical, there will be many instances when circumstances or judgment will indicate otherwise. Therefore, the pilot must be familiar with the principles and techniques involved in crosswind takeoffs, as well as those for normal takeoffs. A crosswind will affect the airplane during takeoff much as it does in taxiing. With this in mind, it can be seen that the technique for crosswind correction during takeoffs closely parallels the crosswind correction techniques used in taxiing. Takeoff roll. The technique used during the initial takeoff roll in a crosswind is generally the same as used in a normal takeoff, except that aileron control must be held into the crosswind. This raises the aileron on the upwind wing to impose a downward force on the wing to counteract the lifting force of the crosswind and prevents the wing from rising. As the airplane is taxied into takeoff position, it is essential that the windsock and other wind direction indicators be checked so that the presence of a crosswind may be recognized and anticipated. If a crosswind is indicated, full aileron should be held into the wind as the takeoff roll is started. This control position should be maintained while the airplane is accelerating and until the ailerons start becoming sufficiently effective for maneuvering the airplane about its longitudinal axis. With the aileron held into the wind, the takeoff path must be held straight with the rudder. See Figure 5-3. Normally, this will require applying downwind rudder pressure, since on the ground the airplane will tend to weather vane into the wind. When takeoff power is applied, torque or P-factor that yaws the airplane to the left may be sufficient to counteract the weather vaning tendency caused by a crosswind from the right. On the other hand, it may also aggravate the tendency to swerve left when the wind is from the left. In any case, whatever rudder pressure is required to keep the airplane rolling straight down the runway should be applied. As the forward speed of the airplane increases and the crosswind becomes more of a relative headwind, the mechanical holding of full aileron into the wind should be reduced. It is when increasing pressure is being felt on the aileron control that the ailerons are becoming more effective. As the aileron's effectiveness increases and the crosswind component of the relative wind becomes less effective, it will be necessary to gradually reduce the aileron pressure. The crosswind component effect does not completely vanish, so some aileron pressure will have to be maintained throughout the takeoff roll to keep the crosswind from raising the upwind wing. If the upwind wing rises, thus exposing more surface to the crosswind, a skipping action may result. See Figure 5-4. This is usually indicated by a series of very small bounces caused by the airplane attempting to fly and then settling back onto the runway. During these bounces, the crosswind also tends to move the airplane sideways, and these bounces will develop into side skipping. This side skipping imposes severe side stresses on the landing gear and could result in structural failure. It is important during a crosswind takeoff roll to hold sufficient aileron into the wind not only to keep the upwind wing from rising, but to hold that wing down so that the airplane will immediately after liftoff be side slipping into the wind enough to counteract drift. Liftoff. As the nose wheel is being raised off the runway, the holding of aileron control into the wind may result in the downwind wing rising and the downwind main wheel lifting off the runway first, with the remainder of the takeoff roll being made on that one main wheel. This is acceptable and is preferable to side skipping. If a significant crosswind exists, the main wheel should be held on the ground slightly longer than in a normal takeoff so that a smooth but very definite liftoff can be made. This procedure will allow the airplane to leave the ground under more positive control so that it will definitely remain airborne while the proper amount of wind correction is being established. More importantly, this procedure will avoid imposing excessive side loads on the landing gear and prevent possible damage that would result from the airplane settling back to the runway while drifting. As both main wheels leave the runway and ground friction no longer resists drifting, the airplane will be slowly carried sideways with the wind unless adequate drift correction is maintained by the pilot. Therefore, it is important to establish and maintain the proper amount of crosswind correction prior to liftoff by applying aileron pressure toward the wind to keep the upwind wing from rising and applying rudder pressure as needed to prevent weather vaning. Initial climb. If proper crosswind correction is being applied, as soon as the airplane is airborne, it will be side-slipping into the wind sufficiently to counteract the drifting effect of the wind. See Figure 5-5. This side-slipping should be continued until the airplane has a positive rate of climb. At that time, the airplane should be turned into the wind to establish just enough wind correction angle to counteract the wind, and then the wings rolled level. Firm and aggressive use of the rudders will be required to keep the airplane headed straight down the runway. The climb with the wind correction angle should be continued to follow a ground track aligned with the runway direction. However, because the force of a crosswind may vary markedly within a few hundred feet of the ground, frequent checks of actual ground track should be made, and the wind correction adjusted as necessary. The remainder of the climb technique is the same used for normal takeoffs and climbs. Common errors in the performance of crosswind takeoffs are: failure to adequately clear the area prior to taxiing onto the active runway, using less than full aileron pressure into the wind initially on the takeoff roll, mechanical use of aileron control rather than sensing the need for varying aileron control input through feel for the airplane, premature liftoff resulting in side skipping, excessive aileron input in the latter stage of the takeoff roll resulting in a steep bank into the wind at liftoff, inadequate drift correction after liftoff. End of Takeoffs and Departure Climbs, Part 1. Chapter 5, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Takeoffs and Departure Climbs, Part 2. Ground effect on takeoff. Ground effect is a condition of improved performance encountered when the airplane is operating very close to the ground. Ground effect can be detected and measured up to an altitude equal to one wingspan above the surface. See Figure 5-6. However, ground effect is most significant when the airplane, especially a low-wing airplane, is maintaining a constant attitude at low airspeed at low altitude. For example, during takeoff, when the airplane lifts off and accelerates to climb speed, and during the landing flare before touchdown. When the wing is under the influence of ground effect, there is a reduction in upwash, downwash, and wingtip vortices. As a result of the reduced wingtip vortices, induced drag is reduced. When the wing is at a height equal to 1/4 the span, the reduction in induced drag is about 25%. And when the wing is at a height equal to 1/10 the span, the reduction in induced drag is about 50%. At high speeds where parasite drag dominates, induced drag is a small part of the total drag. Consequently, the effects of ground effect are of greater concern during takeoff and landing. On takeoff, the takeoff roll, liftoff, and the beginning of the initial climb are accomplished in the ground effect area. The ground effect causes local increases in static pressure, which cause the airspeed indicator and altimeter to indicate slightly less than they should, and usually results in the vertical speed indicator indicating a descent. As the airplane lifts off and climbs out of the ground effect area, however, the following will occur. The airplane will require an increase in angle of attack to maintain the same lift coefficient. The airplane will experience an increase in the induced drag and thrust required. The airplane will experience a pitch-up tendency and will require less elevator travel because of an increase in downwash at the horizontal tail. The airplane will experience a reduction in static source pressure as it leaves the ground effect area and a corresponding increase in indicated airspeed. Due to the reduced drag in ground effect, the airplane may seem to be able to take off below the recommended airspeed. However, as the airplane rises out of ground effect with an insufficient airspeed, initial climb performance may prove to be marginal because of the increased drag. Under conditions of high density altitude, high temperature, and/or maximum gross weight, the airplane may be able to become airborne at an insufficient airspeed, but unable to climb out of ground effect. Consequently, the airplane may not be able to clear obstructions or may settle back on the runway. The point to remember is that additional power is required to compensate for increases in drag that occur as an airplane leaves ground effect, but during an initial climb the engine is already developing maximum power. The only alternative is to lower pitch attitude to gain additional airspeed, which will result in inevitable altitude loss. Therefore, under marginal conditions, it is important that the airplane takes off at the recommended speed that will provide adequate initial climb performance. Ground effect is important to normal flight operations. If the runway is long enough, or if no obstacles exist, ground effect can be used to an advantage by using the reduced drag to improve initial acceleration. Additionally, the procedure for takeoff from unsatisfactory surfaces is to take as much weight on the wings as possible during the ground run and to lift off with the aid of ground effect before true flying speed is attained. It is then necessary to reduce the angle of attack to attain normal airspeed before attempting to fly away from the ground effect area. Short field takeoff and maximum performance climb. Takeoffs and climbs from fields where the takeoff area is short or the available takeoff area is restricted by obstructions require that the pilot operate the airplane at the limit of its takeoff performance capabilities. To depart from such an area safely, the pilot must exercise positive and precise control of airplane attitude and airspeed so that takeoff and climb performance results in the shortest ground roll and the steepest angle of climb. See Figure 5-7. The achieved result should be consistent with the performance section of the FAA-approved Airplane Flight Manual and/or Pilot's Operating Handbook, AFM-POH. In all cases, the power setting, flap setting, airspeed, and procedures prescribed by the airplane's manufacturer should be followed. In order to accomplish a maximum performance takeoff safely, the pilot must have adequate knowledge in the use and effectiveness of the best angle of climb speed, Vx, and the best rate of climb speed, Vy, for the specific make and model of airplane being flown. The speed for Vx is that which will result in the greatest gain in altitude for a given distance over the ground. It is usually slightly less than Vy, which provides the greatest gain in altitude per unit of time. The specific speeds to be used for a given airplane are stated in the FAA-approved AFM-POH. It should be emphasized that in some airplanes, a deviation of 5 knots from the recommended speed will result in a significant reduction in climb performance. Therefore, precise control of airspeed has an important bearing on the successful execution as well as the safety of the maneuver. Takeoff roll. Taking off from a short field requires the takeoff to be started from the very beginning of the takeoff area. At this point, the airplane is aligned with the intended takeoff path. If the airplane manufacturer recommends the use of flaps, they should be extended the proper amount before starting the takeoff roll. This permits the pilot to give full attention to the proper technique and the airplane's performance throughout the takeoff. Some authorities prefer to hold the brakes until the maximum obtainable engine RPM is achieved before allowing the airplane to begin its takeoff run. However, it has not been established that this procedure will result in a shorter takeoff run in all light single-engine airplanes. Takeoff power should be applied smoothly and continuously without hesitation to accelerate the airplane as rapidly as possible. The airplane should be allowed to roll with its full weight on the main wheels and accelerated to the liftoff speed. As the takeoff roll progresses, the airplane's pitch attitude and angle of attack should be adjusted to that which results in the minimum amount of drag and the quickest acceleration. In nosewheel type airplanes, this will involve little use of the elevator control, since the airplane is already in a low drag attitude. Liftoff. Approaching best angle of climb speed, Vx, the airplane should be smoothly and firmly lifted off or rotated by applying back elevator pressure to an attitude that will result in the best angle of climb airspeed, Vx. Since the airplane will accelerate more rapidly after liftoff, additional back elevator pressure becomes necessary to hold a constant speed. After becoming airborne, a wing's level climb should be maintained at Vx until obstacles have been cleared, or, if no obstacles are involved, until an altitude of at least 50 feet above the takeoff surface is attained. Thereafter, the pitch attitude may be lowered slightly and the climb continued at best rate of climb speed, Vy, until reaching a safe maneuvering altitude. Remember that an attempt to pull the airplane off the ground prematurely or to climb too steeply may cause the airplane to settle back to the runway or into the obstacles. Even if the airplane remains airborne, the initial climb will remain flat and climb performance, obstacle clearance, ability seriously degraded until best angle of climb airspeed, Vx, is achieved. See Figure 5-8. The objective is to rotate to the appropriate pitch attitude at or near best angle of climb airspeed. It should be remembered, however, that some airplanes will have a natural tendency to lift off well before reaching Vx. In these airplanes, it may be necessary to allow the airplane to lift off in ground effect and then reduce pitch attitude to level until the airplane accelerates to best angle of climb airspeed with the wheels just clear of the runway surface. This method is preferable to forcing the airplane to remain on the ground with forward elevator pressure until best angle of climb speed is attained. Holding the airplane on the ground unnecessarily puts excessive pressure on the nose wheel, may result in wheelbarrowing, and will hinder both acceleration and overall airplane performance. Initial climb. On short field takeoffs, the landing gear and flaps should remain in takeoff position until clear of obstacles, or as recommended by the manufacturer, and Vy has been established. It is generally unwise for the pilot to be looking in the cockpit or reaching for landing gear and flap controls until obstacle clearance is assured. When the airplane is stabilized at Vy, the gear, if equipped, and then the flaps should be retracted. It is usually advisable to raise the flaps in increments to avoid sudden loss of lift and settling of the airplane. Next, reduce the power to the normal climb setting, or as recommended by the airplane manufacturer. Common errors in the performance of short field takeoffs and maximum performance climbs are: failure to adequately clear the area, failure to utilize all available runway takeoff area, failure to have the airplane properly trimmed prior to takeoff, premature liftoff resulting in high drag, holding the airplane on the ground unnecessarily with excessive forward elevator pressure, inadequate rotation resulting in excessive speed after liftoff, inability to maintain best angle of climb airspeed, fixation on the airspeed indicator during initial climb, premature retraction of landing gear and/or wing flaps. Soft, rough field takeoff and climb. Takeoffs and climbs from soft fields require the use of operational techniques for getting the airplane airborne as quickly as possible to eliminate the drag caused by tall grass, soft sand, mud, and snow, and may or may not require climbing over an obstacle. The technique makes judicious use of ground effect and requires a feel for the airplane and fine control touch. These same techniques are also useful on a rough field, where it is advisable to get the airplane off the ground as soon as possible to avoid damaging the landing gear. Soft surfaces or long, wet grass usually reduces the airplane's acceleration during the takeoff roll so much that adequate takeoff speed might not be attained if normal takeoff techniques were employed. It should be emphasized that the correct takeoff procedure for soft fields is quite different from that appropriate for short fields with firm, smooth surfaces. To minimize the hazards associated with takeoffs from soft or rough fields, support of the airplane's weight must be transferred as rapidly as possible from the wheels to the wings as the takeoff roll proceeds. Establishing and maintaining a relatively high angle of tack or nose-high pitch attitude as early as possible does this. Wing flaps may be lowered prior to starting the takeoff, if recommended by the manufacturer, to provide additional lift and to transfer the airplane's weight from the wheels to the wings as early as possible. Stopping on a soft surface such as mud or snow might bog the airplane down. Therefore, it should be kept in continuous motion with sufficient power while lining up for the takeoff roll. Takeoff roll. As the airplane is aligned with the takeoff path, takeoff power is applied smoothly and as rapidly as the power plant will accept it without faltering. As the airplane accelerates, enough back elevator pressure should be applied to establish a positive angle of attack and to reduce the weight supported by the nose wheel. When the airplane is held at a nose-high attitude throughout the takeoff run, the wings will, as speed increases and lift develops, progressively relieve the wheels of more and more of the airplane's weight, thereby minimizing the drag caused by surface irregularities or adhesion. If this attitude is accurately maintained, the airplane will virtually fly itself off the ground, becoming airborne at airspeed slower than a safe climb speed because of ground effect. See Figure 5-9. After becoming airborne, the nose should be lowered very gently with the wheels clear of the surface to allow the airplane to accelerate to Vy or Vx if obstacles must be cleared. Extreme care must be exercised immediately after the airplane becomes airborne and while it accelerates to avoid settling back onto the surface. An attempt to climb prematurely or too steeply may cause the airplane to settle back to the surface as a result of losing the benefit of ground effect. An attempt to climb out of ground effect before sufficient climb airspeed is attained may result in the airplane being unable to climb further as the ground effect area is transited, even with full power. Therefore, it is essential that the airplane remain in ground effect until at least Vx is reached. This requires feel for the airplane and a very fine control touch in order to avoid over-controlling the elevator as required control pressures change with airplane acceleration. Initial climb. After a positive rate of climb is established and the airplane is accelerated to Vy, retract the landing gear and flaps if equipped. If departing from an airstrip with wet snow or slush on the takeoff surface, the gear should not be retracted immediately. This allows for any wet snow or slush to be air dried. In the event an obstacle must be cleared after a soft field takeoff, the climb out is performed at Vx until the obstacle has been cleared. After reaching this point, the pitch attitude is adjusted to Vy and the gear and flaps are retracted. The power may then be reduced to the normal climb setting. Common errors in the performance of soft, rough field takeoff and climbs are: failure to adequately clear the area, insufficient back elevator pressure during initial takeoff roll resulting in inadequate angle of attack, failure to cross-check engine instruments for indications of proper operation after applying power, poor directional control, climbing too steeply after liftoff, abrupt and/or excessive elevator control while attempting to level off and accelerate after liftoff, allowing the airplane to mush or settle resulting in an inadvertent touchdown after liftoff, attempting to climb out of ground effect area before attaining sufficient climb speed, failure to anticipate an increase in pitch attitude as the airplane climbs out of ground effect. Rejected takeoff engine failure. Emergency or abnormal situations can occur during a takeoff that will require a pilot to reject the takeoff while still on the runway. Circumstances such as a malfunctioning power plant, inadequate acceleration, runway incursion, or air traffic conflict may be reasons for a rejected takeoff. Prior to takeoff, the pilot should have in mind a point along the runway at which the airplane should be airborne. If that point is reached and the airplane is not airborne, immediate action should be taken to discontinue the takeoff. Properly planned and executed, chances are excellent the airplane can be stopped on the remaining runway without using extraordinary measures, such as excessive braking that may result in loss of directional control, airplane damage, and/or personal injury. In the event a takeoff is rejected, the power should be reduced to idle and maximum braking applied while maintaining directional control. If it is necessary to shut down the engine due to a fire, the mixture control should be brought to the idle cutoff position and the magnetos turned off. In all cases, the manufacturer's emergency procedure should be followed. What characterizes all power loss or engine failure occurrences after liftoff is urgency. In most instances, the pilot has only a few seconds after an engine failure to decide what course of action to take and to execute it. Unless prepared in advance to make the proper decision, there is an excellent chance the pilot will make a poor decision, or make no decision at all and allow events to rule. In the event of an engine failure on initial climb out, the pilot's first responsibility is to maintain aircraft control. At a climb pitch attitude without power, the airplane will be at a near stalling angle of attack. At the same time, the pilot may still be holding right rudder. It is essential the pilot immediately lower the pitch attitude to prevent a stall and possible spin. The pilot should establish a controlled glide toward a plausible landing area, preferably straight ahead on the remaining runway. Noise abatement. Aircraft noise problems have become a major concern at many airports throughout the country. Many local communities have pressured airports into developing specific operational procedures that will help limit aircraft noise while operating over nearby areas. For years now, the FAA, airport managers, aircraft operators, pilots, and special interest groups have been working together to minimize aircraft noise for nearby sensitive areas. As a result, noise abatement procedures have been developed for many of these airports that include standardized profiles and procedures to achieve these lower noise goals. Airports that have noise abatement procedures provide information to pilots, operators, air carriers, air traffic facilities, and other special groups that are applicable to their airport. These procedures are available to the aviation community by various means. Most of this information comes from the Airport Facility Directory, local and regional publications, printed handouts, operator bulletin boards, safety briefings, and local air traffic facilities. At airports that use noise abatement procedures, reminder signs may be installed at the taxiway hold positions for applicable runways. These are to remind pilots to use and comply with noise abatement procedures on departure. Pilots who are not familiar with these procedures should ask the tower or air traffic facility for the recommended procedures. In any case, pilots should be considerate of the surrounding community while operating their airplane to and from such an airport. This includes operating as quietly yet safely as possible. End of Takeoffs and Departure Climbs, Part 2.
Chapter 6, Part 1 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook, Volume 1, by Federal Aviation Administration. Chapter 6, Ground Reference Maneuvers, Part 1, Purpose and Scope. Ground reference maneuvers and their related factors are used in developing a high degree of pilot skill. Although most of these maneuvers are not performed as such in normal everyday flying, the elements and principles involved in each are applicable to performance of the customary pilot operations. They aid the pilot in analyzing the effect of wind and other forces acting on the airplane, and in developing a fine control touch, coordination, and the division of attention necessary for accurate and safe maneuvering of the airplane. All of the early part of the pilot's training has been conducted at relatively high altitudes, and for the purpose of developing technique, knowledge of maneuvers, coordination, feel, and the handling of the airplane in general. This training will have required that most of the pilot's attention be given to the actual handling of the airplane and the results of control pressures on the action and attitude of the airplane. If permitted to continue beyond the appropriate training stage, however, the student pilot's concentration of attention will become a fixed habit, one that will seriously detract from the student's ease and safety as a pilot, and will be very difficult to eliminate. Therefore, it is necessary, as soon as the pilot shows proficiency in the fundamental maneuvers, that the pilot be introduced to maneuvers requiring outside attention on a practical application of these maneuvers and the knowledge gained. It should be stressed that, during ground reference maneuvers, it is equally important that basic flying technique previously learned be maintained. The flight instructor should not allow any relaxation of the student's previous standard of technique, simply because a new factor is added. This requirement should be maintained throughout the student's progress from maneuver to maneuver. Each new maneuver should embody some advance and include the principles of the preceding one, in order that continuity be maintained. Each new factor introduced should be merely a step up of one already learned, so that orderly, consistent progress can be made. Maneuvering by reference to ground objects. Ground track or ground reference maneuvers are performed at a relatively low altitude, while applying wind drift correction as needed to follow a predetermined track or path over the ground. They are designed to develop the ability to control the airplane and to recognize and correct for the effect of wind, while dividing attention among other matters. This requires planning ahead of the airplane, maintaining orientation in relation to ground objects, flying appropriate headings to follow a desired ground track, and being cognizant of other air traffic in the immediate vicinity. Ground reference maneuvers should be flown at an altitude of approximately 600 to 1,000 feet AGL. The actual altitude will depend on the speed and type of airplane to a large extent, and the following factors should be considered. The speed with relation to the ground should not be so apparent that events happen too rapidly. The radius of the turn and the path of the airplane over the ground should be easily noted, and changes planned and effected as circumstances require. Drift should be easily discernible, but not tax the student too much in making corrections. Objects on the ground should appear in their proportion and size. The altitude should be low enough to render any gain or loss apparent to the student, but in no case lower than 500 feet above the highest obstruction. During these maneuvers, both the instructor and the student should be alert for available forced landing fields. The area chosen should be away from communities, livestock, or groups of people to prevent possible annoyance or hazards to others. Due to the altitudes at which these maneuvers are performed, there is little time available to search for a suitable field for landing in the event the need arises. Drift and ground track control. Whenever any object is free from the ground, it is affected by the medium with which it is surrounded. This means that a free object will move in whatever direction and speed that the medium moves. For example, if a powerboat is crossing a river and the river is still, the boat could head directly to a point on the opposite shore and travel on a straight course to that point without drifting. However, if the river were flowing swiftly, the water current would have to be considered. That is, as the boat progresses forward with its own power, it must also move upstream at the same rate the river is moving it downstream. This is accomplished by angling the boat upstream sufficiently to counteract the downstream flow. If this is done, the boat will follow the desired track across the river from the departure point directly to the intended destination point. Should the boat not be headed sufficiently upstream, it would drift with the current and run aground at some point downstream on the opposite bank. See Figure 6-1. As soon as an airplane becomes airborne, it is free of ground friction. Its path is then affected by the air mass in which it is flying. Therefore, the airplane, like the boat, will not always track along the ground in the exact direction that it is headed. When flying with the longitudinal axis of the airplane aligned with the road, it may be noted that the airplane gets closer to or farther from the road without any turn having been made. This would indicate that the air mass is moving sideward in relation to the airplane. Since the airplane is flying within this moving body of air, wind, it moves or drifts with the air in the same direction and speed, just like the boat moved with the river current. See Figure 6-1. When flying straight and level and following a selected ground track, the preferred method of correcting for wind drift is to head the airplane, wind correction angle, sufficiently into the wind to cause the airplane to move forward into the wind at the same rate the wind is moving it sideways. Depending on the wind velocity, this may require a large wind correction angle, or one of only a few degrees. When the drift has been neutralized, the airplane will follow the desired ground track. To understand the need for drift correction during flight, consider a flight with a wind velocity of 30 knots from the left and 90 degrees to the direction the airplane is headed. After 1 hour, the body of air in which the airplane is flying will have moved 30 nautical miles, nm, to the right. Since the airplane is moving with this body of air, it too will have drifted 30 nautical miles to the right. In relation to the air, the airplane moved forward, but in relation to the ground, it moved forward as well as 30 nautical miles to the right. There are times when the pilot needs to correct for drift while in a turn. See Figure 6-2. Throughout the turn, the wind will be acting on the airplane from constantly changing angles. The relative wind angle and speed govern the time it takes for the airplane to progress through any part of a turn. This is due to the constantly changing ground speed. When the airplane is headed into the wind, the ground speed is decreased. When headed downwind, the ground speed is increased. Through the crosswind portion of a turn, the airplane must be turned sufficiently into the wind to counteract drift. To follow a desired circular ground track, the wind correction angle must be varied in a timely manner because of the varying ground speed as a turn progresses. The faster the ground speed, the faster the wind correction angle must be established. The slower the ground speed, the slower the wind correction angle may be established. It can be seen, then, that the steepest bank and fastest rate of turn should be made on the downwind portion of the turn, and the shallowest bank and slowest rate of turn on the upwind portion. The principles and techniques of varying the angle of bank to change the rate of turn and wind correction angle for controlling wind drift during a turn are the same for all ground track maneuvers involving changes in direction of flight. When there is no wind, it should be simple to fly along a ground track with an arc of exactly 180 degrees and a constant radius, because the flight path and ground track would be identical. This can be demonstrated by approaching a road at a 90-degree angle, and, when directly over the road, rolling into a medium-banked turn, then maintaining the same angle of bank throughout the 180 degrees of turn. See Figure 6-2. To complete the turn, the rollout should be started at a point where the wings will become level, as the airplane again reaches the road at a 90-degree angle, and will be directly over the road just as the turn is completed. This would be possible only if there were absolutely no wind, and if the angle of bank and the rate of turn remained constant throughout the entire maneuver. If the turn were made with a constant angle of bank and a wind blowing directly across the road, it would result in a constant radius turn through the air. However, the wind effects would cause the ground track to be distorted from a constant radius turn or semicircular path. The greater the wind velocity, the greater would be the difference between the desired ground track and the flight path. To counteract this drift, the flight path can be controlled by the pilot in such a manner as to neutralize the effect of the wind and cause the ground track to be a constant radius semicircle. The effects of wind during turns can be demonstrated after selecting a road, railroad, or other ground reference that forms a straight line parallel to the wind. Fly into the wind directly over and along the line, and then make a turn with a constant medium angle of bank for 360 degrees of turn. See Figure 6-3. The airplane will return to a point directly over the line, but slightly downwind from the starting point, the amount depending on the wind velocity and the time required to complete the turn. The path over the ground will be an elongated circle, although in reference to the air it is a perfect circle. Straight flight during the upwind segment after completion of the turn is necessary to bring the airplane back to the starting position. A similar 360-degree turn may be started at a specific point over the reference line, with the airplane headed directly downwind. In this demonstration, the effect of wind during the constant bank turn will drift the airplane to a point where the line is re-intercepted, but the 360-degree turn will be completed at a point downwind from the starting point. Another reference line which lies directly crosswind may be selected and the same procedure repeated, showing that if wind drift is not corrected, the airplane will, at the completion of the 360-degree turn, be headed in the original direction, but will have drifted away from the line a distance dependent on the amount of wind. From these demonstrations, it can be seen where and why it is necessary to increase or decrease the angle of bank and the rate of turn to achieve a desired track over the ground. The principles and techniques involved can be practiced and evaluated by the performance of the ground track maneuvers discussed in this chapter. Rectangular course. Normally, the first ground reference maneuver the pilot is introduced to is the rectangular course. See Figure 6-4. The rectangular course is a training maneuver in which the ground track of the airplane is equidistant from all sides of a selected rectangular area on the ground. The maneuver simulates the conditions encountered in an airport traffic pattern. While performing the maneuver, the altitude and airspeed should be held constant. The maneuver assists the student pilot in perfecting practical application of the turn, the division of attention between the flight path, ground objects, and the handling of the airplane, the timing of the start of a turn so that the turn will be fully established at a definite point over the ground, the timing of the recovery from a turn so that a definite ground track will be maintained, the establishing of a ground track, and the determination of the appropriate crab angle. Like those of other ground track maneuvers, one of the objectives is to develop division of attention between the flight path and ground references, while controlling the airplane and watching for other aircraft in the vicinity. Another objective is to develop recognition of drift toward or away from a line parallel to the intended ground track. This will be helpful in recognizing drift toward or from an airport runway during the various legs of the airport traffic pattern. For this maneuver, a square or rectangular field, or an area bounded on four sides by section lines or roads, the sides of which are approximately a mile in length, should be selected well away from other air traffic. The airplane should be flown parallel to and at a uniform distance about 1/4 to 1/2 mile away from the field boundaries, not above the boundaries. For best results, the flight path should be positioned outside the field boundaries, just far enough that they may be easily observed from either pilot's seat by looking out the side of the airplane. If an attempt is made to fly directly above the edges of the field, the pilot will have no usable reference points to start and complete the turns. The closer the track of the airplane is to the field boundaries, the steeper the bank necessary at the turning points. Also, the pilot should be able to see the edges of the selected field while seated in a normal position and looking out the side of the airplane during either a left-hand or right-hand course. The distance of the ground track from the edges of the field should be the same regardless of whether the course is flown to the left or right. All turns should be started when the airplane is abeam the corner of the field boundaries, and the bank normally should not exceed 45 degrees. These should be the determining factors in establishing the distance from the boundaries for performing the maneuver. Although the rectangular course may be entered from any direction, this discussion assumes entry on a downwind. On the downwind leg, the wind is a tailwind and results in an increased ground speed. Consequently, the turn onto the next leg is entered with a fairly fast rate of roll-in with relatively steep bank. As the turn progresses, the bank angle is reduced gradually because the tailwind component is diminishing, resulting in a decreasing ground speed. During and after the turn onto this leg, the equivalent of the base leg in a traffic pattern, the wind will tend to drift the airplane away from the field boundary. To compensate for the drift, the amount of turn will be more than 90 degrees. The rollout from this turn must be such that as the wings become level, the airplane is turned slightly toward the field and into the wind to correct for drift. The airplane should again be the same distance from the field boundary and at the same altitude as on other legs. The base leg should be continued until the upwind leg boundary is being approached. Once more, the pilot should anticipate drift and turning radius. Since drift correction was held on the base leg, It is necessary to turn less than 90 degrees to align the airplane parallel to the upwind leg boundary. This turn should be started with a medium bank angle with a gradual reduction to a shallow bank as the turn progresses. The rollout should be timed to assure paralleling the boundary of the field as the wings become level. While the airplane is on the upwind leg, the next field boundary should be observed as it is being approached to plan the turn onto the crosswind leg. Since the wind is a headwind on this leg, it is reducing the airplane's ground speed, and during the turn onto the crosswind leg will try to drift the airplane toward the field. For this reason, the roll-in to the turn must be slow, and the bank relatively shallow to counteract this effect. As the turn progresses, the headwind component decreases, allowing the ground speed to increase. Consequently, the bank angle and rate of turn are increased gradually to assure that upon completion of the turn, the crosswind ground track will continue the same distance from the edge of the field. Completion of the turn with the wings level should be accomplished at a point aligned with the upwind corner of the field. Simultaneously, as the wings are rolled level, the proper drift correction is established with the airplane turned into the wind. This requires that the turn be less than a 90-degree change in heading. If the turn has been made properly, the field boundary will again appear to be 1/4 to 1/2 mile away. While on the crosswind leg, the wind correction angle should be adjusted as necessary to maintain a uniform distance from the field boundary. As the next field boundary is being approached, the pilot should plan the turn onto the downwind leg. Since a wind correction angle is being held into the wind and away from the field while on the crosswind leg, this next turn will require a turn of more than 90 degrees. Since the crosswind will become a tailwind, causing the ground speed to increase during this turn, the bank initially should be medium and progressively increased as the turn proceeds. To complete the turn, the rollout must be timed so that the wings become level at a point aligned with the crosswind corner of the field, just as the longitudinal axis of the airplane again becomes parallel to the field boundary. The distance from the field boundary should be the same as from the other sides of the field. Usually, drift should not be encountered on the upwind or the downwind leg, but it may be difficult to find a situation where the wind is blowing exactly parallel to the field boundaries. This would make it necessary to use a slight wind correction angle on all the legs. It is important to anticipate the turns to correct for ground speed, drift, and turning radius. When the wind is behind the airplane, the turn must be faster and steeper. When it is ahead of the airplane, the turn must be slower and shallower. These same techniques apply while flying in airport traffic patterns. Common errors in the performance of rectangular courses are failure to adequately clear the area, failure to establish proper altitude prior to entry, typically entering the maneuver while descending, failure to establish appropriate wind correction angle resulting in drift, gaining or losing altitude, poor coordination, typically skidding in turns from a downwind heading and slipping in turns from an upwind heading, abrupt control usage, inability to adequately divide attention between airplane control and maintaining ground track, improper timing in beginning and recovering from turns, inadequate visual lookout for other aircraft. End of Chapter 6, Part 1. Chapter 6, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook, Volume 1, by Federal Aviation Administration. Chapter 6, Ground Reference Maneuvers, Part 2, S-turns across a road. An S-turn across a road is a practice maneuver in which the airplane's ground track describes semicircles of equal radii on each side of a selected straight line on the ground. See Figure 6-5. The straight line may be a road, fence, railroad, or section line that lies perpendicular to the wind, and should be of sufficient length for making a series of turns. A constant altitude should be maintained throughout the maneuver. S-turns across a road present one of the most elementary problems in the practical application of the turn, and in the correction for wind drift in turns. While the application of this maneuver is considerably less advanced in some respects than the rectangular course, it is taught after the student has been introduced to that maneuver, in order that the student may have a knowledge of the correction for wind drift in straight flight along a reference line before the student attempt to correct for drift by playing a turn. The objectives of S-turns across a road are to develop the ability to compensate for drift during turns, orient the flight path with ground references, follow an assigned ground track, arrive at specified points on assigned headings, and divide the pilot's attention. The maneuver consists of crossing the road at a 90-degree angle and immediately beginning a series of 180-degree turns of uniform radius in opposite directions, recrossing the road at a 90-degree angle just as each 180-degree turn is completed. To accomplish a constant radius ground track requires a changing roll rate and angle of bank to establish the wind correction angle. Both will increase or decrease as ground speed increases or decreases. The bank must be steepest when beginning the turn on the downwind side of the road, and must be shallowed gradually as the turn progresses from a downwind heading to an upwind heading. On the upwind side, the turn should be started with a relatively shallow bank and then gradually steepened as the airplane turns from an upwind heading to a downwind heading. In this maneuver, the airplane should be rolled from one bank directly into the opposite, just as the reference line on the ground is crossed. Before starting the maneuver, a straight ground reference line or road that lies 90 degrees to the direction of the wind should be selected, then the area checked to ensure that no obstructions or other aircraft are in the immediate vicinity. The road should be approached from the upwind side, at the selected altitude on a downwind heading. When directly over the road, the first turn should be started immediately. With the airplane headed downwind, the ground speed is greatest, and the rate of departure from the road will be rapid, so the roll into the steep bank must be fairly rapid to attain the proper wind correction angle. This prevents the airplane from flying too far from the road and from establishing a ground track of excessive radius. During the latter portion of the first 90 degrees of turn, when the airplane's heading is changing from a downwind heading to a crosswind heading, the ground speed becomes less, and the rate of departure from the road decreases. The wind correction angle will be at the maximum when the airplane is headed directly crosswind. After turning 90 degrees, the airplane's heading becomes more and more an upwind heading. The ground speed will decrease, and the rate of closure with the road will become slower. If a constant steep bank were maintained, the airplane would turn too quickly for the slower rate of closure, and would be headed perpendicular to the road prematurely. Because of the decreasing ground speed and rate of closure while approaching the upwind heading, it will be necessary to gradually shallow the bank during the remaining 90 degrees of the semicircle, so that the wind correction angle is removed completely and the wings become level as the 180-degree turn is completed at the moment the road is reached. At the instant the road is being crossed again, a turn in the opposite direction should be started. Since the airplane is still flying into the headwind, the ground speed is relatively slow. Therefore, the turn will have to be started with a shallow bank, so as to avoid an excessive rate of turn that would establish the maximum wind correction angle too soon. The degree of bank should be that which is necessary to attain the proper wind correction angle, so the ground track describes an arc, the same size as the one established on the downwind side. Since the airplane is turning from an upwind to a downwind heading, the ground speed will increase, and after turning 90 degrees, the rate of closure with the road will increase rapidly. Consequently, the angle of bank and rate of turn must be progressively increased, so that the airplane will have turned 180 degrees at the time it reaches the road. Again, the rollout must be timed so the airplane is in straight and level flight directly over and perpendicular to the road. Throughout the maneuver, a constant altitude should be maintained, and the bank should be changing constantly to effect a true semicircular ground track. Often there is a tendency to increase the bank too rapidly during the initial part of the turn on the upwind side, which will prevent the completion of the 180-degree turn before recrossing the road. This is apparent when the turn is not completed in time for the airplane to cross the road at a perpendicular angle. To avoid this error, the pilot must visualize the desired half-circle ground track and increase the bank during the early part of this turn. During the latter part of the turn, when approaching the road, the pilot must judge the closure rate properly and increase the bank accordingly, so as to cross the road perpendicular to it just as the rollout is completed. Common errors in the performance of S-turns across a road are failure to adequately clear the area, poor coordination, gaining or losing altitude, inability to visualize the half-circle ground track, poor timing in beginning and recovering from turns, faulty correction for drift, inadequate visual lookout for other aircraft. Turns around a point. Turns around a point as a training maneuver is a logical extension of the principles involved in the performance of S-turns across a road. Its purposes as a training maneuver are to further perfect turning technique, to perfect the ability to subconsciously control the airplane while dividing attention between the flight path and ground references, to teach the student that the radius of a turn is a distance which is affected by the degree of bank used when turning with relation to a definite object, to develop a keen perception of altitude, to perfect the ability to correct for wind drift while in turns. In turns around a point, the airplane is flown in 2 or more complete circles of uniform radii or distance from a prominent ground reference point, using a maximum bank of approximately 45 degrees while maintaining a constant altitude. The factors and principles of drift correction that are involved in S-turns are also applicable in this maneuver. As in other ground track maneuvers, a constant radius around a point will, if any wind exists, require a constantly changing angle of bank and angles of wind correction. The closer the airplane is to a direct downwind heading where the ground speed is greatest, the steeper the bank and the faster the rate of turn required to establish the proper wind correction angle. The more nearly it is to a direct upwind heading where the ground speed is least, the shallower the bank and the slower the rate of turn required to establish the proper wind correction angle. It follows, then, that throughout the maneuver the bank and rate of turn must be gradually varied in proportion to the ground speed. The point selected for turns around a point should be prominent, easily distinguished by the pilot, and yet small enough to present precise reference. See Figure 6-6. Isolated trees, crossroads, or other similar small landmarks are usually suitable. To enter turns around a point, the airplane should be flown on a downwind heading to one side of the selected point at a distance equal to the desired radius of turn. In a high-wing airplane, the distance from the point must permit the pilot to see the point throughout the maneuver, even with the wing lowered in a bank. If the radius is too large, the lowered wing will block the pilot's view of the point. When any significant wind exists, it will be necessary to roll into the initial bank at a rapid rate so that the steepest bank is attained abeam of the point when the airplane is headed directly downwind. By entering the maneuver while heading directly downwind, the steepest bank can be attained immediately. Thus, if a maximum bank of 45 degrees is desired, the initial bank will be 45 degrees if the airplane is at the correct distance from the point. Thereafter, the bank is shallowed gradually until the point is reached where the airplane is headed directly upwind. At this point, the bank should be gradually steepened until the steepest bank is again attained when heading downwind at the initial point of entry. Just as S-turns require that the airplane be turned into the wind in addition to varying the bank, so do turns around a point. During the downwind half of the circle, the airplane's nose is progressively turned toward the inside of the circle. During the upwind half, the nose is progressively turned toward the outside. The downwind half of the turn around the point may be compared to the downwind side of the S-turn across a road. The upwind half of the turn around a point may be compared to the upwind side of the S-turn across a road. As the pilot becomes experienced in performing turns around a point and has a good understanding of the effects of wind drift and varying of the bank angle and wind correction angle as required, entry into the maneuver may be from any point. When entering the maneuver at a point other than downwind, however, the radius of the turn should be carefully selected, taking into account the wind velocity and ground speed, so that an excessive bank is not required later on to maintain the proper ground track. The flight instructor should place particular emphasis on the effect of an incorrect initial bank. This emphasis should continue in the performance of elementary eights. Common errors in the performance of turns around a point are failure to adequately clear the area, failure to establish appropriate bank on entry, failure to recognize wind drift. Excessive bank and/or inadequate wind correction angle on the downwind side of the circle, resulting in drift towards the reference point. Inadequate bank angle and/or excessive wind correction angle on the upwind side of the circle, resulting in drift away from the reference point. Skidding turns when turning from downwind to crosswind. Slipping turns when turning from upwind to crosswind. Gaining or losing altitude. Inadequate visual lookout for other aircraft. Inability to direct attention outside the airplane while maintaining precise airplane control. End of Chapter 6, Part 2. Chapter 6, Part 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Airplane Flying Handbook, Volume 1, by Federal Aviation Administration. Chapter 6, Ground Reference Maneuvers, Part 3, Elementary Eights. An eight is a maneuver in which the airplane describes a path over the ground more or less in the shape of a figure 8. In all eights except lazy eights, the path is horizontal as though following a marked path over the ground. There are various types of eights, progressing from the elementary types to very difficult types in the advanced maneuvers. Each has its special use in teaching the student to solve a particular problem of turning with relation to the Earth or an object on the Earth's surface. Each type, as they advance in difficulty of accomplishment, further perfects the student's coordination technique and requires a higher degree of subconscious flying ability. Of all the training maneuvers available to the instructor, only eights require the progressively higher degree of conscious attention to outside objects. However, the real importance of eights is in the requirement for the perfection and display of subconscious flying. Elementary eights, specifically eights along a road, eights across a road, and eights around pylons, are variations of turns around a point, which use 2 points about which the airplane circles in either direction. Elementary eights are designed for the following purposes: to perfect turning technique, to develop the ability to divide attention between the actual handling of controls and an outside objective, to perfect the knowledge of the effect of angle of bank on radius of turn, to demonstrate how wind affects the path of the airplane over the ground, to gain experience in the visualization of the results of planning before the execution of the maneuver, to train the student to think and plan ahead of the airplane. Eights along a road. An eight along a road is a maneuver in which the ground track consists of 2 complete adjacent circles of equal radii on each side of a straight road or other reference line on the ground. The ground track resembles a figure 8. See Figure 6-7. Like the other ground reference maneuvers, its objective is to develop division of attention, while compensating for drift, maintaining orientation with ground references, and maintaining a constant altitude. Although eights along a road may be performed with the wind blowing parallel to the road or directly across the road, for simplification purposes, only the latter situation is explained, since the principles involved in either case are common. A reference line or road which is perpendicular to the wind should be selected and the airplane flown parallel to and directly above the road. Since the wind is blowing across the flight path, the airplane will require some wind correction angle to stay directly above the road during the initial straight and level portion. Before starting the maneuver, the area should be checked to ensure clearance of obstructions and avoidance of other aircraft. Usually, the first turn should be made toward a downwind heading starting with a medium bank. Since the airplane will be turning more and more directly downwind, the ground speed will be gradually increasing, and the rate of departing the road will tend to become faster. Thus, the bank and rate of turn is increased to establish a wind correction angle to keep the airplane from exceeding the desired distance from the road when 180 degrees of change in direction is completed. The steepest bank is attained when the airplane is headed directly downwind. As the airplane completes 180 degrees of change in direction, it will be flying parallel to and using a wind correction angle toward the road, with the wind acting directly perpendicular to the ground track. At this point, the pilot should visualize the remaining 180 degrees of ground track required to return to the same place over the road from which the maneuver started. While the turn is continued toward an upwind heading, the wind will tend to keep the airplane from reaching the road with a decrease in ground speed and rate of closure. The rate of turn and wind correction angle are decreased proportionately so that the road will be reached just as the 360-degree turn is completed. To accomplish this, the bank is decreased so that when headed directly upwind, it will be at the shallowest angle. In the last 90 degrees of the turn, the bank may be varied to correct any previous errors in judging the returning rate and closure rate. The rollout should be timed so that the airplane will be straight and level over the starting point, with enough drift correction to hold it over the road. After momentarily flying straight and level along the road, the airplane is then rolled into a medium bank turn in the opposite direction to begin the circle on the upwind side of the road. The wind will still be decreasing the ground speed and trying to drift the airplane back toward the road. Therefore, the bank must be decreased slowly during the first 90-degree change in direction in order to reach the desired distance from the road and attain the proper wind correction angle when 180-degree change in direction has been completed. As the remaining 180 degrees of turn continues, the wind becomes more of a tailwind and increases the airplane's ground speed. This causes the rate of closure to become faster. Consequently, the angle of bank and rate of turn must be increased further to attain sufficient wind correction angle to keep the airplane from approaching the road too rapidly. The bank will be at its steepest angle when the airplane is headed directly downwind. In the last 90 degrees of the turn, the rate of turn should be reduced to bring the airplane over the starting point on the road. The rollout must be timed so the airplane will be straight and level, turned into the wind, and flying parallel to and over the road. The measure of a student's progress in the performance of eights along a road is the smoothness and accuracy of the change in bank used to counteract drift. The sooner the drift is detected and correction applied, the smaller will be the required changes. The more quickly the student can anticipate the corrections needed, the less obvious the changes will be, and the more attention can be diverted to the maintenance of altitude and operation of the airplane. Errors in coordination must be eliminated and a constant altitude maintained. Flying technique must not be allowed to suffer from the fact that the student's attention is diverted. This technique should improve as the student becomes able to divide attention between the operation of the airplane controls and following a designated flight path. Eights across a road. This maneuver is a variation of eights along a road and involves the same principles and techniques. The primary difference is that, at the completion of each loop of the figure 8, the airplane should cross an intersection of roads or a specific point on a straight road. See figure 6-8. The loops should be across the road, and the wind should be perpendicular to the road. Each time the road is crossed, the crossing angle should be the same, and the wings of the airplane should be level. The eights also may be performed by rolling from one bank immediately to the other, directly over the road. Eights around pylons. This training maneuver is an application of the same principles and techniques of correcting for wind drift as used in turns around a point, and the same objectives as other ground track maneuvers. In this case, 2 points or pylons on the ground are used as references, and turns around each pylon are made in opposite directions to follow a ground track in the form of a figure 8. See figure 6-9. The pattern involves flying downwind between the pylons and upwind outside of the pylons. It may include a short period of straight and level flight while proceeding diagonally from one pylon to the other. The pylons selected should be on a line 90 degrees to the direction of the wind, and should be in an area away from communities, livestock, or groups of people, to avoid possible annoyance or hazards to others. The area selected should be clear of hazardous obstructions and other air traffic. Throughout the maneuver, a constant altitude of at least 500 feet above the ground should be maintained. The 8 should be started with the airplane on a downwind heading when passing between the pylons. The distance between the pylons and the wind velocity will determine the initial angle of bank required to maintain a constant radius from the pylons during each turn. The steepest banks will be necessary just after each turn entry and just before the rollout from each turn where the airplane is headed downwind and the ground speed is greatest. The shallowest banks will be when the airplane is headed directly upwind and the ground speed is least. The rate of bank change will depend on the wind velocity, the same as it does in S-turns and turns around a point, and the bank will be changing continuously during the turns. The adjustment of the bank angle should be gradual, from the steepest bank to the shallowest bank, as the airplane progressively heads into the wind, followed by a gradual increase until the steepest bank is again reached just prior to rollout. If the airplane is to proceed diagonally from one turn to the other, the rollout from each turn must be completed on the proper heading with sufficient wind correction angle to ensure that after brief straight and level flight, the airplane will arrive at the point where a turn of the same radius can be made around the other pylon. The straight and level flight segments must be tangent to both circular patterns. Common errors in the performance of elementary 8s are failure to adequately clear the area, poor choice of ground reference points, improper maneuver entry considering wind direction and ground reference points, incorrect initial bank, poor coordination during turns, gaining or losing altitude, loss of orientation, abrupt rather than smooth changes in bank angle to counteract wind drift in turns, failure to anticipate needed drift correction, failure to apply needed drift correction in a timely manner, failure to roll out of turns on proper heading, inability to divide attention between reference points on the ground, airplane control, and scanning for other aircraft. 8s on pylons. Pylon 8s. The Pylon 8 is the most advanced and most difficult of the low-altitude flight training maneuvers. Because of the various techniques involved, the Pylon 8 is unsurpassed for teaching, developing, and testing subconscious control of the airplane. As the Pylon 8 is essentially an advanced maneuver in which the pilot's attention is directed at maintaining a pivotal position on a selected pylon, with a minimum of attention within the cockpit, it should not be introduced until the instructor is assured that the student has a complete grasp of the fundamentals. Thus, the prerequisites are the ability to make a coordinated turn without gain or loss of altitude, excellent feel of the airplane, stall recognition, relaxation with low-altitude maneuvering, and an absence of the error of over-concentration. Like 8s around pylons, this training maneuver also involves flying the airplane in circular paths, alternately left and right, in the form of a figure 8 around two selected points or pylons on the ground. Unlike 8s around pylons, however, no attempt is made to maintain a uniform distance from the pylon. In 8s on pylons, the distance from the pylons varies if there is any wind. Instead, the airplane is flown at such a precise altitude and airspeed that a line parallel to the airplane's lateral axis and extending from the pilot's eye appears to pivot on each of the pylons. See Figure 6-10. Also, unlike 8s around pylons, in the performance of 8s on pylons, the degree of bank increases as the distance from the pylon decreases. The altitude that is appropriate for the airplane being flown is called the pivotal altitude and is governed by the ground speed. While not truly a ground track maneuver, as were the preceding maneuvers, the objective is similar: to develop the ability to maneuver the airplane accurately while dividing one's attention between the flight path and the selected points on the ground. In explaining the performance of 8s on pylons, the term wingtip is frequently considered as being synonymous with the proper reference line, or pivot point on the airplane. This interpretation is not always correct. High wing, low wing, swept wing, and tapered wing airplanes, as well as those with tandem or side-by-side seating, will all present different angles from the pilot's eye to the wingtip. See Figure 6-11. Therefore, in the correct performance of 8s on pylons, as in other maneuvers requiring a lateral reference, the pilot should use a sighting reference line that, from eye level, parallels the lateral axis of the airplane. The sighting point or line, while not necessarily on the wingtip itself, may be positioned in relation to the wingtip, ahead, behind, above, or below, but even then it will differ for each pilot, and from each seat in the airplane. This is especially true in tandem, fore and aft seat airplanes. In side-by-side type airplanes, there will be very little variation in the sighting lines for different persons if those persons are seated so that the eyes of each are at approximately the same level. An explanation of the pivotal altitude is also essential. There is a specific altitude at which, when the airplane turns at a given ground speed, a projection of the sighting reference line to the selected point on the ground will appear to pivot on that point. Since different airplanes fly at different airspeeds, the ground speed will be different. Therefore, each airplane will have its own pivotal altitude. See Figure 6-12. The pivotal altitude does not vary with the angle of bank being used unless the bank is steep enough to affect the ground speed. A rule of thumb for estimating pivotal altitude in calm wind is to square the true airspeed and divide by 15 for miles per hour, mph, or 11.3 for knots. Distance from the pylon affects the angle of bank. At any altitude above that pivotal altitude, the projected reference line will appear to move rearward in a circular path in relation to the pylon. Conversely, when the airplane is below the pivotal altitude, the projected reference line will appear to move forward in a circular path. See Figure 6-13. To demonstrate this, the airplane is flown at normal cruising speed and at an altitude estimated to be below the proper pivotal altitude, and then placed in a medium banked turn. It will be seen that the projected reference line of sight appears to move forward along the ground. Pylon moves back as the airplane turns. A climb is then made to an altitude well above the pivotal altitude, and when the airplane is again at normal cruising speed, it is placed in a medium banked turn. At this higher altitude, the projected reference line of sight now appears to move backward across the ground. Pylon moves forward in a direction opposite that of flight. After the high altitude extreme has been demonstrated, the power is reduced, and a descent at cruising speed begun in a continuing medium bank around the pylon. The apparent backward travel of the projected reference line with respect to the pylon will slow down as altitude is lost, stop for an instant, then start to reverse itself, and would move forward if the descent were allowed to continue below the pivotal altitude. The altitude at which the line of sight apparently ceased to move across the ground was the pivotal altitude. If the airplane descended below the pivotal altitude, power should be added to maintain airspeed while altitude is regained to the point at which the projected reference line moves neither backward nor forward, but actually pivots on the pylon. In this way, the pilot can determine the pivotal altitude of the airplane. The pivotal altitude is critical and will change with variations in ground speed. Since the headings throughout the turn continually vary from directly downwind to directly upwind, the ground speed will constantly change. This will result in the proper pivotal altitude varying slightly throughout the 8. Therefore, adjustment is made for this by climbing or descending as necessary to hold the reference line or point on the pylons. This change in altitude will be dependent on how much the wind affects the ground speed. The instructor should emphasize that the elevators are the primary control for holding the pylons. Even a very slight variation in altitude affects a double correction, since in losing altitude, speed is gained, and even a slight climb reduces the airspeed. This variation in altitude, although important in holding the pylon, in most cases will be so slight as to be barely perceptible on a sensitive altimeter. Before beginning the maneuver, the pilot should select 2 points on the ground along a line which lies 90 degrees to the direction of the wind. The area in which the maneuver is to be performed should be checked for obstructions and any other air traffic, and it should be located where a disturbance to groups of people, livestock, or communities will not result. The selection of proper pylons is of importance to good 8's-on pylons. They should be sufficiently prominent to be readily seen by the pilot when completing the turn around one pylon and heading for the next, and should be adequately spaced to provide time for planning the turns and yet not cause unnecessary straight and level flight between the pylons. The selected pylons should also be at the same elevation, since differences of over a very few feet will necessitate climbing or descending between each turn. For uniformity, the 8 is usually begun by flying diagonally crosswind between the pylons to a point downwind from the first pylon, so that the first turn can be made into the wind. As the airplane approaches a position where the pylon appears to be just ahead of the wingtip, the turn should be started by lowering the upwind wing to place the pilot's line of sight reference on the pylon. As the turn is continued, the line of sight reference can be held on the pylon by gradually increasing the bank. The reference line should appear to pivot on the pylon. As the airplane heads into the wind, the ground speed decreases. Consequently, the pivotal altitude is lower, and the airplane must descend to hold the reference line on the pylon. As the turn progresses on the upwind side of the pylon, the wind becomes more of a crosswind. Since a constant distance from the pylon is not required on this maneuver, no correction to counteract drifting should be applied during the turns. If the reference line appears to move ahead of the pylon, the pilot should increase altitude. If the reference line appears to move behind the pylon, the pilot should decrease altitude. Varying rudder pressure to yaw the airplane and force the wing and reference line forward or backward to the pylon is a dangerous technique and must not be attempted. As the airplane turns toward a downwind heading, the rollout from the turn should be started to allow the airplane to proceed diagonally to a point on the downwind side of the second pylon. The rollout must be completed in the proper wind correction angle to correct for wind drift, so that the airplane will arrive at a point downwind from the second pylon the same distance it was from the first pylon at the beginning of the maneuver. Upon reaching that point, a turn is started in the opposite direction by lowering the upwind wing to again place the pilot's line of sight reference on the pylon. The turn is then continued just as in the turn around the first pylon, but in the opposite direction. With prompt correction and a very fine control touch, it should be possible to hold the projection of the reference line directly on the pylon, even in a stiff wind. Corrections for temporary variations, such as those caused by gusts or inattention, may be made by shallowing the bank to fly relatively straight to bring forward a lagging wing, or by steepening the bank temporarily to turn back a wing which has crept ahead. With practice, these corrections will become so slight as to be barely noticeable. These variations are apparent from the movement of the wingtips long before they are discernible on the altimeter. Pylon 8s are performed at bank angles ranging from shallow to steep. See Figure 6-14. The student should understand that the bank chosen will not alter the pivotal altitude. As proficiency is gained, the instructor should increase the complexity of the maneuver by directing the student to enter at a distance from the pylon that will result in a specific bank angle at the steepest point in the pylon turn. The most common error in attempting to hold a pylon is incorrect use of the rudder. When the projection of the reference line moves forward with respect to the pylon, many pilots will tend to press the inside rudder to yaw the wing backward. When the reference line moves behind the pylon, they will press the outside rudder to yaw the wing forward. The rudder is to be used only as a coordination control. Other common errors in the performance of 8s on pylons, Pylon 8s, are failure to adequately clear the area, skidding or slipping in turns, whether trying to hold the pylon with rudder or not, excessive gain or loss of altitude, over-concentration on the pylon, and failure to observe traffic, poor choice of pylons, not entering the pylon turns into the wind, failure to assume a heading when flying between pylons that will compensate sufficiently for drift, failure to time the bank so that the turn entry is completed with the pylon in position, abrupt control usage, inability to select pivotal altitude. End of Chapter 6, Part 3.
Chapter 7 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1, by the Federal Aviation Administration. Airport Traffic Patterns. Airport traffic patterns and operations. Just as roads and streets are needed in order to utilize automobiles, airports or airstrips are needed to utilize airplanes. Every flight begins and ends at an airport or other suitable landing field. For that reason, it is essential that the pilot learn the traffic rules, traffic procedures, and traffic pattern layouts that may be in use at various airports. When an automobile is driven on congested city streets, it can be brought to a stop to give way to conflicting traffic. However, an airplane can only be slowed down. Consequently, specific traffic patterns and traffic control procedures have been established at designated airports. The traffic patterns provide specific routes for takeoffs, departures, arrivals, and landings. The exact nature of each airport traffic pattern is dependent on the runway in use, wind conditions, obstructions, and other factors. Control towers and radar facilities provide a means of adjusting the flow of arriving and departing aircraft and render assistance to pilots in busy terminal areas. Airport lighting and runway marking systems are used frequently to alert pilots to abnormal conditions and hazards so arrivals and departures can be made safely. Airports vary in complexity from small grass or sod strips to major terminals having many paved runways and taxiways. Regardless of the type of airport, the pilot must know and abide by the rules and general operating procedures applicable to the airport being used. These rules and procedures are based not only on logic or common sense, but also on courtesy, and their objective is to keep air traffic moving with maximum safety and efficiency. The use of any traffic pattern, service, or procedure does not alter the responsibility of pilots to see and avoid other aircraft. Standard airport traffic patterns. To assure that air traffic flows into and out of an airport in an orderly manner, an airport traffic pattern is established appropriate to the local conditions, including the direction and placement of the pattern, the altitude to be flown, and the procedures for entering and leaving the pattern. Unless the airport displays approved visual markings indicating that turns should be made to the right, the pilot should make all turns in the pattern to the left. When operating at an airport with an operating control tower, the pilot receives by radio a clearance to approach or depart, as well as pertinent information about the traffic pattern. If there is not a control tower, it is the pilot's responsibility to determine the direction of the traffic pattern, to comply with the appropriate traffic rules, and to display common courtesy toward other pilots operating in the area. The pilot is not expected to have extensive knowledge of all traffic patterns at all airports, but if the pilot is familiar with the basic rectangular pattern, it will be easy to make proper approaches and departures from most airports, regardless of whether they have control towers. At airports with operating control towers, the tower operator may instruct pilots to enter the traffic pattern at any point or to make a straight-in approach without flying the usual rectangular pattern. Many other deviations are possible if the tower operator and the pilot work together in an effort to keep traffic moving smoothly. Jets or heavy airplanes will frequently be flying wider and/or higher patterns than lighter airplanes, and in many cases will make a straight-in approach for landing. Compliance with the basic rectangular traffic pattern reduces the possibility of conflicts at airports without an operating control tower. It is imperative that the pilot form the habit of exercising constant vigilance in the vicinity of airports, even though the air traffic appears to be light. The standard rectangular traffic pattern is illustrated in Figure 7-1 on next page. The traffic pattern altitude is usually 1,000 feet above the elevation of the airport surface. The use of a common altitude at a given airport is the key factor in minimizing the risk of collisions at airports without operating control towers. It is recommended that while operating in the traffic pattern at an airport without an operating control tower, the pilot maintain an airspeed that conforms with the limits established by Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, for such an airport. No more than 200 knots, 230 miles per hour, mph. In any case, the speed should be adjusted, when practicable, so that it is compatible with the speed of other airplanes in the pattern. When entering the traffic pattern at an airport without an operating control tower, inbound pilots are expected to observe other aircraft already in the pattern and to conform to the traffic pattern in use. If other aircraft are not in the pattern, then traffic indicators on the ground and wind indicators must be checked to determine which runway and traffic pattern direction should be used. See Figure 7-2. Many airports have L-shaped traffic pattern indicators displayed with a segmented circle adjacent to the runway. The short member of the L shows the direction in which the traffic pattern turns should be made when using the runway parallel to the long member. These indicators should be checked while at a distance well away from any pattern that might be in use, or while at a safe height well above generally used pattern altitudes. When the proper traffic pattern direction has been determined, The pilot should then proceed to a point well clear of the pattern before descending to the pattern altitude. When approaching an airport for landing, the traffic pattern should be entered at a 45-degree angle to the downwind leg, headed toward a point abeam of the midpoint of the runway to be used for landing. Arriving airplanes should be at the proper traffic pattern altitude before entering the pattern, and should stay clear of the traffic flow until established on the entry leg. Entries into traffic patterns while descending create specific collision hazards and should always be avoided. The entry leg should be of sufficient length to provide a clear view of the entire traffic pattern and to allow the pilot adequate time for planning the intended path in the pattern and the landing approach. The downwind leg is a course flown parallel to the landing runway, but in a direction opposite to the intended landing direction. This leg should be approximately half to 1 mile out from the landing runway and at the specific traffic pattern altitude. During this leg, the before landing check should be completed and the landing gear extended if retractable. Pattern altitude should be maintained until abeam the approach end of the landing runway. At this point, power should be reduced and a descent begun. The downwind leg continues past a point abeam the approach end of the runway to a point approximately 45 degrees from the approach end of the runway, and a medium bank turn is made onto the base leg. The base leg is the transitional part of the traffic pattern between the downwind leg and the final approach leg. Depending on the wind condition, it is established at a sufficient distance from the approach end of the landing runway to permit a gradual descent to the intended touchdown point. The ground track of the airplane while on the base leg should be perpendicular to the extended center line of the landing runway, although the longitudinal axis of the airplane may not be aligned with the ground track when it is necessary to turn into the wind to counteract drift. While on the base leg, the pilot must ensure before turning onto the final approach that there is no danger of colliding with another aircraft that may be already on the final approach. The final approach leg is a descending flight path starting from the completion of the base to final turn and extending to the point of touchdown. This is probably the most important leg of the entire pattern, because here the pilot's judgment and procedures must be the sharpest to accurately control the airspeed and descent angle while approaching the intended touchdown point. As stipulated in 14 CFR Part 91, aircraft while on final approach to land or while landing have the right of way over other aircraft in flight or operating on the surface. When 2 or more aircraft are approaching an airport for the purpose of landing, the aircraft at the lower altitude has the right of way. Pilots should not take advantage of this rule to cut in front of another aircraft that is on final approach to land or to overtake that aircraft. The upwind leg is a course flown parallel to the landing runway, but in the same direction to the intended landing direction. The upwind leg continues past a point abeam of the departure end of the runway to where a medium bank 90-degree turn is made onto the crosswind leg. The upwind leg is also the transitional part of the traffic pattern when on the final approach, and a go-around is initiated and climb attitude is established. When a safe altitude is attained, the pilot should commence a shallow bank turn to the upwind side of the airport. This will allow better visibility of the runway for departing aircraft. The departure leg of the rectangular pattern is a straight course aligned with and leading from the takeoff runway. This leg begins at the point the airplane leaves the ground and continues until the 90-degree turn onto the crosswind leg is started. On the departure leg after takeoff, the pilot should continue climbing straight ahead and, if remaining in the traffic pattern, commence a turn to the crosswind leg beyond the departure end of the runway within 300 feet of pattern altitude. If departing the traffic pattern, continue straight out or exit with a 45-degree turn, to the left when in a left-hand traffic pattern, to the right when in a right-hand traffic pattern, beyond the departure end of the runway after reaching pattern altitude. The crosswind leg is the part of the rectangular pattern that is horizontally perpendicular to the extended center line of the takeoff runway and is entered by making approximately a 90-degree turn from the upwind leg. On the crosswind leg, the airplane proceeds to the downwind leg position. Since in most cases the takeoff is made into the wind will now be approximately perpendicular to the airplane's flight path. As a result, the airplane will have to be turned or headed slightly into the wind while on the crosswind leg to maintain a ground track that is perpendicular to the runway centerline extension. Additional information on airport operations can be found in the Aeronautical Information Manual, AIM. End of Chapter 7. Chapter 8, Part 1 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Approaches and Landings, Part 1. Normal Approach and Landing. A normal approach and landing involves the use of procedures for what is considered a normal situation. That is, when engine power is available, the wind is light, or the final approach is made directly into the wind. The final approach path has no obstacles, and the landing surface is firm and of ample length to gradually bring the airplane to a stop. The selected landing point should be beyond the runway's approach threshold, but within the first one-third portion of the runway. The factors involved and the procedures described for the normal approach and landing also have applications to the other than normal approaches and landings which are discussed later in this chapter. This being the case, the principles of normal operations are explained first and must be understood before proceeding to the more complex operations. So that the pilot may better understand the factors that will influence judgment and procedures, that last part of the approach pattern and the actual landing will be divided into 5 phases: the base leg, the final approach, the round out, the touchdown, and the after landing roll. It must be remembered that the manufacturer's recommended procedures, including airplane configuration and airspeeds, and other information relevant to approaches and landings in a specific make and model airplane, are contained in the FAA-approved Airplane Flight Manual and/or Pilot's Operating Handbook, AFM-POH, for that airplane. If any of the information in this chapter differs from the airplane manufacturer's recommendations as contained in the AFM-POH, the airplane manufacturer's recommendations take precedence. Base leg. The placement of the base leg is one of the more important judgments made by the pilot in any landing approach. See Figure 8-1. The pilot must accurately judge the altitude and distance from which a gradual descent will result in landing at the desired spot. The distance will depend on the altitude of the base leg, the effect of wind, and the amount of wing flaps used. When there is a strong wind on final approach, or the flaps will be used to produce a steep angle of descent, the base leg must be positioned closer to the approach end of the runway than would be required with a light wind or no flaps. Normally, the landing gear should be extended and the before landing check completed prior to reaching the base leg. After turning onto the base leg, the pilot should start the descent with reduced power and airspeed of approximately 1.4 VSO. VSO, the stalling speed with power off, landing gears, and flaps down. For example, if VSO is 60 knots, the speed should be 1.4 times 60, or 84 knots. Landing flaps may be partially lowered, if desired at this time. Full flaps are not recommended until the final approach is established. Drift correction should be established and maintained to follow a ground track perpendicular to the extension of the center line of the runway on which the landing is to be made. Since the final approach and landing will normally be made into the wind, there will be somewhat of a crosswind during the base leg. This requires that the airplane be angled sufficiently into the wind to prevent drifting farther away from the intended landing spot. The base leg should be continued to the point where a medium to shallow bank turn will align the airplane's path directly with the center line of the landing runway. This descending turn should be completed at a safe altitude that will be dependent upon the height of the terrain and any obstructions along the ground track. The turn to the final approach should also be sufficiently above the airport elevation to permit a final approach long enough for the pilot to accurately estimate the resultant point of touchdown while maintaining the proper approach airspeed. This will require careful planning as to the starting point and the radius of the turn. Normally, it is recommended that the angle of bank not exceed a medium bank, because the steeper the angle of bank, the higher the airspeed at which the airplane stalls. Since the base to final turn is made at a relatively low altitude, it is important that a stall not occur at this point. If an extremely steep bank is needed to prevent overshooting the proper final approach path, it is advisable to discontinue the approach, go around, and plan to start the turn earlier on the next approach rather than risk a hazardous situation. Final approach. After the base to final approach turn is completed, the longitudinal axis of the plane should be aligned with the center line of the runway or landing surface, so that drift, if any, will be recognized immediately. On a normal approach with no wind drift, the longitudinal axis should be kept aligned with the runway centerline throughout the approach and landing. The proper way to correct for a crosswind will be explained under the section Crosswind Approach and Landing. For now, only an approach and landing where the wind is straight down the runway will be discussed. After aligning the airplane with the runway centerline, the final flap setting should be completed and the pitch attitude adjusted as required for the desired rate of descent. Slight adjustments in pitch and power may be necessary to maintain the descent attitude and the desired approach airspeed. In the absence of the manufacturer's recommended airspeed, a speed equal to 1.3 VSO should be used. If VSO is 60 knots, the speed should be 78 knots. When the pitch attitude and airspeed have been stabilized, the airplane should be retrimmed to relieve the pressure being held on the controls. The descent angle should be controlled throughout the approach so that the airplane will land in the center of the first third of the runway. The descent angle is affected by all four fundamental forces that act on an airplane: lift, drag, thrust, and weight. If all the forces are constant, the descent angle will be constant in a no-wind condition. The pilot can control these forces by adjusting the airspeed, attitude, power, and drag, flaps, or forward slip. The wind also plays a prominent part in the gliding distance over the ground. See Figure 8-2. Naturally, the pilot does not have control over the wind, but may correct for its effect on the airplane's descent by appropriate pitch and power adjustments. Considering the factors that affect the descent angle on the final approach, for all practical purposes, at a given pitch attitude, there is only one power setting for one airspeed, one flap setting, and one wind condition. A change in any one of these variables will require an appropriate coordinated change in the other controllable variables. For example, if the pitch attitude is raised too high without an increase of power, the airplane will settle very rapidly and touch down short of the desired spot. For this reason, the pilot should never try to stretch a glide by applying back elevator pressure alone to reach the desired landing spot. This will shorten the gliding distance if power is not added simultaneously. The proper angle of descent and airspeed should be maintained by coordinating pitch attitude changes and power changes. The objective of a good final approach is to descend at an angle and airspeed that will permit the airplane to reach the desired touchdown point at an airspeed which will result in minimum floating just before touchdown. In essence, a semi-stalled condition. To accomplish this, it is essential that both the descent angle and the airspeed be accurately controlled. Since on a normal approach the power setting is not fixed as in a power-off approach, the power and pitch attitude should be adjusted simultaneously as necessary to control the airspeed and the descent angle or to attain the desired altitudes along the approach path. By lowering the nose and reducing power to keep approach airspeed constant, a descent at a higher rate can be made to correct for being too high in the approach. This is one reason for performing approaches with partial power. If the approach is too high, merely lower the nose and reduce the power. When the approach is too low, add power and raise the nose. Use of flaps. The lift-drag factors may also be varied by the pilot to adjust the descent through the use of landing flaps. See Figure 8-3 and 8-4. Flap extension during landings provides several advantages by producing greater lift and permitting lower landing speed, producing greater drag, permitting a steep descent angle without airspeed increase, reducing the length of the landing roll. Flap extension has a definite effect on the airplane's pitch behavior. The increased camber from flap deflection produces lift primarily on the rear portion of the wing. This produces a nose-down pitching moment. However, the change in tail loads from the downwash deflected by the flaps over the horizontal tail has a significant influence on the pitching moment. Consequently, pitch behavior depends on the design features of the particular airplane. Flap deflection of up to 15 degrees primarily produces lift with minimal drag. The airplane has a tendency to balloon up with initial flap deflection because of the lift increase. The nose-down pitching moment, however, tends to offset the balloon. Flap deflection beyond 15 degrees produces a large increase in drag. Also, deflection beyond 15 degrees produces a significant nose-up pitching moment in high-wing airplanes because the resulting downwash increases the airflow over the horizontal tail. The time of flap extension and the degree of deflection are related. Large flap deflections at one single point in the landing pattern produce large lift changes that require significant pitch and power changes in order to maintain airspeed and descent angle. Consequently, the deflection of flaps at certain positions in the landing pattern has definite advantages. Incremental deflection of flaps on downwind, base leg, and final approach allows smaller adjustment of pitch and power compared to extension of full flaps all at one time. When the flaps are lowered, the airspeed will decrease unless the power is increased or the pitch attitude lowered. On final approach, therefore, the pilot must estimate where the airplane will land through discerning judgment of the descent angle. If it appears that the airplane is going to overshoot the desired landing spot, more flaps may be used if not fully extended, or the power reduced further and the pitch attitude lowered. This will result in a steeper approach. If the desired landing spot is being undershot and a shallower approach is needed, both power and pitch attitude should be increased to readjust the descent angle. Never retract the flaps to correct for undershooting, since that will suddenly decrease the lift and cause the airplane to sink even more rapidly. The airplane must be retrimmed on the final approach to compensate for the change in aerodynamic forces. With the reduced power and with a slower airspeed, the airflow produces less lift on the wings and less downward force on the horizontal stabilizer, resulting in a significant nose-down tendency. The elevator must then be trimmed more nose-up. It will be found that the round-out, touchdown, and landing roll are much easier to accomplish when they are preceded by a proper final approach with precise control of airspeed, attitude, power, and drag, resulting in a stabilized descent angle. Estimating height and movement. During the approach, round-out, and touchdown, vision is of prime importance. To provide a wide scope of vision and to foster good judgment of height and movement, the pilot's head should assume a natural, straight-ahead position. The pilot's visual focus should not be fixed on any one side or any one spot ahead of the airplane, but should be changing slowly from a point just over the airplane's nose to the desired touchdown zone and back again, while maintaining a deliberate awareness of distance from either side of the runway within the pilot's peripheral field of vision. Accurate estimation of distance is, besides being a matter of practice, dependent upon how clearly objects are seen. It requires that the vision be focused properly in order that the important objects stand out as clearly as possible. Speed blurs objects at close range. For example, most everyone has noted this in an automobile moving at high speed. Nearby objects seem to merge together in a blur, while objects farther away stand out clearly. The driver subconsciously focuses the eyes sufficiently far ahead of the automobile to see objects distinctly. The distance at which the pilot's vision is focused should be proportionate to the speed at which the airplane is traveling over the ground. Thus, as speed is reduced during the round out, the distance ahead of the airplane at which it is possible to focus should be brought closer accordingly. If the pilot attempts to focus on a reference that is too close or looks directly down, the reference will become blurred. See Figure 8-5, and the reaction will be either too abrupt or too late. In this case, the pilot's tendency will be to over-control, round out high, and make full stall drop-in landings. When the pilot focuses too far ahead, accuracy in judging the closeness of the ground is lost, and the consequent reaction will be too slow, since there will not appear to be a necessity for action. This will result in the airplane flying into the ground nose first. The change of visual focus from a long distance to a short distance requires a definite time interval, and even though the time is brief, the airplane's speed during the interval is such that the airplane travels an appreciable distance, both forward and downward toward the ground. If the focus is changed gradually, being brought progressively closer as speed is reduced, the time interval and the pilot's reaction will be reduced and the whole landing process smoothed out. Round out, flare. The round out is a slow, smooth transition from a normal approach attitude to a landing attitude, gradually rounding out the flight path to one that is parallel with and within a very few inches above the runway. When the airplane, in a normal descent, approaches within what appears to be 10 to 20 feet above the ground, the round out, or flare, should be started, and once started should be a continuous process until the airplane touches down on the ground. As the airplane reaches a height above the ground, where a timely change can be made into the proper landing attitude, back elevator pressure should be gradually applied to slowly increase the pitch attitude and angle of attack. See Figure 8-6. This will cause the airplane's nose to gradually rise toward the desired landing attitude. The angle of attack should be increased at a rate that will allow the airplane to continue settling slowly as forward speed decreases. When the angle of attack is increased, the lift is momentarily increased, which decreases the rate of descent. Since power normally is reduced to idle during the round out, the airspeed will also gradually decrease. This will cause lift to decrease again, and it must be controlled by raising the nose and further increasing the angle of attack. During the round out, the airspeed is being decreased to touchdown speed while the lift is being controlled so the airplane will settle gently onto the landing surface. The round out should be executed at a rate that the proper landing attitude and the proper touchdown airspeed are attained simultaneously, just as the wheels contact the landing surface. The rate at which the round out is executed depends on the airplane's height above the ground, the rate of descent, and the pitch attitude. A round out started excessively high must be executed more slowly than one from a lower height to allow the airplane to descend to the ground while the proper landing attitude is being established. The rate of rounding out must also be proportionate to the rate of closure with the ground. When the airplane appears to be descending very slowly, the increase in pitch attitude must be made at a correspondingly slow rate. Visual cues are important in flaring at the proper altitude and maintaining the wheels a few inches above the runway until eventual touchdown. Flare cues are primarily dependent on the angle at which the pilot's central vision intersects the ground or runway, ahead and slightly to the side. Proper depth perception is a factor in a successful flare, but the visual cues used most are those related to changes in runway or terrain perspective and to changes in the size of familiar objects near the landing area, such as fences, bushes, trees, hangars, and even sod or runway texture. The pilot should direct central vision at a shallow downward angle of from 10 degrees to 15 degrees toward the runway as the round out, flare, is initiated. See Figure 8-7. Maintaining the same viewing angle causes the point of visual interception with the runway to move progressively rearward toward the pilot as the airplane loses altitude. This is an important visual cue in assessing the rate of altitude loss. Conversely, forward movement of the visual interception point will indicate an increase in altitude and would mean that the pitch angle was increased too rapidly, resulting in an overflare. Location of the visual interception point in conjunction with assessment of flow velocity of nearby off-runway terrain, as well as the similarity of appearance of height above the runway ahead of the airplane in comparison to the way it looked when the airplane was taxied prior to takeoff, is also used to judge when the wheels are just a few inches above the runway. The pitch attitude of the airplane in a full flap approach is considerably lower than in a no-flap approach. To attain the proper landing attitude before touching down, the nose must travel through a greater pitch change when flaps are fully extended. Since the roundout is usually started at approximately the same height above the ground regardless of the degree of flaps used, the pitch attitude must be increased at a faster rate when full flaps are used. However, the roundout should still be executed at a rate proportionate to the airplane's downward motion. Once the actual process of rounding out is started, the elevator control should not be pushed forward. If too much back elevator pressure has been exerted, this pressure should be either slightly relaxed or held constant, depending on the degree of the error. In some cases, it may be necessary to advance the throttle slightly to prevent an excessive rate of sink or stall, all of which would result in a hard drop-in type landing. It is recommended that the student pilot form the habit of keeping one hand on the throttle throughout the approach and landing, should a sudden and unexpected hazardous situation require an immediate application of power. Touchdown. The touchdown is the gentle settling of the airplane onto the landing surface. The roundout and touchdown should be made with the engine idling and the airplane at minimum controllable airspeed, so that the airplane will touch down on the main gear at approximately stalling speed. As the airplane settles, the proper landing attitude is attained by application of whatever back elevator pressure is necessary. Some pilots may try to force or fly the airplane onto the ground without establishing the proper landing attitude. The airplane should never be flown on the runway with excessive speed. It is paradoxical that the way to make an ideal landing is to try to hold the airplane's wheels a few inches off the ground as long as possible with the elevators. In most cases, when the wheels are within 2 or 3 feet off the ground, the airplane will still be settling too fast for a gentle touchdown. Therefore, this descent must be retarded by further back elevator pressure. Since the airplane is already close to its stalling speed and is settling, this added back elevator pressure will only slow up the settling instead of stopping it. At the same time, it will result in the airplane touching the ground in the proper landing attitude and the main wheels touching down first so that little or no weight is on the nose wheel. See Figure 8-8. After the main wheels make initial contact with the ground, back elevator pressure should be held to maintain a positive angle of attack for aerodynamic braking, and to hold the nose wheel off the ground until the airplane decelerates. As the airplane's momentum decreases, back elevator pressure may be gradually relaxed to allow the nose wheel to gently settle onto the runway. This will permit steering with the nose wheel. At the same time, it will cause a low angle of attack and negative lift on the wings to prevent floating or skipping, and will allow the full weight of the airplane to rest on the wheels for better braking action. It is extremely important that the touchdown occur with the airplane's longitudinal axis exactly parallel to the direction in which the airplane is moving along the runway. Failure to accomplish this imposes severe side loads on the landing gear. To avoid these side stresses, the pilot should not allow the airplane to touch down while turned into the wind or drifting. After landing roll. The landing process must never be considered complete until the airplane decelerates to the normal taxi speed during the landing roll or has been brought to a complete stop when clear of the landing area. Many accidents have occurred as a result of pilots abandoning their vigilance and positive control after getting the airplane on the ground. The pilot must be alert for directional control difficulties immediately upon and after touchdown due to the ground friction on the wheels. The friction creates a pivot point on which a moment arm can act. Loss of directional control may lead to an aggravated, uncontrolled, tight turn on the ground, or a ground loop. The combination of centrifugal force acting on the center of gravity, CG, and ground friction of the main wheels resisting it during the ground loop may cause the airplane to tip or lean enough for the outside wingtip to contact the ground. This may even impose a sideward force, which could collapse the landing gear. The rudder serves the same purpose on the ground as it does in the air. It controls the yawing of the airplane. The effectiveness of the rudder is dependent on the airflow, which depends on the speed of the airplane. As the speed decreases and the nose wheel has been lowered to the ground, the steerable nose provides more positive directional control. The brakes of an airplane serve the same primary purpose as the brakes of an automobile, to reduce speed on the ground. In airplanes, they may also be used as an aid in directional control when more positive control is required than could be obtained with rudder or nose wheel steering alone. To use brakes on an airplane equipped with toe brakes, the pilot should slide the toes or feet up from the rudder pedals to the brake pedals. If rudder pressure is being held at the time braking action is needed, that pressure should not be released as the feet or toes are being slid up to the brake pedals, because control may be lost before brakes can be applied. Putting maximum weight on the wheels after touchdown is an important factor in obtaining optimum braking performance. During the early part of rollout, some lift may continue to be generated by the wing. After touchdown, the nose wheel should be lowered to the runway to maintain directional control. During deceleration, the nose may be pitched down by braking, and the weight transferred to the nose wheel from the main wheels. This does not aid in braking action, so back pressure should be applied to the controls without lifting the nose wheel off the runway. This will enable the pilot to maintain directional control while keeping weight on the main wheels. Careful application of the brakes can be initiated after the nose wheel is on the ground and directional control is established. Maximum brake effectiveness is just short of the point where skidding occurs. If the brakes are applied so hard that skidding takes place, braking becomes ineffective. Skidding can be stopped by releasing the brake pressure. Also, braking effectiveness is not enhanced by alternately applying and reapplying brake pressure. The brake should be applied firmly and smoothly as necessary. During the ground roll, the airplane's direction of movement can be changed by carefully applying pressure on one brake or uneven pressures on each brake in the desired direction. Caution must be exercised when applying brakes to avoid over-controlling. The ailerons serve the same purpose on the ground as they do in the air. They change the lift and drag components of the wings. During the after-landing roll, they should be used to keep the wings level in much the same way they were used in flight. If a wing starts to rise, aileron control should be applied toward that wing to lower it. The amount required will depend on speed because as the forward speed of the airplane decreases, the ailerons will become less effective. Procedures for using ailerons in crosswind conditions are explained further in this chapter in the crosswind approach and landing section. After the airplane is on the ground, back elevator pressure may be gradually relaxed to place normal weight on the nose wheel to aid in better steering. If available runway permits, the speed of the airplane should be allowed to dissipate in a normal manner. Once the airplane is slowed sufficiently and is turned onto the taxiway and stopped, the pilot should retract the flaps and clean up the airplane. Many accidents have occurred as a result of the pilot unintentionally operating the landing gear control and retracting the gear instead of the flap control when the airplane was still rolling. The habit of positively identifying both of these controls before actuating them should be formed from the very beginning of flight training and continued in all future flying activities. End of Chapter 8, Part 1. Chapter 8, Part 2 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Approaches and Landings, Part 2. Stabilized Approach Concept. A stabilized approach is one in which the pilot establishes and maintains a constant angle glide path towards a predetermined point on the landing runway. It is based on the pilot's judgment of certain visual clues and depends on the maintenance of a constant final descent airspeed and configuration. An airplane descending on final approach at a constant rate and airspeed will be traveling in a straight line toward a spot on the ground ahead. This spot will not be the spot on which the airplane will touch down, because some float will inevitably occur during the roundout, flare. See Figure 8-9. Neither will it be the spot toward which the airplane's nose is pointed, because the airplane is flying at a fairly high angle of attack, and the component of lift exerted parallel to the Earth's surface by the wings tends to carry the airplane forward horizontally. The point toward which the airplane is progressing is termed the aiming point. See Figure 8-9. It is the point on the ground at which, if the airplane maintains a constant glide path and was not flared for landing, it would strike the ground. To a pilot moving straight ahead toward an object, it appears to be stationary. It does not move. This is how the aiming point can be distinguished. It does not move. However, objects in front of and beyond the aiming point do appear to move as the distance is closed, and they appear to move in opposite directions. During instruction in landings, one of the most important skills a student pilot must acquire is how to use visual cues to accurately determine the true aiming point from any distance out on final approach. From this, the pilot will not only be able to determine if the glide path will result in an undershoot or overshoot, but taking into account float during roundout, the pilot will be able to predict the touchdown point to within a very few feet. For a constant angle glide path, the distance between the horizon and the aiming point will remain constant. If a final approach descent has been established, but the distance between the perceived aiming point and the horizon appears to increase, aiming point moving down away from the horizon, then the true aiming point and subsequent touchdown point is farther down the runway. If the distance between the perceived aiming point and the horizon decreases, aiming point moving up toward the horizon, the true aiming point is closer than perceived. When the airplane is established on final approach, the shape of the runway image also presents clues as to what must be done to maintain a stabilized approach to a safe landing. A runway obviously is normally shaped in the form of an elongated rectangle. When viewed from the air during the approach, the phenomenon known as perspective causes the runway to assume the shape of a trapezoid, with the far end looking narrower than the approach end, and the edge lines converging ahead. If the airplane continues down the glide path at a constant angle, stabilized, the image the pilot sees will still be trapezoidal, but of proportionately larger dimensions. In other words, during a stabilized approach, the runway shape does not change. See Figure 8-10. If the approach becomes shallower, however, the runway will appear to shorten and become wider. Conversely, if the approach is steepened, the runway will appear to become longer and narrower. See Figure 8-11. The objective of a stabilized approach is to select an appropriate touchdown point on the runway and adjust the glide path so that the true aiming point and the desired touchdown point basically coincide. Immediately after rolling out on final approach, the pilot should adjust the pitch attitude and power so that the airplane is descending directly toward the aiming point at the appropriate airspeed. The airplane should be in the landing configuration and trimmed for hands-off flight. With the approach set up in this manner, the pilot will be free to devote full attention toward outside references. The pilot should not stare at any one place, but rather scan from one point to another, such as from the aiming point to the horizon, to the trees and bushes, along the runway, to an area well short of the runway, and back to the aiming point. In this way, the pilot will be more apt to perceive a deviation from the desired glide path, and whether or not the airplane is proceeding directly toward the aiming point. If the pilot perceives any indication that the aiming point on the runway is not where desired, an adjustment must be made to the glide path. This in turn will move the aiming point. For instance, if the pilot perceives that the aiming point is short of the desired touchdown point and will result in an undershoot, an increase in pitch attitude and engine power is warranted. A constant airspeed must be maintained. The pitch and power change, therefore, must be made smoothly and simultaneously. This will result in a shallowing of the glide path with the resulting aiming point moving towards the desired touchdown point. Conversely, if the pilot perceives that the aiming point is farther down the runway than the desired touchdown point and will result in an overshoot, the glide path should be steepened by a simultaneous decrease in pitch attitude and power. Once again, the airspeed must be held constant. It is essential that deviations from the desired glide path be detected early, so that only slight and infrequent adjustments to glide path are required. The closer the airplane gets to the runway, the larger and possibly more frequent the required corrections become, resulting in an unstabilized approach. Common errors in the performance of normal approaches and landings. Inadequate wind drift correction on the base leg. Overshooting or undershooting the turn onto final approach, resulting in too steep or too shallow a turn onto final approach. Flat or skidding turns from base leg to final approach as a result of overshooting, inadequate wind drift correction. Poor coordination during turn from base to final approach. Failure to complete the landing checklist in a timely manner. Unstabilized approach. Failure to adequately compensate for flap extension. Poor trim technique on final approach. Attempting to maintain altitude or reach the runway using elevator alone. Focusing too close to the airplane, resulting in a too high round out. Focusing too far from the airplane, resulting in a too low round out. Touching down prior to attaining proper landing attitude. Failure to hold sufficient back elevator pressure after touchdown. Excessive braking after touchdown. Intentional slips. A slip occurs when the bank angle of an airplane is too steep for the existing rate of turn. Unintentional slips are most often the result of uncoordinated rudder-aileron application. Intentional slips, however, are used to dissipate altitude without increasing airspeed and/or to adjust airplane ground track during a crosswind. Intentional slips are especially useful in forced landings and in situations where obstacles must be cleared during approaches to confined areas. A slip can also be used as an emergency means of rapidly reducing airspeed in situations where wing flaps are inoperative or not installed. A slip is a combination of forward movement and sideward with respect to the longitudinal axis of the airplane movement, the lateral axis being inclined and the sideward movement being toward the low end of this axis, low wing. An airplane in a slip is in fact flying sideways. This results in a change in the direction the relative wind strikes the airplane. Slips are characterized by a marked increase in drag and a corresponding decrease in airplane climb, cruise, and glide performance. It is the increase in drag, however, that makes it possible for an airplane in a slip to descend rapidly without an increase in airspeed. Most airplanes exhibit the characteristic of positive static directional stability and, therefore, have a natural tendency to compensate for slipping. An intentional slip, therefore, requires deliberate cross-controlling ailerons and rudder throughout the maneuver. A side slip is entered by lowering a wing and applying just enough opposite rudder to prevent a turn. In a side slip, the airplane's longitudinal axis remains parallel to the original flight path, but the airplane no longer flies straight ahead. Instead, the horizontal component of wing lift forces the airplane also to move somewhat sideways toward the low wing. See Figure 8-12. The amount of slip and therefore the rate of sideward movement is determined by the bank angle. The steeper the bank, the greater the degree of slip. As bank angle is increased, however, additional opposite rudder is required to prevent turning. A forward slip is one in which the airplane's direction of motion continues the same as before the slip was begun. Assuming the airplane is originally in straight flight, the wing on the side toward which the slip is to be made should be lowered by use of the ailerons. Simultaneously, the airplane's nose must be yawed in the opposite direction by applying opposite rudder so that the airplane's longitudinal axis is at an angle to its original flight path. See Figure 8-13. The degree to which the nose is yawed in the opposite direction from the bank should be such that the original ground track is maintained. In a forward slip, the amount of slip and therefore the sink rate is determined by the bank angle. The steeper the bank, the steeper the descent. In most light airplanes, the steepness of a slip is limited by the amount of rudder travel available. In both side slips and forward slips, the point may be reached where full rudder is required to maintain heading, even though the ailerons are capable of further steepening the bank angle. This is the practical slip limit, because any additional bank would cause the airplane to turn even though full opposite rudder is being applied. If there is a need to descend more rapidly even though the practical slip limit has been reached, lowering the nose will not only increase the sink rate, but will also increase airspeed. The increase in airspeed increases rudder effectiveness, permitting a steeper slip. Conversely, when the nose is raised, rudder effectiveness decreases, and the bank angle must be reduced. Discontinuing a slip is accomplished by leveling the wings and simultaneously releasing the rudder pressure while readjusting the pitch attitude to the normal glide attitude. If the pressure on the rudder is released abruptly, the nose will swing too quickly into line and the airplane will tend to acquire excess speed. Because of the location of the pitot tube and static vents, airspeed indicators in some airplanes may have considerable error when the airplane is in a slip. The pilot must be aware of this possibility and recognize a properly performed slip by the attitude of the airplane, the sound of the airflow, and the feel of the flight controls. Unlike skids, however, if an airplane in a slip is made to stall, it displays very little of the yawing tendency that causes a skidding stall to develop into a spin. The airplane in a slip may do little more than tend to roll into a wings level attitude. In fact, in some airplanes, stall characteristics may even be improved. Go-arounds, rejected landings. Whenever landing conditions are not satisfactory, a go-around is warranted. There are many factors that can contribute to unsatisfactory landing conditions. Situations such as air traffic control requirements, unexpected appearance of hazards on the runway, overtaking another airplane, wind shear, wake turbulence, mechanical failure, and/or an unstabilized approach are all examples of reasons to discontinue a landing approach and make another approach under more favorable conditions. The assumption that an aborted landing is invariably the consequence of a poor approach, which in turn is due to insufficient experience or skill, is a fallacy. The go-around is not strictly an emergency procedure. It is a normal maneuver that may at times be used in an emergency situation. Like any other normal maneuver, the go-around must be practiced and perfected. The flight instructor should emphasize early on, and the student pilot should be made to understand that the go-around maneuver is an alternative to any approach and/or landing. Although the need to discontinue a landing may arise at any point in the landing process, the most critical go-around will be one started when very close to the ground. Therefore, the earlier a condition that warrants a go-around is recognized, the safer the go-around, rejected landing, will be. The go-around maneuver is not inherently dangerous in itself. It becomes dangerous only when delayed unduly or executed improperly. Delay in initiating the go-around normally stems from two sources. 1. Landing expectancy, or set, the anticipatory belief that conditions are not as threatening as they are, and that the approach will surely be terminated with a safe landing. And 2. Pride, the mistaken belief that the act of going around is an admission of failure to execute the approach properly. The improper execution of the go-around maneuver stems from a lack of familiarity with the three cardinal principles of the procedure: power, attitude, and configuration. Power. Power is the pilot's first concern. The instant the pilot decides to go around, full or maximum allowable takeoff power must be applied smoothly and without hesitation, and held until flying speed and controllability are restored. Applying only partial power in a go-around is never appropriate. The pilot must be aware of the degree of inertia that must be overcome before an airplane that is settling towards the ground can regain sufficient airspeed to become fully controllable and capable of turning safely or climbing. The application of power should be smooth as well as positive. Abrupt movements of the throttle in some airplanes will cause the engine to falter. Carburetor heat should be turned off for maximum power. Attitude. Attitude is always critical when close to the ground, and when power is added, a deliberate effort on the part of the pilot will be required to keep the nose from pitching up prematurely. The airplane executing a go-around must be maintained in an attitude that permits a buildup of airspeed well beyond the stall point before any effort is made to gain altitude or to execute a turn. Raising the nose too early may produce a stall from which the airplane could not be recovered if the go-around is performed at a low altitude. A concern for quickly regaining altitude during a go-around produces a natural tendency to pull the nose up. The pilot executing a go-around must accept the fact that an airplane will not climb until it can fly, and it will not fly below stall speed. In some circumstances, it may be desirable to lower the nose briefly to gain airspeed. As soon as the appropriate climb airspeed and pitch attitude are attained, the pilot should rough trim the airplane to relieve any adverse control pressures. Later, more precise trim adjustments can be made when flight conditions have stabilized. Configuration. In cleaning up the airplane during the go-around, the pilot should be concerned first with flaps, and secondly with the landing gear, if retractable. When the decision is made to perform a go-around, takeoff power should be applied immediately and the pitch attitude changed so as to slow or stop the descent. After the descent has been stopped, the landing flaps may be partially retracted or placed in the takeoff position as recommended by the manufacturer. Caution must be used, however, in retracting the flaps. Depending on the airplane's altitude and airspeed, it may be wise to retract the flaps intermittently in small increments to allow time for the airplane to accelerate progressively as they are being raised. A sudden and complete retraction of the flaps could cause a loss of lift, resulting in the airplane settling into the ground. See Figure 8-14. Unless otherwise specified in the AFM-POH, it is generally recommended that the flaps be retracted, at least partially, before retracting the landing gear, for two reasons. First, on most airplanes, full flaps produce more drag than the landing gear. And second, in case the airplane should inadvertently touch down as the go-around is initiated, it is most desirable to have the landing gear in the down and locked position. After a positive rate of climb is established, the landing gear can be retracted. When takeoff power is applied, it will usually be necessary to hold considerable pressure on the controls to maintain straight flight and a safe climb attitude. Since the airplane has been trimmed for the approach, a low power and low airspeed condition, application of maximum allowable power will require considerable control pressure to maintain a climb pitch attitude. The addition of power will tend to raise the airplane's nose suddenly and veer to the left. Forward elevator pressure must be anticipated and applied to hold the nose in a safe climb attitude. Right rudder pressure must be increased to counteract torque and P factor, and to keep the nose straight. The airplane must be held in the proper flight attitude regardless of the amount of control pressure that is required. Trim should be used to relieve adverse control pressures and assist the pilot in maintaining a proper pitch attitude. On airplanes that produce high control pressures when using maximum power on go-arounds, pilots should use caution when reaching for the flap handle. Airplane control may become critical during this high workload phase. The landing gear should be retracted only after the initial or rough trim has been accomplished and when it is certain the airplane will remain airborne. During the initial part of an extremely low go-around, the airplane may settle onto the runway and bounce. This situation is not particularly dangerous if the airplane is kept straight and a constant, safe pitch attitude is maintained. The airplane will be approaching safe flying speed rapidly, and the advanced power will cushion any secondary touchdown. If the pitch attitude is increased excessively in an effort to keep the airplane from contacting the runway, it may cause the airplane to stall. This would be especially likely if no trim correction is made and the flaps remain fully extended. The pilot should not attempt to retract the landing gear until after a rough trim is accomplished and a positive rate of climb is established. Ground effect. Ground effect is a factor in every landing and every takeoff in fixed-wing airplanes. Ground effect can also be an important factor in go-arounds. If the go-around is made close to the ground, the airplane may be in the ground effect area. Pilots are often lulled into a sense of false security by the apparent cushion of air under the wings that initially assists in the transition from an approach descent to a climb. This cushion of air, however, is imaginary. The apparent increase in airplane performance is, in fact, due to a reduction in induced drag in the ground effect area. It is borrowed performance that must be repaid when the airplane climbs out of the ground effect area. The pilot must factor in ground effect when initiating a go-around close to the ground. An attempt to climb prematurely may result in the airplane not being able to climb or even maintain altitude at full power. Common errors in the performance of go-arounds, rejected landings are: failure to recognize a condition that warrants a rejected landing, indecision, delay in initiating a go-around, failure to apply maximum allowable power in a timely manner, abrupt power application, improper pitch attitude, failure to configure the airplane appropriately, attempting to climb out of ground effect prematurely, failure to adequately compensate for torque P factor. End of Chapter 8, Part 2. Chapter 8, Part 3 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Approaches and Landings, Part 3. Crosswind approach and landing. Many runways or landing areas are such that landings must be made while the wind is blowing across rather than parallel to the landing direction. All pilots should be prepared to cope with these situations when they arise. The same basic principles and factors involved in a normal approach and landing apply to a crosswind approach and landing. Therefore, only the additional procedures required for correcting for wind drift are discussed here. Crosswind landings are a little more difficult to perform than crosswind takeoffs, mainly due to different problems involved in maintaining accurate control of the airplane while its speed is decreasing rather than increasing as on takeoff. There are two usual methods of accomplishing a crosswind approach and landing: the crab method and the wing-low, side-slip method. Although the crab method may be easier for the pilot to maintain during final approach, it requires a high degree of judgment and timing in removing the crab immediately prior to touchdown. The wing-low method is recommended in most cases, although a combination of both methods may be used. Crosswind final approach. The crab method is executed by establishing a heading, crab, toward the wind with the wings level so that the airplane's ground track remains aligned with the center line of the runway. See Figure 8-15. This crab angle is maintained until just prior to touchdown, when the longitudinal axis of the plane must be aligned with the runway to avoid sideward contact of the wheels with the runway. If a long final approach is being flown, the pilot may use the crab method until just before the roundout is started, and then smoothly change to the wing-low method for the remainder of the landing. The wing-low, side-slip method will compensate for a crosswind from any angle. But more important, it enables the pilot to simultaneously keep the airplane's ground track and longitudinal axis aligned with the runway centerline throughout the final approach, roundout, touchdown, and after landing roll. This prevents the airplane from touching down in a sideward motion and imposing damaging side loads on the landing gear. To use the wing-low method, the pilot aligns the airplane's heading with the centerline of the runway, notes the rate and direction of drift, and then promptly applies drift correction by lowering the upwind wing. See Figure 8-16. The amount the wing must be lowered depends on the rate of drift. When the wing is lowered, the airplane will tend to turn in that direction. It is then necessary to simultaneously apply sufficient opposite rudder pressure to prevent the turn and keep the airplane's longitudinal axis aligned with the runway. In other words, the drift is controlled with aileron and the heading with rudder. The airplane will now be side-slipping into the wind just enough that both the resultant flight path and the ground track are aligned with the runway. If the crosswind diminishes, this crosswind correction is reduced accordingly, or the airplane will begin slipping away from the desired approach path. See Figure 8-17. To correct for strong crosswind, the slip into the wind is increased by lowering the upwind wing a considerable amount. As a consequence, this will result in a greater tendency of the airplane to turn. Since turning is not desired, considerable opposite rudder must be applied to keep the airplane's longitudinal axis aligned with the runway. In some airplanes, there may not be sufficient rudder travel available to compensate for the strong turning tendency caused by the steep bank. If the required bank is such that full opposite rudder will not prevent a turn, the wind is too strong to safely land the airplane on that particular runway with those wind conditions. Since the airplane's capability will be exceeded, it is imperative that the landing be made on a more favorable runway, either at that airport or at an alternate airport. Flaps can and should be used during most approaches, since they tend to have a stabilizing effect on the airplane. The degree to which flaps should be extended will vary with the airplane's handling characteristics, as well as the wind velocity. Crosswind roundout, flare. Generally, the roundout can be made like a normal landing approach, but the application of a crosswind correction is continued as necessary to prevent drifting. Since the airspeed decreases as the roundout progresses, the flight controls gradually become less effective. As a result, the crosswind correction being held will become inadequate. When using the wing-low method, it is necessary to gradually increase the deflection of the rudder and ailerons to maintain the proper amount of drift correction. Do not level the wings. Keep the upwind wing down throughout the roundout. If the wings are leveled, the airplane will begin drifting and the touchdown will occur while drifting. Remember, the primary objective is to land the airplane without subjecting it to any side loads that result from touching down while drifting. Crosswind touchdown. If the crab method of drift correction has been used throughout the final approach and roundout, the crab must be removed the instant before touchdown by applying rudder to align the airplane's longitudinal axis with its direction of movement. This requires timely and accurate action. Failure to accomplish this will result in severe side loads being imposed on the landing gear. If the wing-low method is used, the crosswind correction, aileron into the wind and opposite rudder, should be maintained throughout the roundout, and the touchdown made on the upwind main wheel. During gusty or high wind conditions, prompt adjustments must be made in the crosswind correction to assure that the airplane does not drift as the airplane touches down. As the forward momentum decreases after initial contact, the weight of the airplane will cause the downwind main wheel to gradually settle onto the runway. In those airplanes having nose wheel steering interconnected with the rudder, the nose wheel may not be aligned with the runway as the wheels touch down because opposite rudder is being held in the crosswind correction. To prevent swerving in the direction the nose wheel is offset, the corrective rudder pressure must be promptly relaxed just as the nose wheel touches down. Crosswind after landing roll. Particularly during the after landing roll, special attention must be given to maintain directional control by the use of rudder or nose wheel steering, while keeping the upwind wing from rising by the use of aileron. When an airplane is airborne, it moves with the air mass in which it is flying regardless of the airplane's heading and speed. When an airplane is on the ground, it is unable to move with the air mass, crosswind, because of the resistance created by ground friction on the wheels. Characteristically, an airplane has a greater profile or side area behind the main landing gear than forward of it does. With the main wheels acting as a pivot point and the greater surface area exposed to the crosswind behind that pivot point, the airplane will tend to turn or weather vane into the wind. Wind acting on an airplane during crosswind landings is the result of two factors. One is the natural wind, which acts in the direction the air mass is traveling, while the other is induced by the movement of the airplane and acts parallel to the direction of movement. Consequently, a crosswind has a headwind component acting along the airplane's ground track and a crosswind component acting 90 degrees to its track. The resultant or relative wind is somewhere between the two components. As the airplane's forward speed decreases during the after landing roll, the headwind component decreases and the relative wind has more of a crosswind component. The greater the crosswind component, the more difficult it is to prevent weather vaning. Retaining control on the ground is a critical part of the after landing roll because of the weather vaning effect of the wind on the airplane. Additionally, tire side load from runway contact while drifting frequently generates rollovers in tricycle-geared airplanes. The basic factors involved are cornering angle and side load. Cornering angle is the angular difference between the heading of a tire and its path. Whenever a load-bearing tire's path and heading diverge, a side load is created. It is accompanied by tire distortion. Although side load differs in varying tires and air pressures, it is completely independent of speed, and through a considerable range is directional proportional to the cornering angle and the weight supported by the tire. As little as 10 degrees of cornering angle will create a side load equal to half the supported weight. After 20 degrees, the side load does not increase with increasing cornering angle. For each high-wing tricycle-geared airplane, there is a cornering angle at which rollover is inevitable, the rollover axis being the line linking the nose and main wheels. At lesser angles, the rollover may be avoided by use of ailerons, rudder, or steerable nose wheel, but not brakes. While the airplane is decelerating during the after landing roll, more and more aileron is applied to keep the upwind wing from rising. Since the airplane is slowing down, there is less airflow around the ailerons, and they become less effective. At the same time, the relative wind is becoming more of a crosswind and exerting a greater lifting force on the upwind wing. When the airplane is coming to a stop, the aileron control must be held fully toward the wind. Maximum safe crosswind velocities. Takeoffs and landings in certain crosswind conditions are inadvisable or even dangerous. See Figure 8-18. If the crosswind is great enough to warrant an extreme drift correction, a hazardous landing condition may result. Therefore, the takeoff and landing capabilities with respect to the reported surface wind conditions and the available landing directions must be considered. Before an airplane is type certified by the Federal Aviation Administration, FAA, it must be flight tested to meet certain requirements. Among these is the demonstration of being satisfactorily controllable with no exceptional degree of skill or alertness on the part of the pilot in 90-degree crosswinds up to a velocity equal to 0.2 VSO. This means a wind speed of 2/10 of the airplane's stalling speed with power off and landing gear flaps down. Regulations require that the demonstrated crosswind velocity be included on a placard in airplanes certificated after May 3, 1962. The headwind component and the crosswind component for a given situation can be determined by reference to a crosswind component chart. See Figure 8-19. It is imperative that pilots determine the maximum crosswind component of each airplane they fly and avoid operations in wind conditions that exceed the capability of the airplane. Common errors in the performance of crosswind approaches and landings are attempting to land in crosswinds that exceed the airplane's maximum demonstrated crosswind component, inadequate compensation for wind drift on the turn from base leg to final approach, resulting in undershooting or overshooting, inadequate compensation for wind drift on final approach, unstabilized approach, failure to compensate for increased drag during side slip, resulting in excessive sink rate and/or too low an airspeed, touchdown while drifting, excessive airspeed on touchdown, failure to apply appropriate flight control inputs during rollout, failure to maintain direction control on rollout, excessive braking. Turbulent air approach and landing. Power on approaches at an airspeed slightly above the normal approach speed should be used for landing in turbulent air. This provides for more positive control of the airplane when strong horizontal wind gusts or up and down drafts are experienced. Like other power-on approaches, when the pilot can vary the amount of power, a coordinated combination of both pitch and power adjustments is usually required. As in most other landing approaches, the proper approach attitude and airspeed require a minimum roundout and should result in little or no floating during the landing. To maintain good control, the approach in turbulent air with gusty crosswind may require the use of partial wing flaps. With less than full flaps, the airplane will be in a higher pitch attitude. Thus, it will require less of a pitch change to establish the landing attitude, and the touchdown will be at a higher airspeed to ensure more positive control. The speed should not be so excessive that the airplane will float past the desired landing area. One procedure is to use the normal approach speed plus 1/2 of the wind gust factors. If the normal speed is 70 knots and the wind gusts increase 15 knots, airspeed of 77 knots is appropriate. In any case, the airspeed and the amount of flaps should be as the airplane manufacturer recommends. An adequate amount of power should be used to maintain the proper airspeed and descent path throughout the approach, and the throttle retarded to idling position only after the main wheels contact the landing surface. Care must be exercised in closing the throttle before the pilot is ready for touchdown. In this situation, the sudden or premature closing of the throttle may cause a sudden increase in the descent rate that could result in a hard landing. Landings from power approaches in turbulence should be such that the touchdown is made with the airplane in approximately level flight attitude. The pitch attitude at touchdown should be only enough to prevent the nose wheel from contacting the surface before the main wheels have touched the surface. After touchdown, the pilot should avoid the tendency to apply forward pressure on the yoke, as this may result in wheelbarrowing and possible loss of control. The airplane should be allowed to decelerate normally, assisted by careful use of wheel brakes. Heavy braking should be avoided until the wings are devoid of lift and the airplane's full weight is resting on the landing gear. End of Chapter 8, Part 3.
Chapter 8, Part 4 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Andrea Kay. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 8, Part 4. Short Field Approach and Landing. Short field approaches and landings require the use of procedures for approaches and landings at fields with a relatively short landing area or where an approach is made over obstacles that limit the available landing area. Figures 8-20 and 8-21. As in short field takeoffs, it is one of the most critical of the maximum performance operations. It requires that the pilot fly the airplane at one of its crucial performance capabilities while close to the ground in order to safely land within confined areas. This low-speed type of power-on approach is closely related to the performance of flight at minimum controllable airspeeds. To land within a short field or a confined area, the pilot must have precise, positive control of the rate of descent and airspeed to produce an approach that will clear any obstacles, result in little or no floating during the roundout, and permit the airplane to be stopped in the shortest possible distance. The procedures for landing in a short field or for landing approaches over obstacles, as recommended in the AFM-POH, should be used. A stabilized approach is essential. Figures 8-22 and 8-23. These procedures generally involve the use of full flaps and the final approach started from an altitude of at least 500 feet higher than the touchdown area. A wider than normal pattern should be used so that the airplane can be properly configured and trimmed. In the absence of the manufacturer's recommended approach speed, a speed of not more than 1.3 VSO should be used. For example, in an airplane that stalls at 60 knots with power off and flaps and landing gear extended, the approach speed should not be higher than 78 knots. In gusty air, no more than 1/2 the gust factor should be added. An excessive amount of airspeed could result in a touchdown too far from the runway threshold or an after-landing roll that exceeds the available landing area. After the landing gear and full flaps have been extended, the pilot should simultaneously adjust the power and the pitch attitude to establish and maintain the proper descent angle and airspeed. A coordinated combination of both pitch and power adjustments is required. When this is done properly, very little change in the airplane's pitch attitude and power setting is necessary to make corrections in the angle of descent and airspeed. The short field approach and landing is in reality an accuracy approach to a spot landing. The procedures previously outlined in the section on the stabilized approach concept should be used. If it appears that the obstacle clearance is excessive and touchdown will occur well beyond the desired spot, leaving insufficient room to stop, power may be reduced while lowering the pitch attitude to steepen the descent path and increase the rate of descent. If it appears that the descent angle will not ensure safe clearance of obstacles, power should be increased while simultaneously raising the pitch attitude to shallow the descent path and decrease the rate of descent. Care must be taken to avoid an excessively low airspeed. If the speed is allowed to become too slow, an increase in pitch and application of full power may only result in a further rate of descent. This occurs when the angle of attack is so great and creating so much drag that the maximum available power is insufficient to overcome it. This is generally referred to as operating in the region of reversed command or operating on the backside of the power curve. Because the final approach over obstacles is made at a relatively steep approach angle and close to the airplane's stalling speed, the initiation of the round-out or flare must be judged accurately to avoid flying into the ground or stalling prematurely and sinking rapidly. A lack of floating during the flare, with sufficient control to touch down properly, is one verification that the approach speed was correct. Touchdown should occur at the minimum controllable airspeed with the airplane in approximately the pitch attitude that will result in a power-off stall when the throttle is closed. Care must be exercised to avoid closing the throttle too rapidly before the pilot is ready for touchdown, as closing the throttle may result in an immediate increase in the rate of descent and a hard landing. Upon touchdown, the airplane should be held in this positive pitch attitude as long as the elevators remain effective. This will provide aerodynamic braking to assist in deceleration. Immediately upon touchdown and closing the throttle, appropriate braking should be applied to minimize the after-landing roll. The airplane should be stopped within the shortest possible distance consistent with safety and controllability. If the proper approach speed has been maintained, resulting in minimum float during the roundout, and the touchdown made at minimum control speed, minimum braking will be required. Common errors in the performance of short field approaches and landings are failure to allow enough room on final to set up the approach, necessitating an overly steep approach and high sink rate, unstabilized approach, undue delay in initiating glide path corrections, too low an airspeed on final resulting in inability to flare properly and landing hard, too high an airspeed resulting in floating on roundout, prematurely reducing power to idle on roundout, resulting in hard landing, touchdown with excessive airspeed, excessive and/or unnecessary braking after touchdown, failure to maintain directional control. Soft field approach and landing. Landing on fields that are rough or have soft surfaces, such as snow, sand, mud, or tall grass, requires unique procedures. When landing on such surfaces, The objective is to touch down as smoothly as possible and at the slowest possible landing speed. The pilot must control the airplane in a manner that the wings support the weight of the airplane as long as practical to minimize drag and stresses imposed on the landing gear by the rough or soft surface. The approach for the soft field landing is similar to the normal approach used for operating into long, firm landing areas. The major difference between the two is that during the soft field landing, the airplane is held 1 to 2 feet off the surface in ground effect as long as possible. This permits a more gradual dissipation of forward speed to allow the wheels to touch down gently at minimum speed. This technique minimizes the nose-over forces that suddenly affect the airplane at the moment of touchdown. Power can be used throughout the level off and touchdown to ensure touchdown at the slowest possible airspeed, and the airplane should be flown onto the ground with the weight fully supported by the wings. Figure 8-24. The use of flaps during soft field landings will aid in touching down at minimum speed and is recommended whenever practical. In low-wing airplanes, the flaps may suffer damage from mud, stones, or slush thrown up by the wheels. If flaps are used, it is generally inadvisable to retract them during the after-landing roll, because the need for flap retraction is usually less important than the need for total concentration on maintaining full control of the airplane. The final approach airspeed used for short field landings is equally appropriate to soft field landings. The use of higher approach speeds may result in excessive float in ground effect, and floating makes a smooth, controlled touchdown even more difficult. There is, however, no reason for a steep angle of descent unless obstacles are present in the approach path. Touchdown on a soft or rough field should be made at the lowest possible airspeed with the airplane in a nose-high pitch attitude. In nose-wheel type airplanes, after the main wheels touch the surface, the pilot should hold sufficient back elevator pressure to keep the nose wheel off the surface. Using back elevator pressure and engine power, the pilot can control the rate at which the weight of the airplane is transferred from the wings to the wheels. Field conditions may warrant that the pilot maintain a flight condition in which the main wheels are just touching the surface, but the weight of the airplane is still being supported by the wings until a suitable taxi surface is reached. At any time during this transition phase, before the weight of the airplane is being supported by the wheels and before the nose wheel is on the surface, the pilot should be able to apply full power and perform a safe takeoff, obstacle clearance and field length permitting, should the pilot elect to abandon the landing. Once committed to a landing, the pilot should gently lower the nose wheel to the surface. A slight addition of power usually will aid in easing the nose wheel down. The use of brakes on a soft field is not needed and should be avoided, as this may tend to impose a heavy load on the nose gear due to premature or hard contact with the landing surface, causing the nose wheel to dig in. The soft or rough surface itself will provide sufficient reduction in the airplane's forward speed. Often it will be found that upon landing on a very soft field, the pilot will need to increase power to keep the airplane moving and from becoming stuck in the soft surface. Common errors in the performance of soft field approaches and landings are excessive descent rate on final approach, excessive airspeed on final approach, unstabilized approach, round out too high above the runway surface, poor power management during round out and touchdown, hard touchdown, inadequate control of the airplane weight transfer from wings to wheels after touchdown, allowing the nose wheel to fall to the runway after touchdown rather than controlling its descent. End of Chapter 8, Part 4. Recording by Andrea Kay.
Chapter 8, Part 5 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 8, Part 5. Power Off Accuracy Approaches. Power off accuracy approaches are approaches and landings made by gliding with the engine idling through a specific pattern to a touchdown beyond and within 200 feet of a designated line or mark on the runway. The objective is to instill in the pilot the judgment and procedures necessary for accurately flying the airplane without power to a safe landing. The ability to estimate the distance an airplane will glide to a landing is the real basis of all power-off accuracy approaches and landings. This will largely determine the amount of maneuvering that may be done from a given altitude. In addition to the ability to estimate distance, it requires the ability to maintain the proper glide while maneuvering the airplane. With experience and practice, altitudes up to approximately 1,000 feet can be estimated with fair accuracy. While above this level, the accuracy and judgment of height above the ground decreases, since all features tend to merge. The best aid in perfecting the ability to judge height above this altitude is through the indications of the altimeter and associating them with the general appearances of the Earth. The judgment of altitude in feet, hundreds of feet, or thousands of feet is not as important as the ability to estimate gliding angle and its resultant distance. The pilot who knows the normal glide angle of the airplane can estimate with reasonable accuracy the approximate spot along a given ground path at which the airplane will land, regardless of altitude. The pilot, who also has the ability to accurately estimate altitude, can judge how much maneuvering is possible during the glide, which is important to the choice of landing areas in an actual emergency. The objective of a good final approach is to descend at an angle that will permit the airplane to reach the desired landing area and at an airspeed that will result in minimum floating just before touchdown. To accomplish this, it is essential that both the descent angle and the airspeed be accurately controlled. Unlike a normal approach, when the power setting is variable, on a power-off approach the power is fixed at the idle setting. Pitch attitude is adjusted to control the airspeed. This will also change the glide or descent angle. By lowering the nose to keep the approach airspeed constant, the descent angle will steepen. If the airspeed is too high, raise the nose. And when the airspeed is too low, lower the nose. If the pitch attitude is raised too high, the airplane will settle rapidly due to the slow airspeed and insufficient lift. For this reason, never try to stretch a glide to reach the desired landing spot. Uniform approach patterns such as 90-degree, 180-degree, or 360-degree power-off approaches are described further in this chapter. Practice in these approaches provides the pilot with the basis on which to develop judgment in gliding distance and in planning an approach. The basic procedure in these approaches involves closing the throttle at a given altitude and gliding to a key position. This position, like the pattern itself, must not be allowed to become the primary objective. It is merely a convenient point in the air from which the pilot can judge whether the glide will safely terminate at the desired spot. The selected key position should be one that is appropriate for the available altitude and the wind condition. From the key position, the pilot must constantly evaluate the situation. It must be emphasized that, although accurate spot touchdowns are important, safe and properly executed approaches and landings are vital. The pilot must never sacrifice a good approach or landing just to land on the desired spot. 90-degree power-off approach. The 90-degree power-off approach is made from the base leg and requires only a 90-degree turn-on to final approach. The approach path may be varied by positioning the base leg closer to or farther out from the approach end of the runway according to wind conditions. See Figure 8-25. The glide from the key position on the base leg through the 90-degree turn to the final approach is the final part of all accuracy landing maneuvers. The 90-degree power-off approach usually begins from a rectangular pattern at approximately 1,000 feet above the ground or at normal traffic pattern altitude. The airplane should be flown onto a downwind leg at the same distance from the landing surface as in a normal traffic pattern. The before landing checklist should be completed on the downwind leg, including extension of the landing gear if the airplane is equipped with retractable gear. After a medium bank turn onto the base leg is completed, the throttle should be retarded slightly and airspeed allowed to decrease to the normal base leg speed. See Figure 8-26. On the base leg, the airspeed, wind, drift correction, and altitude should be maintained while proceeding to the 45-degree key position. At this position, the intended landing spot will appear to be on a 45-degree angle from the airplane's nose. The pilot can determine the strength and direction of the wind from the amount of crab necessary to hold desired ground track on the base leg. This will help in planning the turn onto final approach and in lowering the correct amount of flaps. At the 45-degree key position, the throttle should be closed completely. The propeller control, if equipped, advance to the full increase RPM position and altitude maintained until the airspeed decreases to the manufacturer's recommended glide speed. In the absence of recommended speed, use 1.4 VSO. When the airspeed is attained, the nose should be lowered to maintain the gliding speed and controls retrimmed. The base to final turn should be planned and accomplished so that upon rolling out of the turn, the airplane will be aligned with the runway centerline. When on final approach, the wing flaps are lowered and the pitch attitude adjusted as necessary to establish the proper descent angle and airspeed. 1.3 VSO. Then the controls retrimmed. Slight adjustments in pitch attitude or flap settings may be necessary to control the glide angle and airspeed. However, never try to stretch the glide or retract the flaps to reach the desired landing spot. The final approach may be made with or without the use of slips. After the final approach glide has been established, full attention is then given to making a good, safe landing rather than concentrating on the selected landing spot. The base leg position and the flap setting already determined the probability of landing on the spot. In any event, it is better to execute a good landing 200 feet from the spot than to make a poor landing precisely on the spot. 180-degree power-off approach. The 180-degree power-off approach is executed by gliding with the power off from a given point on a downwind leg to a pre-selected landing spot. See Figure 8-27. It is an extension of the principles involved in the 90-degree power-off approach just described. Its objective is to further develop judgment in estimating distance and glide ratios, in that the airplane is flown without power from a higher altitude and through a 90-degree turn to reach the base leg position at a proper altitude for executing the 90-degree approach. The 180-degree power-off approach requires more planning and judgment than the 90-degree power-off approach. In the execution of 180-degree power-off approaches, the airplane is flown on a downwind heading parallel to the landing runway. The altitude from which this type of approach should be started will vary with the type of airplane, but it should usually not exceed 1,000 feet above the ground, except with large airplanes. Greater accuracy in judgment and maneuvering is required at higher altitudes. When abreast of or opposite the desired landing spot, the throttle should be closed and altitude maintained while decelerating to the manufacturer's recommended glide speed, or 1.4 VSO. The point at which the throttle is closed is the downwind key position. The turn from the downwind leg to the base leg should be a uniform turn with a medium or slightly steeper bank. The degree of bank and amount of this initial turn will depend upon the glide angle of the airplane and the velocity of the wind. Again, the base leg should be positioned as needed for the altitude or wind condition. Position the base leg to conserve or dissipate altitude so as to reach the desired landing spot. The turn onto the base leg should be made with an altitude high enough and close enough to permit the airplane to glide. to what would normally be the base key position in a 90-degree power-off approach. Although the key position is important, it must not be overemphasized nor considered as a fixed point on the ground. Many inexperienced pilots may gain a conception of it as a particular landmark, such as a tree, crossroad, or other visual reference, to be reached at a certain altitude. This will result in a mechanical conception and leave the pilot at a total loss at any time such objects are not present. Both altitude and geographical location should be varied as much as is practical to eliminate any such conception. After reaching the base key position, the approach and landing are the same as in the 90-degree power-off approach. 360-degree power-off approach. The 360-degree power-off approach is one in which the airplane glides through a 360-degree change of direction to the preselected landing spot. The entire pattern is designed to be circular, but the turn may be shallowed, steepened, or discontinued at any point to adjust the accuracy of the flight path. The 360-degree approach is started from a position over the approach end of the landing runway or slightly to the side of it, with the airplane headed in the proposed landing direction and the landing gear and flaps retracted. See Figure 8-28. It is usually initiated from approximately 2,000 feet or more above the ground, where the wind may vary significantly from that of lower altitudes. This must be taken into account when maneuvering the airplane to a point from which a 90-degree or 180-degree power-off approach can be completed. After the throttle is closed over the intended point of the landing, the proper glide speed should immediately be established and a medium banked turn may be in the desired direction so as to arrive at the downwind key position opposite the intended landing spot. At or just beyond the downwind key position, the landing gear may be extended, if the airplane is equipped with retractable gear. The altitude at the downwind key position should be approximately 1,000 to 1,200 feet above the ground. After reaching that point, the turn should be continued to arrive at a base leg key position at an altitude of about 800 feet above the terrain. Flaps may be used at this position as necessary, but full flaps should not be used until established on the final approach. The angle of bank can be varied as needed throughout the pattern to correct for wind conditions and to align the airplane with the final approach. The turn to final should be completed at a minimum altitude of 300 feet above the terrain. Common errors in performance of power-off accuracy approaches are downwind leg too far from the runway landing area, overextension of downwind leg resulting from tailwind, inadequate compensation for wind drift on base leg, skidding turns in an effort to increase gliding distance, failure to lower landing gear in retractable gear airplanes, attempting to stretch the glide during undershoot, premature flap extension, landing gear extension, use of throttle to increase the glide instead of merely clearing the engine, forcing the airplane onto the runway in order to avoid overshooting the designated landing spot. Emergency approaches and landings. Simulated. From time to time on dual flights, the instructor should give simulated emergency landings by retarding the throttle and calling simulated emergency landing. The objective of these simulated emergency landings is to develop the pilot's accuracy, judgment, planning, procedures, and confidence when little or no power is available. A simulated emergency landing may be given with the airplane in any configuration. When the instructor calls simulated emergency landing, the pilot should immediately establish a glide attitude and ensure the flaps and landing gear are in the proper configuration for the existing situation. When the proper glide speed is attained, the nose should then be lowered and the airplane trimmed to maintain that speed. A constant gliding speed should be maintained because variations of gliding speed nullify all attempts at accuracy and judgment of gliding distance and the landing spot. The many variables, such as altitude, obstruction, wind direction, landing surface and gradient, and landing distance requirements of the airplane will determine the pattern and approach procedures to use. Utilizing any combination of normal gliding maneuvers, from wings level to spirals, the pilot should eventually arrive at the normal key position at a normal traffic pattern altitude for the selected landing area. From this point on, the approach should be as nearly as possible to the normal power-off approach. See Figure 8-29. With the greater choice of fields afforded by higher altitudes, the inexperienced pilots may be inclined to delay making a decision, and with considerable altitude in which to maneuver, errors in maneuvering and estimation of glide distance may develop. All pilots should learn to determine the wind direction and estimate its speed from the windsock at the airport, smoke from factories or houses, dust, brush fires, and windmills. Once a field has been selected, the student pilot should always be required to indicate it to the instructor. Normally, the student should be required to plan and fly a pattern for landing on the field first elected until the instructor terminates the simulated emergency landing. This will give the instructor an opportunity to explain and correct any errors. It will also give the student an opportunity to see the results of the errors. However, if the student realizes during the approach that a poor field has been selected, one that would obviously result in disaster if a landing were to be made, and there is a more advantageous field within a gliding distance, a change to a better field should be permitted. The hazards involved in these last-minute decisions, such as excessive maneuvering at very low altitudes, should be thoroughly explained by the instructor. Slipping the airplane, using flaps, varying the position of the base leg, and varying the turn onto final approach should be stressed as ways of correcting for misjudgment of altitude and glide angle. Eagerness to get down is one of the most common faults of inexperienced pilots during simulated emergency landings. In giving way to this, they forget about the speed and arrive at the edge of the field with too much speed to permit a safe landing. Too much speed may be just as dangerous as too little. It results in excessive floating and overshooting the desired landing spot. It should be impressed on the students that they cannot dive at a field and expect to land on it. During all simulated emergency landings, the engine should be kept warm and cleared. During a simulated emergency landing, either the instructor or the student should have complete control of the throttle. There should be no doubt as to who has control, since many near accidents have occurred from such misunderstandings. Every simulated emergency landing approach should be terminated as soon as it can be determined whether a safe landing could have been made. In no case should it be continued to a point where it creates an undue hazard or an annoyance to persons or property on the ground. In addition to flying the airplane from the point of simulated engine failure to where a reasonable safe landing could be made, the student should also be taught certain emergency cockpit procedures. The habit of performing these cockpit procedures should be developed to such an extent that, when the engine failure actually occurs, the student will check the critical items that would be necessary to get the engine operating again while selecting a field and planning an approach. Combining the two operations, accomplishing emergency procedures and planning and flying the approach, will be difficult for the student during the early training in emergency landings. There are definite steps and procedures to be followed in a simulated emergency landing. Although they may differ somewhat from the procedures used in an actual emergency, they should be learned thoroughly by the student and each step called out to the instructor. The use of a checklist is strongly recommended. Most airplane manufacturers provide a checklist of the appropriate items. See Figure 8-30. Critical items to be checked should include the position of the fuel tank selector, the quantity of fuel in the tank selected, the fuel pressure gauge to see if the electric fuel pump is needed, the position of the mixture control, the position of the magneto switch, and the use of carburetor heat. Many actual emergency landings have been made and later found to be the result of the fuel selector valve being positioned to an empty tank while the other tank had plenty of fuel. It may be wise to change the position of the fuel selector valve even though the fuel gauge indicates fuel in all tanks, because fuel gauges can be inaccurate. Many actual emergency landings could have been prevented if the pilots had developed the habit of checking these critical items during flight training to the extent that it carried over into later flying. Instruction in emergency procedures should not be limited to simulated emergency landings caused by power failures. Other emergencies associated with the operation of the airplane should be explained, demonstrated, and practiced if practicable. Among these emergencies are such occurrences as fire in flight, electrical or hydraulic system malfunctions, unexpected severe weather conditions, engine overheating, imminent fuel exhaustion, and the emergency operation of airplane systems and equipment. End Chapter 8, Part 5. Recording by Dale Latham.
Chapter 8, Part 6 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Norman Ilver. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Faulty approaches and landings. Low final approach. When the base leg is too low, insufficient power is used, landing flaps are extended prematurely, or the velocity of the wind is misjudged. Sufficient altitude may be lost, which will cause the airplane to be well below the proper final approach path. In such a situation, the pilot would have to apply considerable power to fly the airplane at an excessively low altitude up to the runway threshold. When it is realized the runway will not be reached unless appropriate action is taken, power must be applied immediately to maintain the airspeed, while the pitch attitude is raised to increase lift and stop the descent. When the proper approach path has been intercepted, the correct approach attitude should be reestablished and the power reduced and a stabilized approach maintained. Figure 8-31. Do not increase the pitch attitude without increasing the power, since the airplane will decelerate rapidly and may approach the critical angle of attack and stall. Do not retract the flaps. This will suddenly decrease lift and cause the airplane to sink more rapidly. If there is any doubt about the approach being safely completed, it is advisable to execute an immediate go-around. High final approach. When the final approach is too high, lower the flaps as required. Further reduction in power may be necessary, while lowering the nose simultaneously to maintain approach airspeed and steepen the approach path. Figure 8-32. When the proper approach path has been intercepted, adjust the power as required to maintain a stabilized approach. When steepening the approach path, however, care must be taken that the descent does not result in an excessively high sink rate. If a high sink rate is continued close to the surface, it may be difficult to slow to a proper rate prior to ground contact. Any sink rate in excess of 800 to 1,000 feet per minute is considered excessive. A go-around should be initiated if the sink rate becomes excessive. Slow final approach. When the airplane is flown at a slower than normal airspeed on the final approach, the pilot's judgment of the sink rate, descent, and the height of round-out will be difficult. During an excessively slow approach, the wing is operating near the critical angle of attack, and, depending on the pitch attitude changes and control usage, the airplane may stall or sink rapidly, contacting the ground with a hard impact. Whenever a slow-speed approach is noted, the pilot should apply power to accelerate the airplane and increase the lift to reduce the sink rate and to prevent a stall. This should be done while still at a high enough altitude to establish the correct approach airspeed and attitude. If too slow and too low, it is best to execute a go-around. Use of power. Power can be used effectively during the approach and round-out to compensate for errors in judgment. Power can be added to accelerate the airplane to increase lift without increasing the angle of attack. Thus, the descent can be slowed to an acceptable rate. If the proper landing attitude has been attained and the airplane is only slightly high, the landing attitude should be held constant and sufficient power applied to help ease the airplane onto the ground. After the airplane has touched down, it will be necessary to close the throttle so the additional thrust and lift will be removed and the airplane will stay on the ground. High round out. Sometimes when the airplane appears to temporarily stop moving downward, the round out has been made too rapidly and the airplane is flying level, too high above the runway. Continuing the round out would further reduce the airspeed, resulting in an increase in angle of attack to the critical angle. This would result in the airplane stalling and dropping hard onto the runway. To prevent this, the pitch attitude should be held constant until the airplane decelerates enough to again start descending. Then the round out can be continued to establish the proper landing attitude. This procedure should only be used when there is adequate airspeed. It may be necessary to add a slight amount of power to keep the airspeed from decreasing excessively and to avoid losing lift too rapidly. Although the back elevator pressure may be relaxed slightly, the nose should not be lowered any perceptible amount to make the airplane descend when fairly close to the runway, unless some power is added momentarily. The momentary decrease in lift that would result from lowering the nose and decreasing the angle of attack may be so great that the airplane might contact the ground with the nose wheel first, which could collapse. When the proper landing attitude is attained, the airplane is approaching a stall because the airspeed is decreasing and the critical angle of attack is being approached, even though the pitch attitude is no longer being increased. Figure 8-33. It is recommended that a go-around be executed anytime it appears the nose must be lowered significantly or that the landing is in any other way uncertain. Late or rapid round out. Starting the round out too late or pulling the elevator control back too rapidly to prevent the airplane from touching down prematurely can impose a heavy load factor on the wing and cause an accelerated stall. Suddenly increasing the angle of attack and stalling the airplane during a round out is a dangerous situation since it may cause the airplane to land extremely hard on the main landing gear and then bounce back into the air. As the airplane contacts the ground, the tail will be forced down very rapidly by the back elevator pressure and by inertia acting downward on the tail. Recovery from this situation requires prompt and positive application of power prior to occurrence of the stall. This may be followed by a normal landing if sufficient runway is available. Otherwise, the pilot should execute a go-around immediately. If the round out is late, the nose wheel may strike the runway first, causing the nose to bounce upward. No attempt should be made to force the airplane back onto the ground. A go-around should be executed immediately. Floating during round out. If the airspeed on final approach is excessive, it will result in the airplane floating. Figure 8-34. Before the touchdown can be made, the airplane may be well past the desired landing point and the available runway may be insufficient. When diving in an airplane on final approach to land at the proper point, there will be an appreciable increase in airspeed. The proper touchdown attitude cannot be established without producing an excessive angle of attack and lift. This will cause the airplane to gain altitude or balloon. Anytime the airplane floats, judgment of speed, height, and sink rate must be especially acute. The pilot must smoothly and gradually adjust the pitch attitude as the airplane decelerates to touchdown speed and starts to settle, so the proper landing attitude is attained at the very moment of touchdown. The slightest error in judgment and timing will result in either ballooning or bouncing. The recovery from floating will depend on the amount of floating and the effect of any crosswind, as well as the amount of runway remaining. Since prolonged floating utilizes considerable runway length, it should be avoided, especially on short runways or in strong crosswinds. If the landing cannot be made on the first third of the runway, or the airplane drifts sideways, the pilot should execute a go-around. Ballooning during round out. If the pilot misjudges the rate of sink during a landing and thinks the airplane is descending faster than it should, there is a tendency to increase the pitch attitude and angle of attack too rapidly. This not only stops the descent, but actually starts the airplane climbing. This climbing during the round out is known as ballooning. Figure 8-35. Ballooning can be dangerous because the height above the ground is increasing and the airplane may be rapidly approaching a stalled condition. The altitude gained in each instance will depend on the airspeed or the speed with which the pitch attitude is increased. When ballooning is slight, a constant landing attitude should be held and the airplane allowed to gradually decelerate and settle onto the runway. Depending on the severity of ballooning, the use of throttle may be helpful in cushioning the landing. By adding power, thrust can be increased to keep the airspeed from decelerating too rapidly and the wings from suddenly losing lift. But throttle must be closed immediately after touchdown. Remember that torque can be created as power is applied. Therefore, it will be necessary to use rudder pressure to keep the airplane straight as it settles onto the runway. When ballooning is excessive, it is best to execute a go-around immediately. Do not attempt to salvage the landing. Power must be applied before the airplane enters a stalled condition. The pilot must be extremely cautious of ballooning when there is a crosswind present, because the crosswind correction may be inadvertently released or it may become inadequate. Because of the lower airspeed after ballooning, the crosswind affects the airplane more. Consequently, the wing will have to be lowered even further to compensate for the increased drift. It is imperative that the pilot make certain that the appropriate wing is downed and that directional control is maintained with opposite rudder. If there is any doubt or the airplane starts to drift, execute a go-around. Bouncing during touchdown. When the airplane contacts the ground with a sharp impact as the result of an improper attitude or an excessive rate of sink, it tends to bounce back into the air. Though the airplane's tires and shock struts provide some springing action, the airplane does not bounce like a rubber ball. Instead, it rebounds into the air because the wing's angle of attack was abruptly increased, producing a sudden addition of lift. Figure 8-36. The abrupt change in angle of attack is a result of the inertia instantly forcing the airplane's tail downward when the main wheels contact the ground sharply. The severity of the bounce depends on the airspeed at the moment of contact and the degree to which the angle of attack or pitch attitude was increased. Since a bounce occurs when the airplane makes contact with the ground before a proper touchdown attitude is attained, it is almost invariably accompanied by the application of excessive back elevator pressure. This is usually the result of the pilot realizing too late that the airplane is not in the proper attitude and attempting to establish it just as a second touchdown occurs. The corrective action for a bounce is the same as for ballooning and similarly depends on its severity. When it is very slight and there is no extreme change in the airplane's pitch attitude, a follow-up landing may be executed by applying sufficient power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. In the event a very slight bounce is encountered while landing with a crosswind correction must be maintained while the next touchdown is made. Remember that since the subsequent touchdown will be made at a slower airspeed, the upwind wing will have to be lowered even further to compensate for drift. Extreme caution and alertness must be exercised anytime a bounce occurs, but particularly when there is a crosswind. Inexperienced pilots will almost invariably release the crosswind correction. When one main wheel of the airplane strikes the runway, the other wheel will touch down immediately afterwards, and the wings will become level. Then, with no crosswind correction, as the airplane bounces, the wind will cause the airplane to roll with the wind, thus exposing even more surface to the crosswind and drifting the airplane more rapidly. When a bounce is severe, the safest procedure is to execute a go-around immediately. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. The go-around procedure should be continued even though the airplane may descend and another bounce may be encountered. It would be extremely foolish to attempt a landing from a bad bounce, since airspeed diminishes very rapidly in the nose-high attitude, and a stall may occur before a subsequent touchdown could be made. Porpoising. In a bounced landing that is improperly recovered, the airplane comes in nose first, setting off a series of motions that imitate the jumps and dives of a porpoise, hence the name. Figure 8-37. The problem is improper airplane attitude at touchdown, sometimes caused by inattention, not knowing where the ground is, mistrimming, or forcing the airplane onto the runway. Ground effect decreases elevator control effectiveness and increases the effort required to raise the nose. Not enough elevator or stabilator trim can result in a nose-low contact with the runway and a porpoise develops. Porpoising can also be caused by improper airspeed control. Usually, if an approach is too fast, the airplane floats, and the pilot tries to force it on the runway when the airplane still wants to fly. A gust of wind, a bump in the runway, or even a slight tug on the control wheel will send the airplane aloft again. The corrective action for a porpoise is the same as for a bounce and similarly depends on its severity. When it is very slight, and there is no extreme change in the airplane's pitch attitude, a follow-up landing may be executed by applying sufficient power to cushion the subsequent touchdown and smoothly adjusting the pitch to the proper touchdown attitude. When a porpoise is severe, the safest procedure is to execute a go-around immediately. In a severe porpoise, the airplane's pitch oscillations can become progressively worse until the airplane strikes the runway nose first with sufficient force to collapse the nose gear. Pilot attempts to correct a severe porpoise with flight control and power inputs will most likely be untimely and out of sequence with the oscillations and only make the situation worse. No attempt to salvage the landing should be made. Full power should be applied while simultaneously maintaining directional control and lowering the nose to a safe climb attitude. Wheelbarrowing. When a pilot permits the airplane weight to become concentrated about the nose wheel during the takeoff or landing roll, a condition known as wheelbarrowing will occur. Wheelbarrowing may cause loss of directional control during the landing roll because braking action is ineffective, and the airplane tends to swerve or pivot on the nose wheel, particularly in crosswind conditions. One of the most common causes of wheelbarrowing during the landing roll is a simultaneous touchdown of the main and nose wheel with excessive speed, followed by the application of forward pressure on the elevator control. Usually the situation can be corrected by smoothly applying back elevator pressure. However, if wheelbarrowing is encountered and runway and other conditions permit, it may be advisable to promptly initiate a go-around. Wheelbarrowing will not occur if the pilot achieves and maintains the correct landing attitude, touches down at the proper speed, and gently lowers the nose wheel while losing speed on rollout. If the pilot decides to stay on the ground rather than attempt a go-around, or if directional control is lost, the throttle should be closed and the pitch attitude smoothly but firmly rotated to the proper landing attitude. Raise the flaps to reduce lift and to increase the load on the main wheels for better braking action. Hard landing. When the airplane contacts the ground during landings, its vertical speed is instantly reduced to 0. Unless provisions are made to slow this vertical speed and cushion the impact of touchdown, the force of contact with the ground may be so great that it could cause structural damage to the airplane. The purpose of pneumatic tires, shock-absorbing landing gears, and other devices is to cushion the impact and to increase the time in which the airplane's vertical descent is stopped. The importance of this cushion may be understood from the computation that a 6-inch free fall on landing is roughly equal to a 340 foot per minute descent. Within a fraction of a second, the airplane must be slowed from this rate of vertical descent to zero without damage. During this time, the landing gear, together with some aid from the lift of the wings, must apply whatever force is needed to counteract the force of the airplane's inertia and weight. The lift decreases rapidly as the airplane's forward speed is decreased, and the force on the landing gear increases by the impact of touchdown. When the descent stops, the lift will be practically zero, leaving the landing gear alone to carry both the airplane's weight and inertia force. The load imposed at the instant of touchdown may easily be 3 or 4 times the actual weight of the airplane, depending on the severity of contact. Touchdown in a drift or crab. At times the pilot may correct for wind drift by crabbing on the final approach. If the round out and touchdown are made while the airplane is drifting or in a crab, it will contact the ground while moving sideways. This will impose extreme side loads on the landing gear and, if severe enough, may cause structural failure. The most effective method to prevent drift in primary training airplanes is the wing-low method. This technique keeps the longitudinal axis of the airplane aligned with both the runway and the direction of motion throughout the approach and touchdown. There are 3 factors that will cause the longitudinal axis and the direction of motion to be misaligned during the touchdown: drifting, crabbing, or a combination of both. If the pilot has not taken adequate corrective action to avoid drift during a crosswind landing, the main wheel's tire tread offers resistance to the airplane's sideward movement in respect to the ground. Consequently, any sidewise velocity of the airplane is abruptly decelerated, with the results that the inertia force is as shown in Figure 8-38. This creates a moment around the main wheel when it contacts the ground, tending to overturn or tip the airplane. If the windward wingtip is raised by the action of this moment, all the weight and shock of landing will be borne by one main wheel. This could cause structural damage. Not only are the same factors present that are attempting to raise a wing, but the crosswind is also acting on the fuselage surface behind the main wheels, tending to yaw, weather vane the airplane into the wind. This often results in a ground loop. Ground loop. A ground loop is an uncontrolled turn during ground operation that may occur while taxiing or taking off, but especially during the after-landing roll. Drift or weather vaning does not always cause a ground loop, although these things may cause the initial swerve. Careless use of the rudder, or an uneven ground surface, or a soft spot that retards one main wheel of the airplane may also cause a swerve. In any case, the initial swerve tends to make the airplane ground loop, whether it is a tail wheel or a nose wheel type. Figure 8-39. Nose wheel type airplanes are somewhat less prone to ground loop than tail wheel type airplanes. Since the center of gravity, CG, is located forward of the main landing gear on these airplanes, anytime a swerve develops, centrifugal force acting on the CG will tend to stop the swerving action. If the airplane touches down while drifting or in a crab, the pilot should apply aileron toward the high wing and stop the swerve with the rudder. Brakes should be used to correct for turns or swerves only when the rudder is inadequate. The pilot must exercise caution when applying corrective brake action because it is very easy to over-control and aggravate the situation. If brakes are used, sufficient brake should be applied on the low wing wheel outside of the turn to stop the swerve. When the wings are approximately level, the new direction must be maintained until the airplane has slowed to taxi speed or has stopped. In nose wheel airplanes, a ground loop is almost always a result of wheelbarrowing. The pilot must be aware that even though the nose wheel type airplane is less prone than the tail wheel type airplane, virtually every type of airplane, including large multi-engine airplanes, can be made to ground loop when sufficiently mishandled. Wing rising after touchdown. When landing in a crosswind, there may be instances when a wing will rise during the after-landing roll. This may occur whether or not there is a loss of directional control, depending on the amount of crosswind and the degree of corrective action. Anytime an airplane is rolling on the ground in a crosswind condition, the upwind wing is receiving a greater force from the wind than the downwind wing. This causes a lift differential. Also, as the upwind wing rises, there is an increase in the angle of attack, which increases lift on the upwind wing, rolling the airplane downwind. When the effects of these two factors are great enough, the upwind wing may rise even though directional control is maintained. If no correction is applied, it is possible that the upwind wing will rise sufficiently to cause the downwind wing to strike the ground. In the event a wing starts to rise during the landing roll, the pilot should immediately apply more aileron pressure toward the high wing and continue to maintain direction. The sooner the aileron is applied, the more effective it will be. The further a wing is allowed to rise before taking corrective action, the more airplane surface is exposed to the force of the crosswind. This diminishes the effectiveness of the aileron. Hydroplaning. Hydroplaning is a condition that can exist when an airplane is landed on a runway surface contaminated with standing water, slush, and/or wet snow. Hydroplaning can have serious adverse effects on ground controllability and braking efficiency. The three basic types of hydroplaning are dynamic hydroplaning, reverted rubber hydroplaning, and viscous hydroplaning. Any one of these three can render an airplane partially or totally uncontrollable anytime during the landing roll. Dynamic hydroplaning. Dynamic hydroplaning is a relatively high-speed phenomenon that occurs when there is a film of water on the runway that is at least 1/10 inch deep. As the speed of the airplane and the depth of the water increase, the water layer builds up an increasing resistance to displacement, resulting in the formation of a wedge of water beneath the tire. At some speed, termed the hydroplaning speed, VP, the water pressure equals the weight of the airplane and the tire is lifted off the runway surface. In this condition, the tires no longer contribute to directional control and braking action is nil. Dynamic hydroplaning is related to tire inflation pressure. Data obtained during hydroplaning tests have shown that the minimum dynamic hydroplaning speed, VP, of a tire to be 8.6 times the square root of the tire pressure in pounds per square inch, PSI. For an airplane with a main tire pressure of 24 pounds, the calculated hydroplaning speed would be approximately 42 knots. This is important to note that the calculated speed referred to above is for the start of dynamic hydroplaning. Once hydroplaning has started, it may persist to a significantly slower speed depending on the type being experienced. Reverted rubber hydroplaning. Reverted rubber, steam hydroplaning, occurs during heavy braking that results in a prolonged locked-wheeled skid. Only a thin film of water on the runway is required to facilitate this type of hydroplaning. The tire skidding generates enough heat to cause the rubber to contact with the runway to revert to its original uncured state. The reverted rubber acts as a seal between the tire and the runway, and delays the water exit from the tire footprint area. The water heats and is converted to steam, which supports the tire off the runway. Reverted rubber hydroplaning frequently follows an encounter with dynamic hydroplaning, during which time the pilot may have the brakes locked in an attempt to slow the airplane. Eventually, the airplane slows enough to where the tires make contact with the runway surface and the airplane begins to skid. The remedy for this type of hydroplane is for the pilot to release the brakes and allow the wheels to spin up and apply moderate braking. Reverted rubber hydroplaning is insidious in that the pilot may not know when it begins, and it can persist to very slow ground speeds, 20 knots or less. Viscous hydroplaning. Viscous hydroplaning is due to the viscous properties of water. A thin film of fluid, no more than 1/1000th of an inch in depth, is all that is needed. The tire cannot penetrate the fluid, and the tire rolls on top of the film. This can occur at much slower speed than dynamic hydroplane, but requires a smooth or smooth-acting surface such as asphalt or a touchdown area coated with accumulated rubber of past landings. Such a surface can have the same coefficient of friction as wet ice. When confronted with the possibility of hydroplaning, it is best to land on a grooved runway if available. Touchdown speed should be as slow as possible, consistent with safety. After the nose wheel is lowered to the runway, moderate braking should be applied. If deceleration is not detected and hydroplaning is suspected, the nose should be raised and aerodynamic drag utilized to decelerate to a point where the brakes do become effective. Proper braking technique is essential. The brakes should be applied firmly until reaching a point just short of a skid. At the first sign of a skid, the pilot should release brake pressure and allow the wheels to spin up. Directional control should be maintained as far as possible with the rudder. Remember that in a crosswind, if hydroplaning should occur, the crosswind will cause the airplane to simultaneously weather vane into the wind as well as slide downwind. End of Chapter 8.
Chapter 9 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook, Volume 1 by Federal Aviation Administration. Chapter 9. Performance Maneuvers. Performance maneuvers are used to develop a high degree of pilot skill. They aid the pilot in analyzing the forces acting on the airplane and in developing a fine control touch, coordination, timing, and division of attention for precise maneuvering of the airplane. Performance maneuvers are termed advanced maneuvers because the degree of skill required for proper execution is normally not acquired until a pilot has obtained a sense of orientation and control feel in normal maneuvers. An important benefit of performance maneuvers is the sharpening of fundamental skills to the degree that the pilot can cope with unusual or unforeseen circumstances occasionally encountered in normal flight. Advanced maneuvers are variations and/or combinations of basic maneuvers previously learned. They embody the same principles and techniques as the basic maneuvers, but require a higher degree of skill for proper execution. The student, therefore, who demonstrates a lack of progress in the performance of advanced maneuvers is more than likely deficient in one or more of the basic maneuvers. The flight instructor should consider breaking the advanced maneuver down into its component basic maneuvers in an attempt to identify and correct the deficiency before continuing with the advanced maneuver. Steep turns. The objective of the maneuver is to develop the smoothness, coordination, orientation, division of attention, and control techniques necessary for the execution of maximum performance turns when the airplane is near its performance limits. Smoothness of control use, coordination, and accuracy of execution are the important features of this maneuver. The steep turn maneuver consists of a turn in either direction using a bank angle between 45 to 60 degrees. This will cause an overbanking tendency during which maximum turning performance is attained and relatively high load factors are imposed. Because of the high load factors imposed, these turns should be performed at an airspeed that does not exceed the airplane's designed maneuvering speed, VA. The principles of an ordinary steep turn apply, but as a practice maneuver, the steep turns should be continued until 360 degrees or 720 degrees of turn have been completed. See Figure 9-1. An airplane's maximum turning performance is its fastest rate of turn and its shortest radius of turn, which change both airspeed and angle of bank. Each airplane's turning performance is limited by the amount of power its engine is developing, its limit load factor, structural strength, and its aerodynamic characteristics. The limiting load factor determines the maximum bank, which can be maintained without stalling or exceeding the airplane's structural limitations. In most small airplanes, the maximum bank has been found to be approximately 50 degrees to 60 degrees. The pilot should realize the tremendous additional load that is imposed on an airplane as the bank is increased beyond 45 degrees. During a coordinated turn, With a 70-degree bank, a load factor of approximately 3 Gs is placed on the airplane structure. Most general aviation type airplanes are stressed for approximately 3.8 Gs. Regardless of the airspeed or the type of airplanes involved, a given angle of bank in a turn, during which altitude is maintained, will always produce the same load factor. Pilots must be aware that an additional load factor increases the stalling speed at a significant rate. Stalling speed increases with the square root of the load factor. For example, a light airplane that stalls at 60 knots in level flight will stall at nearly 85 knots in a 60-degree bank. The pilot's understanding and observance of this fact is an indispensable safety precaution for the performance of all maneuvers requiring turns. Before starting the steep turn, the pilot should ensure that the area is clear of other air traffic since the rate of turn will be quite rapid. After establishing the manufacturer's recommended entry speed or design maneuvering speed, the airplane should be smoothly rolled into the selected bank angle between 45 to 60 degrees. As the turn is being established, back elevator pressure should be smoothly increased to increase the angle of attack. This provides the additional wing lift required to compensate for the increasing load factor. After the selected bank angle has been reached, the pilot will find that considerable force is required on the elevator control to hold the airplane in level flight to maintain altitude. Because of this increase in the force applied to the elevators, the load factor increases rapidly as the bank is increased. Additional back elevator pressure increases the angle of attack, which results in an increase in drag. Consequently, power must be added to maintain the entry altitude and airspeed. Eventually, as the bank approaches the airplane's maximum angle, the maximum performance or structural limit is being reached. If this limit is exceeded, the airplane will be subjected to excessive structural loads and will lose altitude or stall. The limit load factor must not be exceeded to prevent structural damage. During the turn, the pilot should not stare at any one object. To maintain altitude as well as orientation requires an awareness of the relative position of the nose, the horizon, the wings, and the amount of bank. The pilot who references the aircraft's turn by watching only the nose will have difficulty holding altitude constant. On the other hand, the pilot who watches the nose, the horizon, and the wings can usually hold altitude within a few feet. If the altitude begins to increase or decrease, relaxing or increasing the back elevator pressure will be required as appropriate. This may also require a power adjustment to maintain the selected airspeed. A small increase or decrease of 1 to 3 degrees of bank angle may be used to control small altitude deviations. All bank angle changes should be done with coordinated use of aileron and rudder. The rollout from the turn should be timed so that the wings reach level flight when the airplane is exactly on the heading from which the maneuver was started. While the recovery is being made, back elevator pressure is gradually released and power reduced as necessary to maintain the altitude and airspeed. Common errors in performance of steep turns are failure to adequately clear the area, excessive pitch change during entry or recovery, attempts to start recovery prematurely, failure to stop the turn on a precise heading, excessive rudder during recovery resulting in skidding, inadequate power management, inadequate airspeed control, poor coordination, gaining altitude in right turns and or losing altitude in left turns, failure to maintain constant bank angle, disorientation, attempting to perform the maneuver by instrument reference rather than visual reference, failure to scan for other traffic during the maneuver. Steep spiral. The objective of this maneuver is to improve pilot techniques for airspeed control, wind drift control, planning, orientation, and division of attention. The steep spiral is not only a valuable flight training maneuver, but it has practical application in providing a procedure for dissipating altitude while remaining over a selected spot in preparation for landing, especially for emergency forced landings. A steep spiral is a constant gliding turn, during which a constant radius around a point on the ground is maintained. Similar to the maneuver, turns around a point. The radius should be such that the steepest bank will not exceed 60 degrees. Sufficient altitude must be obtained before starting this maneuver so that the spiral may be continued through a series of at least 360-degree turns. See Figure 9-2. The maneuver should not be continued below 1,000 feet above the surface unless performing an emergency landing in conjunction with the spiral. Operating the engine at idle speed for a prolonged period during the glide may result in excessive engine cooling or spark plug fouling. The engine should be cleared periodically by briefly advancing the throttle to normal cruise power while adjusting the pitch attitude to maintain a constant airspeed. Preferably, this should be done while headed into the wind to minimize any variation in ground speed and radius of turn. After the throttle is closed and the gliding speed is established, a gliding spiral should be started and a turn of constant radius maintained around a selected spot on the ground. This will require correction for wind drift by steepening the bank on downwind headings and shallowing the bank on upwind headings, just as in the maneuver turns around a point. During the descending spiral, the pilot must judge the direction and speed of the wind at different altitudes and make appropriate changes in the angle of bank to maintain a uniform radius. A constant airspeed should also be maintained throughout the maneuver. Failure to hold the airspeed constant will cause the radius of the turn and necessary angle of bank to vary excessively. On the downwind side of the maneuver, the steeper the bank angle, the lower the pitch attitude must be to maintain a given airspeed. Conversely, on the upwind side, as the bank angle becomes shallower, the pitch attitude must be raised to maintain the proper airspeed. This is necessary because the airspeed tends to change as the bank is changed from shallow to steep to shallow. During practice of the maneuver, the pilot should execute 3 turns and roll out toward a definite object or on a specific heading. During the rollout, smoothness is essential, and the use of controls must be so coordinated that no increase or decrease of speed results when the straight glide is resumed. Common errors in performance of steep spirals are failure to adequately clear the area, failure to maintain constant airspeed, poor coordination resulting in skidding and or slipping, inadequate wind drift correction, failure to coordinate the controls so that no increase, decrease in speed results when straight glide is resumed, failure to scan for other traffic, failure to maintain orientation. Chandelle. The objective of this maneuver is to develop the pilot's coordination, orientation, planning, and accuracy of control during maximum performance flight. A chandelle is a maximum performance climbing turn beginning from approximately straight and level flight and ending at the completion of a precise 180 degrees of turn in wings level, nose high attitude at the minimum controllable airspeed. See Figure 9-3. The maneuver demands that the maximum flight performance of the airplane be obtained. The airplane should gain the most altitude possible for a given degree of bank in a power setting without stalling. Since numerous atmospheric variables beyond control of the pilot will affect the specific amount of altitude gained, the quality of the performance of the maneuver is not judged solely on the altitude gain, but by the pilot's overall proficiency as it pertains to climb performance for the power bank combination used, and to the elements of piloting skill demonstrated. Prior to starting a chandelle, the flaps and gear, if retractable, should be in the up position, power set to cruise condition, and the airspace behind and above clear of other air traffic. The maneuver should be entered from the straight and level flight or a shallow dive and at a speed no greater than the maximum entry speed recommended by the manufacturer, in most cases not above the airplane's design maneuvering speed. VA. After the appropriate airspeed and power setting have been established, the chandelle is started by smoothly entering a coordinated turn with an angle of bank appropriate for the airplane being flown. Normally, this angle of bank should not exceed approximately 30 degrees. After the appropriate bank is established, a climbing turn should be started by smoothly applying back elevator pressure to increase the pitch attitude at a constant rate and to attain the highest pitch attitude as 90 degrees of turn is completed. As the climb is initiated in airplanes with fixed pitch propellers, full throttle may be applied, but it is applied gradually so that the maximum allowable RPM is not exceeded. In airplanes with constant speed propellers, power may be left at the normal cruise setting. Once the bank has been established, the angle of bank should remain constant until 90 degrees of turn is completed. Although the degree of bank is fixed during this climbing turn, it may appear to increase and, in fact, actually will tend to increase if allowed to do so as the maneuver continues. When the turn has progressed 90 degrees from the original heading, the pilot should begin rolling out of the bank at a constant rate while maintaining a constant pitch attitude. Since the angle of bank will be decreasing during the rollout, the vertical component of lift will increase slightly. For this reason, it may be necessary to release a slight amount of back elevator pressure in order to keep the nose of the airplane from rising higher. As the wings are being leveled at the completion of 180 degrees of turn, the pitch attitude should be noted by checking the outside references and the attitude indicator. This pitch attitude should be held momentarily while the plane is at the minimum controllable airspeed. Then the pitch attitude may be gently reduced to return to straight and level cruise flight. Since the airspeed is constantly decreasing throughout the maneuver, the effects of engine torque become more and more prominent. Therefore, right rudder pressure is gradually increased to control yaw and maintain a constant rate of turn and to keep the airplane in coordinated flight. The pilot should maintain coordinated flight by the feel of pressures being applied on the controls and by the ball instrument of the turn and slip indicator. If coordinated flight is being maintained, the ball will remain in the center of the race. To roll out of a left chandelle, the left aileron must be lowered to raise the left wing. This creates more drag than the aileron on the right wing, resulting in the tendency for the airplane to yaw to the left. With the low airspeed at this point, torque effect tries to make the airplane yaw to the left even more. Thus, there are two forces pulling the airplane's nose to the left: aileron drag and torque. To maintain coordinated flight, considerable right rudder pressure is required during the rollout to overcome the effects of aileron drag and torque. In a chandelle to the right, when control pressure is applied to begin the rollout, the aileron on the right wing is lowered. This creates more drag on that wing and tends to make the airplane yaw to the right. At the same time, the effect of torque at the lower speed is causing the airplane's nose to yaw to the left. Thus, aileron drag pulling the nose to the right and torque pulling to the left tend to neutralize each other. If excessive left rudder pressure is applied, the rollout will be uncoordinated. The rollout to the left can usually be accomplished with very little left rudder, since the effects of aileron drag and torque tend to neutralize each other. Releasing some right rudder, which has been applied to correct for torque, will normally give the same effect as applying left rudder pressure. When the wings become level and the ailerons are neutralized, the aileron drag disappears. Because of the low airspeed and high power, the effects of torque become the more prominent force and must continue to be controlled with rudder pressure. A rollout to the left is accomplished mainly by applying aileron pressure. During the rollout, right rudder pressure should be gradually released, and the left rudder applied only as necessary to maintain coordination. Even when the wings are level and aileron pressure is released, right rudder pressure must be held to counteract torque and hold the nose straight. Common errors in performance of chandelles are: failure to adequately clear the area, too shallow an initial bank resulting in a stall, too steep an initial bank resulting in failure to gain maximum performance, allowing the actual bank to increase after establishing initial bank angle, failure to start the recovery at the 90-degree point in the turn, allowing the pitch attitude to increase as the bank is rolled out during the second 90-degree of turn. Removing all of the bank before the 180-degree point is reached. Nose low on recovery, resulting in too much airspeed. Control roughness. Poor coordination, slipping or skidding. Stalling at any point during the maneuver. Execution of a steep turn instead of a climbing maneuver. Failure to scan for other aircraft. Attempting to perform the maneuver by instrument reference rather than visual reference. Lazy 8. The Lazy 8 is a maneuver designed to develop perfect coordination of controls through a wide range of airspeeds and altitudes so that certain accuracy points are reached with planned attitude and airspeed. In its execution, the dive, climb, and turn are all combined, and the combinations are varied and applied throughout the performance range of the airplane. It is the only standard flight training maneuver during which at no time do the forces on the controls remain constant. The Lazy 8 as a training maneuver has great value since constantly varying forces and attitudes are required. These forces must be constantly coordinated due not only to the changing combination of banks, dives, and climbs, but also to constantly varying airspeed. The maneuver helps develop subconscious feel, planning, orientation, coordination, and speed sense. It is not possible to do a Lazy 8 mechanically because the control pressures required for perfect coordination are never exactly the same. This maneuver derives its name from the manner in which the extended longitudinal axis of the airplane is made to trace a flight pattern in the form of a figure 8 lying on its side. A Lazy 8. See Figure 9-4. A Lazy 8 consists of two 180-degree turns in opposite directions while making a climb and a descent in a symmetrical pattern during each of the turns. At no time throughout the Lazy 8 is the airplane flown straight and level. Instead, it is rolled directly from one bank to the other with the wings level only at the moment the turn is reversed, the completion of each 180-degree change in heading. As an aid for making symmetrical loops of the 8 during each turn, prominent reference points should be selected on the horizon. The reference point selected should be 45 degrees, 90 degrees, and 135 degrees from the direction in which the maneuver is begun. Prior to performing a Lazy 8, the airspace behind and above should be clear of other air traffic. The maneuver should be entered from the straight and level flight at normal cruise power and at an airspeed recommended by the manufacturer or at the airplane's design maneuvering speed. The maneuver is started from level flight with a gradual climbing turn in the direction of the 45-degree reference point. The climbing turn should be planned and controlled so that the maximum pitch-up attitude is reached at the 45-degree point. The rate of rolling into the bank must be such as to prevent the rate of turn from becoming too rapid. As the pitch attitude is raised, the airspeed decreases, causing the rate of turn to increase. Since the bank also is being increased, it too causes the rate of turn to increase. Unless the maneuver is begun with a slow rate of roll, the combination of increasing pitch and increasing bank will cause the rate of turn to be so rapid that the 45-degree reference point will be reached before the highest pitch attitude is attained. At the 45-degree point, the pitch attitude should be at maximum and the angle of bank continuing to increase. Also, at the 45-degree point, the pitch attitude should start to decrease slowly toward the horizon and the 90-degree reference point. Since the airspeed is still decreasing, right rudder pressure will have to be applied to counteract torque. As the airplane's nose is being lowered toward the 90-degree reference point, the bank should continue to increase. Due to the decreasing airspeed, a slight amount of opposite aileron pressure may be required to prevent the bank from becoming too steep. When the airplane completes 90 degrees of the turn, the bank should be at the maximum angle, approximately 30 degrees. The airspeed should be at its minimum, 5 to 10 knots above stall speed, and the airplane pitch attitude should be passing through level flight. It is at this time that an imaginary line extending from the pilot's eye and parallel to the longitudinal axis of the airplane passes through the 90-degree reference point. Lazy 8s normally should be performed with no more than approximately a 30-degree bank. Steeper banks may be used, but control touch and technique must be developed to a much higher degree than when the maneuver is performed with a shallower bank. The pilot should not hesitate at this point, but should continue to fly the airplane into a descending turn so that the airplane's nose describes the same size loop below the horizon as it did above. As the pilot's reference line passes through the 90-degree point, the bank should be decreased gradually and the airplane's nose allowed to continue lowering. When the airplane has turned 135 degrees, the nose should be in its lowest pitch attitude. The airspeed will be increasing during this descending turn, so it will be necessary to gradually relax rudder and aileron pressure and to simultaneously raise the nose and roll the wings level. As this is being accomplished, the pilot should note the amount of turn remaining and adjust the rate of rollout and pitch change so that the wings become level and the original airspeed is attained in level flight just as the 180-degree point is reached. Upon returning to starting altitude and the 180-degree point, a climbing turn should be started immediately in the opposite direction toward the selected reference points to complete the second half of the 8 in the same manner as the first half. See Figure 9-5. Due to the decreasing airspeed, considerable right rudder pressure is gradually applied to counteract torque at the top of the 8 in both the right and left turns. The pressure will be greatest at the point of lowest airspeed. More right rudder pressure will be needed during the climbing turn to the right than in the turn to the left because more torque correction is needed to prevent yaw from decreasing the rate of turn. In the left climbing turn, the torque will tend to contribute to the turn. Consequently, less rudder pressure is needed. It will be noted that the controls are slightly crossed in the right climbing turn because of the need for left aileron pressure to prevent overbanking and right rudder to overcome torque. The correct power setting for the Lazy 8 is that which will maintain the altitude for the maximum and minimum airspeeds used during the climbs and descents of the 8. Obviously, if excess power were used, the airplane would have gained altitude when the maneuver is completed. If insufficient power were used, altitude would have been lost. Common errors in performance of Lazy 8s are failure to adequately clear the area, using the nose or top of engine cowl instead of the true longitudinal axis resulting in unsymmetrical loops, watching the airplane instead of the reference points, inadequate planning resulting in the peaks of the loops both above and below the horizon not coming in the proper place, control roughness, usually caused by attempts to counteract poor planning. Persistent gain or loss of altitude with the completion of each 8. Attempting to perform the maneuver rhythmically, resulting in poor pattern symmetry. Allowing the airplane to fall out of the tops of the loops rather than flying the airplane through the maneuver. Slipping and or skidding. Failure to scan for other traffic. End of Chapter 9. Recording by Dale Latham.
Chapter 10 of Airplane Flying Handbook, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Dorr. Airplane Flying Handbook, Volume 1 by the Federal Aviation Administration. Chapter 10, Night Operations. Night Vision. Generally, most pilots are poorly informed about night vision. Human eyes never function as effectively at night as the eyes of animals with nocturnal habits. But if humans learn how to use their eyes correctly and know their limitations, night vision can be improved significantly. There are several reasons for training to use the eyes correctly. One reason is the mind and eyes act as a team for a person to see well. both team members must be used effectively. The construction of the eyes is such that to see at night they are used differently than during the day. Therefore, it is important to understand the eye's construction and how the eye is affected by darkness. Innumerable light-sensitive nerves called cones and rods are located at the back of the eye or retina, a layer upon which all images are focused. These nerves connect to the cells of the optic nerve, which transmits messages directly to the brain. The cones are located in the center of the retina, and the rods are concentrated in a ring around the cones. See Figure 10-1. The function of the cones is to detect color, details, and faraway objects. The rods function when something is seen out of the corner of the eye or peripheral vision. They detect objects, particularly those that are moving, but do not give detail or color, only shades of gray. Both the cones and the rods are used for vision during daylight. Although there is not a clear-cut division of function, the rods make night vision possible. The rods and cones function in daylight and in moonlight, but in the absence of normal light, the process of night vision is placed almost entirely on the rods. The fact that rods are distributed in a band around the cones and do not lie directly behind the pupils makes off-center viewing, looking to one side of an object, important during night flight. During daylight, an object can be seen best by looking directly at it, but at night, a scanning procedure to permit off-center viewing of the object is more effective. Therefore, the pilot should consciously practice this scanning procedure to improve night vision. The eye's adaptation to darkness is another important aspect of night vision. When a dark room is entered, it is difficult to see anything until the eyes become adjusted to the darkness. Most everyone has experienced this after entering a darkened movie theater. In this process, the pupils of the eyes first enlarge to receive as much of the available light as possible. After approximately 5 to 10 minutes, the cones become adjusted to the dim light, and the eyes become 100 times more sensitive to the light than they were before the dark room was entered. Much more time, about 30 minutes, is needed for the rods to become adjusted to darkness. But when they do adjust, they are about 100,000 times more sensitive to light than they were in the lighted area. After the adaptation process is complete, much more can be seen, especially if the eyes are used correctly. After the eyes have adapted to the dark, the entire process is reversed when entering a lighted room. The eyes are first dazzled by the brightness, but become completely adjusted in a very few seconds, thereby losing their adaptation to the dark. Now, if the dark room is re-entered, the eyes again go through the long process of adapting to the darkness. The pilot before and during night flight must consider the adaptation process of the eyes. First, the eyes should be allowed to adapt to the low level of light, and then they should be kept adapted. After the eyes have become adapted to the darkness, the pilot should avoid exposing them to any bright white light that will cause temporary blindness and could result in serious consequences. Temporary blindness caused by an unusually bright light may result in illusions or after images until the eyes recover from the brightness. The brain creates these illusions reported by the eyes. This results in misjudging or incorrectly identifying objects, such as mistaking slanted clouds for the horizon or populated areas for a landing field. Vertigo is experienced as a feeling of dizziness and imbalance that can create or increase illusions. The illusions seem very real, and pilots at every level of experience and skill can be affected. Recognizing that the brain and eyes can play tricks in this manner is the best protection for flying at night. Good eyesight depends upon physical condition. Fatigue, colds, vitamin deficiency, alcohol, stimulants, smoking, or medication can seriously impair vision. Keeping these facts in mind and taking adequate precautions should safeguard night vision. In addition to the principles previously discussed, the following items will aid in increasing night vision effectiveness. Adapt the eyes to darkness prior to flight and keep them adapted. About 30 minutes is needed to adjust the eyes to maximum efficiency after exposure to a bright light. If oxygen is available, use it during night flying. Keep in mind that a significant deterioration in night vision can occur at cabin altitudes as low as 5,000 feet. Close one eye when exposed to bright light to help avoid the blinding effect. Do not wear sunglasses after sunset. Move the eyes more slowly than in daylight. Blink the eyes if they become blurred. Concentrate on seeing objects. Force the eyes to view off-center. Maintain good physical condition. Avoid smoking, drinking, and using drugs that may be harmful. Night illusions. In addition to night vision limitations, pilots should be aware that night illusions could cause confusion and concerns during night flying. The following discussion covers some of the common situations that cause illusions associated with night flying. On a clear night, distant stationary lights can be mistaken for stars or other aircraft. Even the northern lights can confuse a pilot and indicate a false horizon. Certain geometrical patterns of ground lights, such as a freeway, runway, approach, or even lights on a moving train, can cause confusion. Dark nights tend to eliminate reference to a visual horizon. As a result, pilots need to rely less on outside references at night and more on flight and navigation instruments. Visual autokinesis can occur when a pilot stares at a single light source for several seconds on a dark night. The result is that the light will appear to be moving. The autokinesis effect will not occur if the pilot expands the visual field. It is a good procedure not to become fixed on one source of light. Distractions and problems can result from a flickering light in the cockpit, anti-collision light, strobe lights, or other aircraft lights, and can cause flicker vertigo. If continuous, the possible physical reactions can be nausea, dizziness, grogginess, unconsciousness, headaches, or confusion. The pilot should try to eliminate any light source causing blinking or flickering problems in the cockpit. A black hole approach occurs when the landing is made from over water or non-lighted terrain, where the runway lights are the only source of light. Without peripheral visual cues to help, pilots will have trouble orientating themselves relative to Earth. The runway can seem out of position, downsloping or upsloping, and in the worst case, results in landing short of the runway. If an electronic glide slope or visual approach slope indicator, VASI, is available, it should be used. If navigation aids, NAV-aids, are unavailable, careful attention should be given to using the flight instruments to assist in maintaining orientation and a normal approach. If at any time the pilot is unsure of his or her position or attitude, a go-around should be executed. Bright runway and approach lighting systems, especially where few lights illuminate the surrounding terrain, may create the illusion of less distance to the runway. In this situation, the tendency is to fly a higher approach. Also, when flying over terrain with only a few lights, it will make the runway recede or appear farther away. With this situation, the tendency is common to fly a lower than normal approach. If the runway has a city in the distance, on higher terrain, the tendency will be to fly a lower than normal approach. A good review of the airfield layout and boundaries before initiating any approach will help the pilot maintain a safe approach angle. Illusions created by runway lights result in a variety of problems. Bright lights or bold colors advance the runway, making it appear closer. Night landings are further complicated by the difficulty of judging distance and the possibility of confusing approach and runway lights. For example, when a double row of approach lights joins the boundary lights of the runway, there can be confusion where the approach lights terminate and runway lights begin. Under certain conditions, approach lights can make the aircraft seem higher in a turn to final than when its wings are level. Pilot equipment. Before beginning a night flight, carefully consider personal equipment that should be readily available during the flight. At least one reliable flashlight is recommended as standard equipment on all night flights. Remember to place a spare set of batteries in the flight kit. A D-cell size flashlight with a bulb switching mechanism that can be used to select white or red light is preferable. The white light is used while performing the pre-flight visual inspection of the airplane, and the red light is used when performing cockpit operations. Since the red light is non-glaring, it will not impair night vision. Some pilots prefer two flashlights, one with the white light for pre-flight and the other a pen light type with the red light. The latter can be suspended by a string from around the neck to ensure the light is always readily available. One word of caution. If a red light is used for reading an aeronautical chart, the red features of the chart will not show up. Aeronautical charts are essential for night cross-country flight, and if the intended course is near the edge of the chart, the adjacent chart should also be available. The lights of cities and towns can be seen at surprising distances at night, and if this adjacent chart is not available to identify those landmarks, confusion could result. Regardless of the equipment used, organization of the cockpit eases the burden on the pilot and enhances safety. Airplane equipment and lighting. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, specifies the basic minimum airplane equipment required for night flight. This equipment includes only basic instruments, lights, electrical energy source, and spare fuses. The standard instruments required for instrument flight under 14 CFR Part 91 are a valuable asset for aircraft control at night. An anti-collision light system, including a flashing or rotating beacon and position lights, is required airplane equipment. Airplane position lights are arranged similar to those of boats and ships. A red light is positioned on the left wingtip, a green light on the right wingtip, and a white light on the tail. See Figure 10-2. This arrangement provides a means by which pilots can determine the general direction of movement of other airplanes in flight. If both the red and green light of another aircraft were observed, the airplane would be flying toward the pilot and could be on a collision course. Landing lights are not only useful for taxi, takeoffs, and landings, but also provide a means by which airplanes can be seen at night by other pilots. The Federal Aviation Administration, FAA, has initiated a voluntary pilot safety program called Operation Lights On. The lights on idea is to enhance the see and be seen concept of averting collisions both in the air and on the ground, and to reduce the potential for bird strikes. Pilots are encouraged to turn on their landing lights when operating within 10 miles of an airport. This is for both day and night or in conditions of reduced visibility. This should also be done in areas where flocks of birds may be expected. Although turning on aircraft lights supports the see and be seen concept, pilots should not become complacent about keeping a sharp lookout for other aircraft. Most aircraft lights blend in with the stars or the lights of the cities at night and go unnoticed unless a conscious effort is made to distinguish them from other lights. Airport and navigation lighting aids. The lighting systems used for airports, runways, obstructions, and other visual aids at night are other important aspects of night flying. Lighted airports located away from congested areas can be identified readily at night by the lights outlining the runways. Airports located near or within large cities are often difficult to identify in the maze of lights. It is important not only to know the exact location of an airport relative to the city, but also to be able to identify these airports by the characteristics of their lighting pattern. Aeronautical lights are designed and installed in a variety of colors and configurations, each having its own purpose. Although some lights are used only during low ceiling and visibility conditions, this discussion includes only the lights that are fundamental to visual flight rules, VFR, night operation. It is recommended that prior to a night flight, and particularly a cross-country night flight, the pilot check the availability and status of lighting systems at the destination airport. This information can be found on aeronautical charts and in the airport/facility directory. The status of each facility can be determined by reviewing pertinent notices to airmen, NOTAMs. A rotating beacon is used to indicate the location of most airports. The beacon rotates at a constant speed, thus producing what appears to be a series of light flashes at regular intervals. These flashes may be one or two different colors that are used to identify various types of landing areas. For example, lighted civilian land airports, alternating white and green. Lighted civilian water airports, alternating white and yellow. Lighted military airports, alternating white and green but are differentiated from civil airports by dual-peaked, too quick, white flashes, then green. Beacons producing red flashes indicate obstructions or areas considered hazardous to aerial navigation. Steady burning red lights are used to mark obstructions on or near airports and sometimes to supplement flashing lights on en route obstructions. High-intensity flashing white lights are used to mark some supporting structures of overhead transmission lines that stretch across rivers, chasms, and gorges. These high-intensity lights are also used to identify tall structures such as chimneys and towers. As a result of the technological advancements in aviation, runway lighting systems have become quite sophisticated to accommodate takeoffs and landings in various weather conditions. However, the pilot whose flying is limited to VFR only needs to be concerned with the following basic lighting of runways and taxiways. The basic runway lighting system consists of two straight parallel lines of runway edge lights defining the lateral limits of the runway. These lights are aviation white, although aviation yellow may be substituted for a distance of 2,000 feet from the far end of the runway to indicate a caution zone. At some airports, the intensity of the runway edge lights can be adjusted to satisfy the individual needs of the pilot. The length limits of the runway are defined by straight lines of lights across the runway ends. At some airports, the runway threshold lights are aviation green, and the runway end lights are aviation red. At many airports, the taxiways are also lighted. A taxiway edge lighting system consists of blue lights that outline the usable limits of taxi paths. Preparation and pre-flight. Night flying requires that pilots be aware of and operating within their abilities and limitations. Although careful planning of any flight is essential, night flying demands more attention to the details of pre-flight preparation and planning. Preparation for a night flight should include a thorough review of the available weather reports and forecasts, with particular attention given to temperature dew point spread. A narrow temperature dew point spread may indicate the possibility of ground fog. Emphasis should also be placed on wind direction and speed, since its effect on the airplane cannot be as easily detected at night as during the day. On night cross-country flights, appropriate aeronautical charts should be selected, including the appropriate adjacent charts. Course lines should be drawn in black to be more distinguishable. Prominently lighted checkpoints along the prepared course should be noted. Rotating beacons at airports, lighted obstructions, lights of cities or towns, and lights from major highway traffic all provide excellent visual checkpoints. The use of radio navigation aids and communication facilities adds significantly to the safety and efficiency of night flying. All personal equipment should be checked prior to flight to ensure proper functioning. It is very disconcerting to find at the time of need that a flashlight, for example, does not work. All airplane lights should be turned on momentarily and checked for operation. Position lights can be checked for loose connections by tapping the light fixture. If the lights blink while being tapped, further investigation to determine the cause should be made prior to flight. The parking ramp should be examined prior to entering the airplane. During the day, it is quite easy to see step ladders, chuck holes, wheel chocks, and other obstructions. But at night, it is more difficult. A check of the area can prevent taxiing mishaps. Starting, taxiing, and run-up. After the pilot is seated in the cockpit and prior to starting the engine, all items and materials to be used on the flight should be arranged in such a manner that they will be readily available and convenient to use. Extra caution should be taken at night to assure the propeller area is clear. Turning the rotating beacon on or flashing the airplane position lights will serve to alert persons nearby to remain clear of the propeller. To avoid excessive drain of electrical current from the battery, it is recommended that the unnecessary electrical equipment be turned off until after the engine has been started. After starting and before taxiing, the taxi or landing light should be turned on. Continuous use of the landing light with RPM power settings normally used for taxiing may place an excessive drain on the airplane's electrical system. Also, overheating of the landing light could become a problem because of inadequate airflow to carry the heat away. Landing lights should be used as necessary while taxiing. When using landing lights, consideration should be given to not blinding other pilots. Taxi slowly, particularly in congested areas. If taxi lines are painted on the ramp or taxiway, these lines should be followed to ensure a proper path along the route. The before takeoff and run-up should be performed using the checklist. During the day, forward movement of the airplane can be detected easily. At night, the airplane could creep forward without being noticed unless the pilot is alert for this possibility. Hold or lock the brakes during the run-up and be alert for any forward movement. Takeoff and climb. Night flying is very different from day flying and demands more attention of the pilot. The most noticeable difference is the limited availability of outside visual references. Therefore, flight instruments should be used to a greater degree in controlling the airplane. This is particularly true on night takeoffs and climbs. The cockpit light should be adjusted to a minimum brightness that will allow the pilot to read the instruments and switches and yet not hinder the pilot's outside vision. This will also eliminate light reflections on the windshield and windows. After ensuring that the final approach and runway are clear of other air traffic, or when cleared for takeoff by the tower, the landing lights and taxi lights should be turned on and the airplane lined up with the center line of the runway. If the runway does not have centerline lighting, use the painted center line and the runway edge lights. After the airplane is aligned, the heading indicator should be noted or set to correspond to the known runway direction. To begin the takeoff, the brake should be released and the throttle smoothly advanced to maximum allowable power. As the airplane accelerates, it should be kept moving straight ahead, between and parallel to the runway edge lights. The procedure for night takeoffs is the same as for normal daytime takeoffs, except that many of the runway visual cues are not available. Therefore, the flight instruments should be checked frequently during the takeoff to ensure the proper pitch attitude, heading, and airspeed are being attained. As the airspeed reaches the normal liftoff speed, the pitch attitude should be adjusted to that which will establish a normal climb. This should be accomplished by referring to both outside visual references, such as lights, and to the flight instruments. See Figure 10-3. After becoming airborne, the darkness of night often makes it difficult to note whether the airplane is getting closer to or farther from the surface. To ensure the airplane continues in a positive climb, be sure a climb is indicated on the attitude indicator, vertical speed indicator, VSI, and altimeter. It is also important to ensure the airspeed is at best climb speed. Necessary pitch and bank adjustments should be made by referencing the attitude and heading indicators. It is recommended that turns not be made until reaching a safe maneuvering altitude. Although the use of landing lights provides help during the takeoff, they become ineffective after the airplane has climbed to an altitude where the light beam no longer extends to the surface. The light can cause distortion when it is reflected by haze, smoke, or fog that might exist in the climb. Therefore, when the landing light is used for the takeoff, it may be turned off after the climb is well established, provided other traffic in the area does not require its use for collision avoidance. Orientation and navigation. Generally, at night it is difficult to see clouds and restrictions to visibility, particularly on dark nights or under overcast. The pilot flying under VFR must exercise caution to avoid flying into clouds or a layer of fog. Usually, the first indication of flying into restricted visibility conditions is the gradual disappearance of lights on the ground. If the lights begin to take on an appearance of being surrounded by a halo or glow, the pilot should use caution in attempting further flight in that same direction. Such a halo or glow around lights on the ground is indicative of ground fog. Remember that if a descent must be made through fog, smoke, or haze in order to land, the horizontal visibility is considerably less when looking through the restriction than it is when looking straight down through it from above. Under no circumstances should a VFR night flight be made during poor or marginal weather conditions unless both the pilot and aircraft are certified and equipped for Flight Under Instrument Flight Rules, IFR. The pilot should practice and acquire competency in straight and level flight, climbs and descents, level turns, climbing and descending turns, and steep turns. Recovery from unusual attitudes should also be practiced, but only on dual flights with a flight instructor. The pilot should also practice these maneuvers with all the cockpit lights turned off. This blackout training is necessary if the pilot experiences an electrical or instrument light failure. Training should also include using the navigation equipment and local nav aids. In spite of fewer references or checkpoints, night cross-country flights do not present particular problems if pre-planning is adequate, and the pilot continues to monitor position, time estimates, and fuel consumed. Nav aids, if available, should be used to assist in monitoring en route progress. Crossing large bodies of water at night in single-engine airplanes could be potentially hazardous, not only from the standpoint of landing, ditching, in the water, but also because, with little or no lighting, the horizon blends with the water, in which case depth perception and orientation become difficult. During poor visibility conditions over water, the horizon will become obscure and may result in a loss of orientation. Even on clear nights, the stars may be reflected on the water's surface, which could appear as a continuous array of lights, thus making the horizon difficult to identify. Lighted runways, buildings, or other objects may cause illusions to the pilot when seen from different altitudes. At an altitude of 2,000 feet, a group of lights on an object may be seen individually, while at 5,000 feet or higher, the same lights could appear to be one solid light mass. These illusions may become quite acute with altitude changes, and if not overcome, could present problems in respect to approaches to lighted runways. Approaches and landings. When approaching the airport to enter the traffic pattern and land, it is important that the runway lights and other airport lighting be identified as early as possible. If the airport layout is unfamiliar to the pilot, sighting of the runway may be difficult until very close in due to the maze of lights observed in the area. See Figure 10-4. The pilot should fly toward the rotating beacon until the lights outlining the runway are distinguishable. To fly a traffic pattern of proper size and direction, the runway threshold and runway edge lights must be positively identified. Once the airport lights are seen, these lights should be kept in sight throughout the approach. Distance may be deceptive at night due to limited lighting conditions. A lack of intervening references on the ground and the inability of the pilot to compare the size and location of different ground objects cause this. This also applies to the estimation of altitude and speed. Consequently, more dependence must be placed on flight instruments, particularly the altimeter and the airspeed indicator. When entering the traffic pattern, allow for plenty of time to complete the before landing checklist. If the heading indicator contains a heading bug, setting it to the runway heading will be an excellent reference for the pattern legs. Every effort should be made to maintain the recommended airspeeds and execute the approach and landing in the same manner as during the day. A low, shallow approach is definitely inappropriate during a night operation. The altimeter and VSI should be constantly cross-checked against the airplane's position along the base leg and final approach. A visual approach slope indicator, VASI, is an indispensable aid in establishing and maintaining a proper glide path. See Figure 10-5. After turning onto the final approach and aligning the airplane midway between the two rows of runway edge lights, the pilot should note and correct for any wind drift. Throughout the final approach, pitch and power should be used to maintain a stabilized approach. Flaps should be used the same as in a normal approach. Usually, halfway through the final approach, the landing light should be turned on. Earlier use of the landing light may be necessary because of operation lights on or for local traffic considerations. The landing light is sometimes ineffective since the light beam will usually not reach the ground from higher altitudes. The light may even be reflected back into the pilot's eyes by an existing haze, smoke, or fog. This disadvantage is overshadowed by the safety considerations provided by using the Operation Lights On procedure around other traffic. The round out and touchdown should be made in the same manner as in day landings. At night, the judgment of height, speed, and sink rate is impaired by the scarcity of observable objects in the landing area. The inexperienced pilot may have a tendency to round out too high until attaining familiarity with the proper height for the correct round out. To aid in determining the proper round out point, continue a constant approach descent until the landing lights reflect on the runway and tire marks on the runway can be seen clearly. At this point, the round out should be started smoothly and the throttle gradually reduced to idle as the airplane is touching down. See Figure 10-6. During landings, without the use of landing lights, The roundout may be started when the runway lights at the far end of the runway first appear to be rising higher than the nose of the airplane. This demands a smooth and very timely roundout and requires that the pilot feel for the runway surface using power and pitch changes as necessary for the airplane to settle slowly to the runway. Blackout landing should always be included in night pilot training as an emergency procedure. Night emergencies. Perhaps the pilot's greatest concern about flying a single-engine airplane at night is the possibility of a complete engine failure and the subsequent emergency landing. This is a legitimate concern, even though continuing flight into adverse weather and poor pilot judgment account for most serious accidents. If the engine fails at night, several important procedures and considerations to keep in mind are: maintain positive control of the airplane and establish the best glide configuration and airspeed. Turn the airplane towards an airport or away from congested areas. Check to determine the cause of the engine malfunction, such as the position of fuel selectors, magneto switch, or primer. If possible, the cause of the malfunction should be corrected immediately and the engine restarted. Announce the emergency situation to Air Traffic Control, ATC, or Unicom. If already in radio contact with a facility, do not change frequencies unless instructed to change. If the condition of the nearby terrain is known, turn towards an unlighted portion of the area. Plan an emergency approach to an unlighted portion. Consider an emergency landing area close to public access if possible. This may facilitate rescue or help if needed. Maintain orientation with the wind to avoid a downwind landing. Complete the before landing checklist and check the landing lights for operation at altitude and turn on in sufficient time to illuminate the terrain or obstacles along the flight path. The landing should be completed in the normal landing attitude and the slowest possible airspeed. If the landing lights are unusable and outside visual references are not available, the airplane should be held in level landing attitude until the ground is contacted. After landing, turn off all switches and evacuate the airplane as quickly as possible. End of Chapter 10. End of Volume 1 of the Airplane Flying Handbook, FAA-H-8083-3A by the Federal Aviation Administration.